are missing.
Indeed, we are doing both, like live YouTube streaming and also local recording, just to be sure every day.
Yes. So it will, whatever I say will remain.
Yes, in many different places.
In many different places, it cannot be erased. If I say something very wrong, it cannot be erased. I like to do.
We are on YouTube anyway. Who starts the recording?
Yeah, I'm recording. I will record.
Okay, good.
Okay, you tell me when we can start. If the number of
yeah, just I would say in 2 minutes we start. We start 35, just to.
Okay, fine.
Okay, I think we can now start.
Okay.
So, yeah, welcome everyone to this last and fifth day of the workshop. The first session, in the first session, we have 4 speakers, among which Fedele, Lizzi, Gabriele Gionti, Alessia Platania, and Alexey Koshelev. And our first speaker is Fedele Lizzi, who's going to speak about quantum spacetime and non-commutative geometry. So please, Fedele. And obvious. Yeah, and obvious.
So yes, please. I got the invitation, or one of the later messages. The organizers were saying that I could put pronouns after my name if I so liked. So I put a pronoun, whatever is a pronoun. So I put whatever as a pronoun, and I will enforce the whatever rule for pronouns for during my talk. I will, so the obs was observers. And I will, discuss work which I done in various collaborations, various combinations, but the names which are involved are Maria Dimitrievich-Ciric, Nicola Konik, Max Kurkov, Mattia Manfredonia, Flavio Mercati, and Timothée Poulain, and Patrizia Vitale. Although some of those are for the last part, which I doubt I will be able to cover. Okay. Let's start. Gravity is the theory of curved space-time. It's the dynamical variable is space-time itself. In fact, one way to quantize is to consider the metric as a field to quantize. Okay, these excellent things have been done with this, but this has not been completely successful, and is in good company because, of course, there is not a completely successful theory of quantum gravity. Otherwise, there are different meeting focalizing on something which is working. So what I worked for many years, and I still work on, is the idea of non-commutative geometry applied to quantum gravity. And the idea there is that since the object to quantize is space-time, perhaps one should use a quantum space-time. And I will concentrate on dynamics, this kinematics, not dynamics. So the quantum space-time is the object which is in the background. I am not yet really quantizing it. I just want to understand what is a quantum space-time, a promising quantum space-time. And in the line with this meeting, I will concentrate on the role of observers, which are quantum observers in a quantum space-time. And I will try to say something. Okay, you know that the most famous non-commutative space is the one described by non-commuting coordinates. Not all non-commutative spaces are just of this kind. I will be in this framework, but I want to stress that not all non-commutative spaces are 2 coordinates which don't commute. However, it's true that the most famous one goes under the name of Doppler, Fredenhagen, and Roberts. There is a T missing. Or Moyal or Grönwald-Moyal, and produce the product. And it's really a reproduction of the quantum mechanics one. It was featured in the famous article of Seiberg and Witten. So after their Wittenization, it became a very famous topic. And about now 20 years ago, really, many years ago, and is really probably the simplest one. And the commutator between the coordinate functions is a constant, and this is really the quantum mechanics formally. So, which was good because we could use quantum mechanical things. However, although I worked on it, I never really believed that this was the final answer. This was because this breaks Lorentz invariance in a bad way. It maintains translation invariance, but it breaks Lorentz invariance, it makes rotations. This is not a problem for quantum mechanics. There is not in general a symmetry which rotates coordinates into momenta. But for Lorentz transformation, I want to have Poincaré, but the problem is with Lorentz, not with translation. This would mean that if I have this theta mu nu, this will be a fundamental antisymmetric tensor. So like f mu nu, it has two directions, a vector and a pseudo vector. And this would characterize our universe. And in fact, most of the predictions were based on this, but it would show up in cosmology. And the recent data, I did work on something about 20 years ago again, but the limits now are basically, they're more and more stringent, and this CMB, cosmic microwave background, is leaving very little room. But in general, apart from this issue, quantization of gravity, you should have symmetries. You cannot go away with symmetry. And the answer is that quantum space-time will require quantum symmetries. And we do have quantum symmetries. Quantum groups and Hopf algebras are the framework in which we have the formation of symmetries, and they have developed in parallel to non-commutative geometry with several intersections. One way to define quantum groups is to say that the functions on the group do not commute apart from the elements of the group. I could talk a lot in various aspects. I want to concentrate in one, and if I have time, which I doubt, in two particular cases in which I have a quantum space-time which came from a quantum group, from a Hopf algebra. And this goes under the name of Kappa-Poincaré. And I will mention a few features of that, and I will, as I said, concentrate on the role of observers. So this is the homogeneous space of this quantum symmetry. I will say something of this quantum symmetry, but for what we are concerned, it has this commutator. Now, lambda was originally called 1 over kappa. I call it lambda because I like to have the idea that the symmetry disappears when lambda goes to 0. So lambda is a small parameter. Kappa is more similar to the speed of light. So it's something which gives you normal or non or commutative spaces when it goes to infinity. So I use lambda, and as I said, there are some variations of this, but I don't know if I will have no time. So first of all, I will to show you how I want to describe this space. I will remind you, of course, you know this very well, a case study, some features of quantum phase-time of a particle. So this is well known. I have a 6-dimensional classical space. I introduce commutation relations which are non-trivial, and they are of the constant kind. And I have a 6-dimensional space, but usually I represent this on L2, on the Hilbert space of a smaller space, L2 over R3. Q is okay, is because I have the position space, and I represent the operators as Q as multiplicative operator and P as a derivative operator. And notice that I start with a 6-dimensional space, but L2 is L2 only of 3-dimensional And Q and P are self-adjoint unbounded operators with a dense domain. And for each I, the spectrum is the real line. They have no proper eigenvectors, but they have improper eigenvectors, which are distributions. You know them. And now, why the three-dimensional space? Because it's possible to have a simultaneous complete set of computing observables, which are the 3Q, and the improper eigenvectors are the delta functions. And for a particular momentum, the improper eigenfunctions are the plane waves. Now, how do I find these plane waves? Well, I solve the eigenvalue equation, and I find that this is solved by this kind of functions with a vector alpha, but I want this operator to be self-adjoint, symmetric, and with a dense domain of the adjoint. And so no function of this kind is square integrable, so there are no proper eigenfunctions. But I know that it's self-adjoint on the domain of absolutely continuous function. The alpha must be pure imaginary as a basis in the spectral decomposition, and you find plane waves. Now, with various, depending on your mathematical sensibility, you may be worrying about domains or not, but you know that the improper eigenfunctions are distribution or the basis for the spectral decomposition. And there are infinite plane waves with a precise frequency, and they are not vector in Hilbert space, but we more or less know what we mean when we talk of a particle of momentum h bar k. So it really depends on your mathematical sensibilities, but we all understand what we mean. Okay, we have chosen Q as a complete set of observables, and the description of a quantum state is through the modulus of the wave function, normalized in a proper way, and this is a density probability. Now, remember that psi is a complex vector. It contains information about the density probability of momentum as well, because it's all Hilbert spaces are isomorphic, so I just could have chosen P as a complete set, and I just reverse plane waves with delta function, and I have a Fourier transform. So the probability of the momentum is the Fourier transform of this psi, which you sometimes call phi or psi tilde. Fourier transform is an isometry. So if I have a normalized function, which means the probability is, I can use it as a probability. If I do the Fourier transform with the proper factors of 2 pi, of course, I find again a normalized psi of p. And I can, and of course, I have other choices. I can take number operators, angular momentum, combinations, and multiplics. Now, different observer will have his own Hilbert space, no? A psi of x, and a different observer will have a psi of x prime. So I have to do a tensor product. I don't say it normally, because this is not a problem. I can make unitary transformation from one set to another, and implicitly I'm using a mathematical object, which I will not describe in detail, which is a coproduct. Namely, if I have a representation of one group, really, one Lie algebra, then I can reproduce it a representation for 2 observers, because it's trivial, we know what to do. They would agree on this. But quantum groups have taught us that there is more than the Lie algebra structure, because symmetries are described by Hopf algebra, because I put together representation. Now, as I said, normally, if they have no deformation, this is done in a co-commutative way. I will not describe what we do, but normally we know how to put together the representation of 2 observers which are in 2 different positions, translated, boosted, rotated. They can talk to each other without any problem. But if the algebra is deformed, so is the group. And I will describe one example, or maybe 2, in which interesting things happen. I will not go into the full formalism. I will go in more details probably in the proceedings. Okay, this was for quantum space. This was a case study to remind you to set the stage. The formation parameter was h bar. Now I will go for Kappa-Minkowski, in which the formation parameter is lambda, and I will leave h bar alone. For the moment, and this moment is long because although I'm working on it, the kinematics which I'll do will be a kinematics only of space-time. I'm not putting a dynamics, so I'm not putting momentum. So, but it's a relativistic space to some extent. No, so I will have to worry about Poincaré transformations, of course. So I want to look for a representation on the excess of my kappa Poincaré on L2 over 3. So although I have 4 operators, the x mu, x0, and xi, the complete set of observables, as I will see, is 3-dimensional. So I will go on L2 over 3. And I can define the operators in this way. So I'm using the techniques of quantum mechanics. If I have a non-commuting algebra, I can represent it as operators. And so x bar I is this one, and it's multiplication, x hat, and x0, if I want to represent the commutation relation, is a dilation. And I have to put a 3/2 because R doesn't commute with dr, and therefore I need a 3/2. This is actually the number of dimensions divided by 2. So I can do it in other dimensions, and there will be a different factor here. And C5 dilations is clear that the polar basis is more appropriate. And in fact, I can rewrite the Kappa-Minkowski commutation relation in terms of r, theta, and phi, and t. And t, x0, commutes with the functions of theta, with functions of phi, but doesn't commute with r. And it's a dilation. It doesn't commute with r. Commutation with r is r. And I have an uncertainty relation. The uncertainty relation is not like the one that we know from Heisenberg or even the deformed. Is this: if the uncertainty in time multiplied by the uncertainty in the radius is lambda over 2 times the expectation value of r. So there is no uncertainty in the origin. Okay, what is the spectrum of the time operator? And then I do the same thing that I did for plane waves. They are monomials. What were plane waves were monomials, and I can see that this alpha is spurious. I can see that the monomials give real eigenvalues, self-adjoint operators, only when alpha is of this kind. So these are the equivalent of plane waves. So they are the eigenfunctions of time in this space. And this distribution have the correct dimensions. And I need a factor of tau to write things in this way, which is a convenient way. A factor of lambda. Really, I would need a length, something with the dimension of length. But there is a natural, just to have a log for dimensional reasons. I do have a scale, and I use this one. In principle, it could be a different one, but it would be rather just looking for troubles. Okay, for Q and P, I had a complete set of observables, and I could go from one to the other with a Fourier transform. And for Kappa-Minkowski, instead, I go back and forth between these two sets of complete commuting observables with a Mellin transform. There are various versions of Mellin transform, but this is the one which I use. There are factors of 3/2 here which are important. And another important thing is that I will have to always use the correct measure when I integrate in R. So R is not a one-dimensional variable, but it's on the outline, but it's defined with the measure which is dr r squared dr. This is the measure. This is something very important. If you don't realize this, we will do wrong things. And in fact, you see that these two powers are different because this integration dr, there would be an r squared, and this would be r to the 3/2, which would match this. So these are one inverse of the other. And in this way, I can interpret this as probability density, the probability for the probability to find a particle either in position r or in time tau. Just to give some example, I have this usual thing. If I take something which I localize in this way, it's a little conical cylinder, trapezoidal cylinder, I don't know how to say it. I take this cone and I take just a little area. This is just to make calculation simple. So I localize a particle in this. This is A, and there is an angle of this kind. And so if I take the limit of A going to 0, I'm localizing in Z0 at some distance. And if I do the Mellin transform, I will find that I find a constant. It's like the Gaussian which gets flattened. And therefore, I can see in this case, just as I say, when I take a Gaussian in momentum and position, that if I try to localize in position, I delocalize in momentum, and vice versa. And the same thing happens here, but it's different formula, different transforms, but it's the same. Localization in, here it is, or these formulas, we see when A goes to 0, this goes to 0, but then the normalization will diverge, and etc. So I put the formula, but the gist of what I'm saying is that a sharp localizing a particle far away from the origin implies that the particle cannot be localized in time, but it has to be far away from the origin. At the origin, I can localize. And this is in perfect agreement with the localization of Kappa-Minkowski. So now comes the issue which is relevant for this conference. I have chosen an origin, so there is a special point. I've broken translations. So there is a place in the universe, which is the origin. Sorry that this is in the same session with Gabriele, but is this again, I'm back to ether. There is a point where this Kappa God is sitting. Well, everything I'm doing is related to one observer, which is me. And I'm assuming the existence of this observer, which measures the localization of states. So this observer is located at the origin, and he can measure with absolute precision where she is. I'm enforcing the whatever pronoun rule. For him, for this observer, there is an here and now, and makes sense. So I know where I am, and I or she can localize precision the states. But I cannot localize things which are away from me. And this is a non-commutative of Kappa-Minkowski. So what about other observers? What will they do? Will they be able to localize a state which is not localizable for me? Well, if I want independence of observers, yes, they can localize where they are, but so there is a paradox. Okay, a different observer the problem is translations here. So a different observer will generally be Poincaré transformed, will be translated, rotated, and boosted. But and these operations are done with an element of the Poincaré group. But I have kappa Poincaré. So I have to require invariance for my transformation under the transformation of x, which goes into x prime. And you see, I'm putting here a tensor product because this is a tensor product of the elements of my Hilbert space, operators times an element of the Poincaré group. So in general, we don't write this because there is no problem in this operation, which are gamma mu, x mu. But now I have a quantum group. I'm skipping all the details, but one of the consequences, actually, it worked the other way around. First, Kappa Poincaré was introduced by Majid, Roued, Lukierski, and Tolstoy. I'm probably forgetting somebody. And then Kappa-Minkowski was introduced, again, more or less by the same people. And then the deformation of the group was introduced. And this is slightly basis dependent. So I'm going to use a particular basis, which is due to Zagreski, and it's also discussed in papers by Mercati and Servola in Spiriting What I Need. So what happens is that the translations do not commute. And this commutator is exactly the same of the coordinates. So I0 AI is AI and the rest is 0. The element translation, I mean the parameter of the translation. The elements of the Lorentz transformation instead commute, and then the Lorentz transformation with translation, I have a complicated object which I will not need for this talk. What I need is this. What I need is that the translations do not commute.
Fedele, you have 5 minutes.
How many?
5 minutes. 5.
Yes. I represent the Kappa-Minkowski algebras operators, but I have chosen an operator. But then, in order to choose this operator, I have to take also the algebra which involves the observers as well, with their own set of observables. And I call this new set of state as PK, sorry. And our generalized Hilbert space will now be enlarged, not only functions of space-time, either R or tau, but functions of A and lambda. And I can also represent the transformations, the parameters, which have now, the parameter of the translations, which have now become operators as well, in this way. I don't want to go into details. Everything is in the papers and will be in the proceedings with more detail. But in half an hour, we're going to give just the impression. The space of observers is non-commutative. And the non-commutative is present only for, is mainly present for translations. So I want to describe the space of observers seen as states. So I consider the observer located at the origin, me, which is reached by the identity transformation. So if there is another observer, which is where I am, nothing happens. I have to use the coproduct, but the states of the two observers which are sitting in the same place are the same. So this is a consistency check. So the coincident observer will have the same concept. I can also rotate them. So if I make a rotation, nothing happens. Now, but if I make now a transformation of states, what will the other observer see? So I have to identify X with one tensor X. I have an extended algebra, which extends Kappa-Minkowski, and using the formalism of quantum mechanics. So this is position of states and observable. Now I have the key points. I cannot localize position states, but I cannot localize also where the observer is. As long as I don't care about rotation. Rotation is not a problem. So two observers just rotate and one with each other, no problem. But I cannot localize the observer. I can, and I will do this, I will skip, I can also do all the transformations in 1+1 dimensions, but I have no time. And I can have all the states, and I can see how they transform in these enlarged states. And I have no problem. So this is an important expectation value of the transformed coordinates is completely defined by translation, which is good. So the new set of states for the observer just translated with this quantum group. In general, okay, I can see that the uncertainty enlarges with the states. I think I have 1 minute, no? And
yes.
1 minute. In 1 minute, I want to just summarize this and then say something else. Okay, I have a good example which is better said in words. The idea is that I can localize where this pen is. It's near me, and I can localize where this pen is. You cannot localize with this pen is because you are far away from me. But you can somehow localize where this pen is. You know that this pen is near my face, is near my nose. No, but you cannot localize where I am because you roughly know. Well, from my accent, you may know that I am in Naples. But somebody may better know in which part of Naples, but you cannot localize where I am. So you can localize the fact that the pen is near me, but you cannot localize exactly where the pen is because you don't know where I am. You know it with an uncertainty. Now, of course, I could give you classically the exact coordinates of where I am, and you go on Google Maps and see it, but this is classical. Quantum mechanical is not. Now, this is perfectly compatible with the relative locality of Amerino Camellia, Kowalski, Glickman, Fedele, and Smolin. They start in a different way with curved momentum space, and they don't talk in the same thing, but it's the same. This is finally the thing is the same. Okay, I have no time to discuss the other thing that I wanted to discuss, but since I mentioned it, I left the right, I suppose, to put it in the proceedings, because there is a different non-commutativity, which is Rho-Minkowski, which is an angular non-commutativity. X0, x1 is not x1, but it's x2, and something of this kind. In this case, this non-commutativity, which is called Rho-Minkowski by Amerino Camellia and collaborators, gives rise to discrete time. So now the problem is that two different observers will have different discrete times shifted to one to the other, but then there is some sort of Aharonov bomb kind of thing which makes again the system invariant. Okay, I am 1 minute off, but I finish here and I'll take some questions for the. I'll take the 5 minutes of questions. I just already see a few of them.
Yeah, thank you very much, Fedele. Indeed, let's move quickly to the questions so we don't waste time. The first question was from Nick Maromatos. Please, Nick.
Yeah, hello, Fedele. Nice talk and inspiring as always. So my question is, how much does your, so as far as I understand, you lose, I didn't understand the final point. Do you recover Poincaré invariance or you lose it? I think you lose it.
I have Kappa Poincaré invariance.
You have Kappa Poincaré.
So you can choose whether to say that I have it. No, I don't have Kappa Poincaré invariance in the usual sense.
That's
but
right.
I have Kappa Poincaré invariance.
Okay, so my two brief questions is, what do you conclude on dispersion relations for particles? Have you examined this? So in other words, are you going to have modifications like in some of the
yes. The next questionnaire may give a seminar impromptu on this. There are for both these cases, which are the one I discussed and the one I not, there are some dispersion relation differences, and these things have a rich phenomenology. which is because these effects we may amplify. So you can see, you could see, it's one of the projects which I have in mind, you could see the deformed dispersion relation as a uncertainty in the source of the, the point-like source is so you could see that. I would like to have this more formally, but already informally. Giovanni, who is here asking the next question, has been working on this for many years, and
very good.
So that's all. So the answer is yes, and not for invariance, but yes for
and if you use the string non-commutativity, which is due to an external magnetic field, for instance,
yes,
you get similar. I guess you would get similar.
Yes,
effect.
with the Drinfeld.
With the Drinfeld,
I can do the same thing with the Drinfeld. In fact, this Minkowski is a Drinfeld twist.
Okay.
You can do the same thing with twists, and I may put it in well. The proceedings have to be a fair thing of the talk, but I will take a poetic license and I will put something which
I look forward to that.
Answer to the questions.
I look forward to that.
Something.
Thank you very much. You answer fully. Thank you.
I think that the organizer will allow me to have a creative interpretation of the proceedings.
Thank you.
Okay, next question from Giovanni.
Hi, can you hear me?
Yes.
I can.
Ciao, Fedele. No, I just need a little help. I probably thought in these terms for many years without realizing it. And so I need your guidance to make me realize. When you go to the picture of this big Hilbert space,
yes,
where basically with respect to the conventional picture, it is a big step, an interesting big step, because usually our Hilbert space is, in my language, is a mathematical suitcase which contains the possible observations by one observer. Now you and collaborators introduced this bigger Hilbert space, which, if I understand, should contain together the observations by different observers, or basically also how a single event, because there is the passive side, which is particularly interesting in these cases, a single process is viewed differently by different observers, and it will manifest as different states on this space, basically.
Yes.
Now, is it enough to get this nice enrichment? Is it enough to ask still that my operators that are physical observables are self-adjoint operators on this big Hilbert space? Is that, I mean, do I have, or let me put it another way, could it change the self-adjointness issue? Basically, I have, in the picture with one observer, I identify a certain operator as self-adjoint and therefore is physical for Alice. Now I have a picture with Alice and Bob. That same operator is, am I guaranteed in some way that it's still self-adjoint? It's still, it seems like a powerful tool, but
yes, the answer is I don't know. In the sense that there is another little point which I still want to understand better. It's correlated to the fact that not every self-adjoint operator is an observable. Now, the Hilbert, not every other Hilbert set of operators is an observer. An observer, there is something extra. And the full mathematical framework is not completely clear to me. And I connect with what Nick was saying, asking about Poincaré, about the string things. Probably if there are Drinfeld twists, then in a paper with Aschieri and Patrizia Vitale, we gave a procedure to really deform, it's called twisting all the way, deforming all tensor products. So if I have a twist then I think I can do everything, because I know how to deform all tensor products, and self-adjointness will come up. Kappa-Minkowski, the twist of Kappa-Minkowski is a little bit, is more complicated. And therefore, I'm thinking of it. That's all. So that it's a long way to say I don't completely know these things. But it's a fundamental issue which we
okay. Sorry, guys.
We have a different way of seeing things. As
I think we're already quite late. Maybe we can move also further discussion this point in the discussion session.
Yes. Then I can travel to see Gianni. We'll see soon in the department. Okay.
So yeah, let's
I will be here
Fedele.
for the final discussion.
Yes, of course.
Okay.
Sure. Thank you very much, Fedele.
I finish sharing, or you stop share.
I can do also. Okay, perfect.
Okay, and I'm mute myself.
Our next speaker is Gabriele Gionti.
Yes.
Hi, Gabriele.
Hi. Okay. Okay, do you see my screen?
No. Well, I see the screen, but I don't see the slide.
Okay. Again. Okay, now?
Yeah, perfect. I can see it now.
Okay. Okay, thank you very much to the organizer for this nice conference, and also for giving me the opportunity to talk about my recent research. I have done this research from several years, and I hope I have come to an end. Essentially, what I have done is a canonical analysis of a Brans-Dicke theory, an Hamiltonian analysis, and from this analysis, I have studied this vexata question of the inequivalence or equivalence between the Einstein and Jordan frame. Why the Brans-Dicke theory? Because it's should be the theory, the low energy limit of or the effective theory of a theory of quantum gravity, in which the gravitational constant, it's not constant, but vary because of the variation of the gravitational field at Planck length. So I will show you my thesis, final thesis, that from a canonical point of view, from a Hamiltonian point of view, as regards the canonical transformation, the passage from the Einstein to Jordan frame is not a canonical transformation, although in the literature you find that many people say that it's canonical. Okay. I don't know why I cannot proceed with the slide. Okay. This is an outline of my talk. I will introduce what is the definition of Jordan and Einstein frame. I will introduce briefly the definition of a scalar tensor theory of gravity with the Gibbons-Hawking-York boundary term. And I will discuss also the Weil conformal transformation from the Jordan to Einstein frame. I will make an Hamiltonian. I will show you an Hamiltonian analysis of a Brans-Dicke theory with the Gibbons-Hawking-York boundary term. And I will arrive to this Hamiltonian transformation from Hamiltonian canonical transformation from the Jordan to the Einstein frame, and the vexata question: are these transformations canonical? We'll show that they are not canonical. There are other canonical transformations that are called anti-Newtonian or anti-gravity transformation. I will show you an example of a Friedmann-Lemaitre-Robinson-Walker finite-dimensional case, a solution of Brans-Dicke theory, and I will deal this finite-dimensional example both in the Jordan and Einstein frame. And I will also try to study, this is still a work in progress, a canonical analysis of Brans-Dicke theory in the limiting case of omega equal to the -3/2, the Jordan frame and the Einstein frame. And I will show that also in this case, in this limiting case, in this case, the Poisson bracket in the two frames are not the same. So the transformation from the Einstein to Jordan frame is not canonical. And I will withdraw conclusions. So as in a very seminal paper, quite old, from 1962, Dicke made the following observation. If I measure the proton mass, this measurement is also done in relatively to a unit of measurement for the mass. I have to define a unit of measurement for mass. So if I rescale this unit of measurement in natural units by a quantity, for example, a natural unit that is lambda to the -1, the measure of, so the new unit of measurement is lambda -1, the old unit of measurement. The new measure of the proton mass will be lambda -1, the old one. And this is an observation by Faraoni and Nadeau, but it's also in the paper of Dicke, that if I do the ratio of the new measure of the proton with new unit of measurement respect to the old one, I get a ratio that is the same. So if, for example, I have a line element, I repeat the same reasoning on the line element, and I rescale the unit of measurement length by factor lambda. So in the new unit of measurement, the line element is lambda, the old unit of measurement. This implies that since the unit of measurement is the square root of the metric coefficient with the product of two differentials, I got that the metric coefficient in the new unit of measurement rescale by factor of lambda to -2. This is essentially this rescaling implies is essentially a Weil conformal transformation. So I call the starting reference frame in which from which I depart the Jordan frame, and the other reference frame the Einstein frame. And these two frames, in these two frames, not the equation, but the observables are comparable, because I have to understand what are the dimension of the observable and scale this dimension through the length scale I showed before. Now, Dicke very nicely give the following transformation between the Jordan and Einstein frame for redefining of unit of measurement. So the mass scale, like as we have seen, like the scale factor to the -1, the proper time as the scale factor, and the line element the same, the vector potential in the same way, and the curvature of this, the potential does not get anything. The contrariant version a factor of -4. The electric charge the same. The velocity of light the same, and the h bar the same, and so, and the the delta scales the same way. Anyway, confrontation of physical observables in the two frames has to take in what is important is that in the two frame we have to take in account the dimension of the observable. So, for example, if as the observable, I will use the redshift, if I consider the redshift, and this is defined like 1 plus the length to the length to the observed divided by the length of the emission. And if in the Einstein frame I see that this quantity should be equal, for example, since it's proportional to the scale factor of the universe at the observed divided by the scale factor of the emission. This thing, since this is rescaled by a factor of omega 0 divided by omega t, this quantity in general people say that there is a problem, but this is not a problem because we have to rescale the length to respect to the unit of measurement that is a certain wavelength of the atomic transition. And this is proportional, as we have seen before, to the scale factor of the universe divided the same wavelength of the atomic transition, and and this is equal to the, as you can see, the length of the astrophysical object emitted divided by the length of the wavelength of the atomic transmission. And so the ratio is not, as we have shown before, between quantity that are the only quantity nude, so to say, not normalized, but the unit of measurement. But this quantity should be rescaled in their unit of measurement in such a way that the redshift that is adimensional, the right definition is the following one, and this definition is independent from scale redefinition of unit of measurement. Okay. After this definition, we are ready to start with if you consider scalar tensor theory, this scalar tensor theory is defined in the following way in the Jordan frame, and that is a non-minimal theory of gravity coupled with a function of the scalar field with the Gibbons-Hawking-York boundary term. And if we consider the following transformation, that is a conformal transformation between the two frames, the tensor mimic the lambda to the square lambda we have seen before, the transformation will give the following action in the Einstein frame, and that is nothing else that gravity minimally coupled to a scalar field, where the coefficient A is the following one, and the potential, definition of potential, the following one. So the idea is that if I got, this is the solution of the equation of motion in the Einstein frame, the tilde of this couple will be the solution of that are redefined through the conformal transformation are the transformation in the Einstein frame. Now, consider as a particular case of scalar tensor theory, the Brans-Dicke theory. This theory, in this theory, f of phi is nothing else than phi. And consider the 3+1 decomposition of the metric that is the following one, in which n are the lapse and n of I are the shift, and So the ADM decomposition is this quantity. Sorry, the ADM decomposition of the Lagrangian is the following one, where K are the extrinsic K of ij are the extrinsic curvature. And we define the canonical momenta in the following way. The canonical momenta associated to the lapse are the primary constraint, the shift are also the primary constraint. And we define the canonical momenta associated to the metric and to the field. And we arrive to a definition ADM Hamiltonian that takes the following form. This ADM decomposition of the density of the Hamiltonian is nothing else that the product of the lapse for the Hamiltonian constraint and the shift with the momentum constraint that are defined in the following way. Now, the total Hamiltonian, that is the Hamiltonian you have to define outside the constraint surface, has this following form. This is the not the density, but the total Hamiltonian. The Poisson bracket following, there is a mistake here, Menotti 2017, not 1997. The Poisson bracket are the following one. The preservation of the momenta associated with the lapse and the shift give respectively the Hamiltonian and the momentum constraint. And we know that the momentum constraint, the generator of the diffeomorphism on the three surfaces, on the as you can see on the metric and on the momentum associated with the metric, and the algebra of the between the momentum constraint get the usual form as in Einstein general relativity, and the same momentum constraint. Hamiltonian constraint, momentum constraint, and also the problem is the calculation of the commutator Hamiltonian constraint. This is quite elaborated, but at the end you get the same result as in Einstein general relativity. That is a combination of the momentum constraint, and in differential form get the same form. So you get the same result as in Einstein general relativity. The problem is when you pass to the Einstein frame. So if you want to implement the transformation, the Weil conformal transformation from the Einstein to the Jordan frame, you have to redefine the ADM metric in the following form, where the lapse and the shift and the tree metric gets the following coefficients. Now, if you perform this transformation, you get an action that is nothing else that in the Einstein frame, Einstein general relativity minimally coupled to a scalar field with a Gibbons-Hawking-York boundary term that is like in Einstein general relativity. Now, if you go and you redefine the momentum and associated the momentum associated to the metric, the tree metric, and to the scalar field, you get this quantity, and you get also the transformation between the momenta in the two reference from the Jordan to the Einstein frame, as you can see. And you have the Hamiltonian, ADM Hamiltonian that gets this form. So to be a bit precise, what is a canonical transformation? A canonical transformation is a transformation in which the symplectic form is preserved. This implies that the Poisson bracket compared in the two frame should have this form. So if it's canonical, this transformation should be preserved. Now, we want to check if this set of transformations is real canonical from the old variable in the Jordan frame and the new variable in the Einstein frame. Now, for simplicity, we repeat the transformation. The transformation are this one. And in general, many authors, and this is quite the point, says that the only transformation that really are important are the one on that regards the trimetric and the momentum associated to metric, the field and the moment associated to the field. This is what usually Deruel, Senodonda, and Youssef said in a paper in 2019. So the transformation on the lapse and on the shift does not count. And so in 2009, they wrote a paper in which they say that this transformation is canonical, and they performed the constraint analysis in the Jordan frame, making transformation to the Einstein frame and making the hypothesis that transformation is canonical. So they found the same algebra. Okay, the algebra is the same, but the right way of pursuing this calculation is in the Einstein frame, sorry, in the Jordan frame, because the transformation is not canonical. If you calculate this parenthesis very naively, this transformation is not canonical. It's different from zero. So the right way of doing this calculation is in the Einstein frame. And it's not true that the lapse and the shift are only gauge variable, because as Roberto Casatier pointed me out, and I showed before, in order to get that the Hamiltonian constraint is a constraint, you have to do this Poisson bracket, and the same for the momentum constraint. So it's quite delicate. So this the lapse and shift are real variable. One way of getting rid of this gauge variable is, as Dirac has done. I mean, you have to impose an extra a gauge fixing morally, and you treat the gauge fixing as a Dirac constraint, and allow that this constraint from first class pass to second class, and define Dirac bracket. This is what we have done with Alfio Bonanno and Alessia in 2018 in a mini superspace case in which the total Hamiltonian was the Hamiltonian, the lapse for the Hamiltonian constraint plus the primary constraint associated to the lapse that were first class. So you have to impose the usual thing that n, in general, what they do in cosmology, n equal 1. You see that in this way, the constraint from first class becomes second class. And this implies that lambda should be 0, and you define Dirac bracket. And this is the way you get rid in a canonical way or in a clean way of the gauge variable. Now, there exists canonical transformation for which these transformations are preserved. And these are the anti-gravity or anti-Newtonian transformation, in which you essentially allow that the trimetric and the momentum associated to the trimetric and the field and the momentum associated to the scalar field will transform, but you hold, you don't transform the lapse and the shift. And these are canonical because you don't have the same problem as before. How much time do I have?
8 minutes.
8 minutes. Okay, thank you. Now, sorry, maybe I've been too fast.
More time for question then.
More time for question. Okay. If you perform this anti-gravity or transformation, you pass from the Jordan frame to another frame that are the frame of the anti-gravity or anti-Newtonian variable, and you got an Hamiltonian that has the following form. And this Hamiltonian, it's canonical respect to the Hamiltonian in Jordan frame. So the structure of the Poisson bracket are completely preserved, and you have the same constraint and the same. So the solution of the of this Hamiltonian system can be transformed from one frame to the other. So this is the beautiness of the canonical transformation. So to stress, what are these anti-gravity on canonical transformation? Are transformation in which you map the lapse in the lapse, the shift in the shift, the trimetric, you transform the trimetric with a conformal factor. Essentially, as lambda grows, the metric relative to the anti-Newtonian transformation enhances space-time distances and emulates a large constant. So, for example, in 2 dimension, you have that the anti-gravity transformation get this form. So as lambda increase, the light cone become thinner and thinner, and this corresponds to an increase, as I said before, of the gravitational constant. Sorry. So if I have performed also a finite dimensional case. I mean, if you use a Friedmann-Lemaitre-Robertson walk and you put in this in Brans-Dicke theory, you got the following Hamiltonian. And sorry, so, I have a yes. Sorry, I had the problem with. Sorry.
Everything okay?
No, I have, yeah. Now it's okay. So if you use this transformation, it is the Friedmann-Lemaitre-Robertson walk, and you put this in the Brans-Dicke theory, you get the following Hamiltonian. So you see that momenta transforms in the following way, are defined. So you got the momenta, the primary constraint that are this quantity, the constraint associated to the scale factor of the universe. You have the momenta associated to the scalar field, that is this formula, that now the scalar field, if you assume that the universe is homogeneous and isotropic, does not depend on the position x, but only on time from the time. So you get an Hamiltonian that has the following form, and these are the non-canonical transformation that are transformation from the Jordan to the Einstein frame. And again, you have the same problem that the Poisson bracket of the lapse with the momentum associated with scalar field is not zero. And you have again this anti-gravity or anti-Newtonian transformation that are the canonical one. You get this Hamiltonian that is canonical respect to the Hamiltonian in Jordan frame, and the set of solution you get are this following one that are different respect to the transformation from the Einstein from the Jordan to the Einstein frame. Now, in the few minutes that I have, I would like to discuss another example, the Brans-Dicke case, in the case omega equal to -3/2. In this case, for consistency reasons, the potential has to be of this form. And this theory is also conformal invariant. So you get an Hamiltonian that has this form in the Jordan frame. And you have the Hamiltonian constraint that has the same form more or less as before, and Hamiltonian constraint, and you have also an extra constraint that is due to the conformal invariant, because in the diffeomorphism you have also this conformal symmetry, and this has to take in account the fact that you have this extra diffeomorphism that is the conformal invariant. And all these constraints are first class. It's quite elaborate to demonstrate that these are first class, but calculation, although quite long and tedious, could be done if If you do this calculation using smearing function, you got this quantity, and you see that there are a linear combination of constraints. And if you calculate the Hamiltonian constraint, you get the first part that is essentially the part that comes from Einstein's relativity, but you got another part that is nothing that the primary constraint that is first class, and this says that you have this extra diffeomorphism that are the conformal transformation. If you do the passage from the Einstein to the Jordan frame, you get the action as the following form. Now it's Einstein coupled to something that it remains only the potential of the scalar field that at the end is a constant. And you got the Hamiltonian that has the following form, that is a combination of the Hamiltonian constraint plus the momentum constraint that is the same as in Einstein relativity. And the analog of the constraint, the primary constraint in the Einstein frame C equal approx 0 on the constraint surface is nothing else than pi approx 0. And the constraints are the same as Einstein, the constraint of Einstein general relativity. Now, if you do the Poisson bracket in this Einstein frame, you got that the Poisson bracket are this one that are completely different from this Poisson bracket, as you see. And this shows you that the Poisson bracket, the structure of the Poisson bracket are not the same. So the transformation from the Jordan to the Einstein frame, it's not a canonical transformation because the structure of the Poisson bracket is completely not preserved, also in the case omega equals to minus 3/2. Now I will end with conclusion. We have analyzed the Hamiltonian formalism of Brans-Dicke theory in the Jordan frame and with the Gibbons-York boundary there, both in the case omega different from 3/2, the limiting case, and the case in which omega is equal to minus 3/2. We have shown that while conformal transformation in the Hamiltonian form from the Jordan to Einstein frame are not canonical in the Hamiltonian sense. Also, in the case omega equals to minus 3/2, a set of true canonical transformation has been shown. These are the anti-gravity, anti-canonical transformation, anti-Newtonian transformation, sorry. And in the case omega equal to minus 3/2, it's even more bad situation because the Poisson bracket of the constraint algebra is completely different in the two frames. Some studies have already singled out that the inequivalent of the Jordan and Einstein frame at quantum level. So this problem was already known at quantum level. Now, it seems that this problem of inequivalence emerged also already at the Hamiltonian level in the classical case. So the problem now, if the two frames, Jordan and Einstein frame, are physical equivalent, the question will be, the question that I have is the following: is there a feasible way to reduce the degree of freedom through a gauge fix in such a way to recover also an Hamiltonian equivalence at classical level? This question remains open to me. Thank you.
Thank you very much, Gabriele. So we have some time for question. Nick is the first one.
Okay.
Yes, sorry. Nice talk. What do you, in string theory, so to understand, do you claim there is an equivalence when I perform the redefinition of the metric between the Jordan frame and the Einstein frame or not? Because in string theory, as you know, they use that quite often, but do you find, I'm just trying to understand, do you find some subtleties in this redefinition? And
from a Lagrange, what I know is that from a physical point of view, as I tried to show, maybe I was quite fast. From a physical point of view, the observable should be, if you scale the observable, taking into account the dimension they have. If you scale well, the observable should be the same, should get the same result. But what is different, I expect from a mathematical point of view, they are different.
Okay, this is why I'm asking, because it's important, because as you know, in the inflation scenario, Higgs inflation, for instance, they always perform this transformation saying this is completely equivalent. So even if the observables are equivalent, you are saying that in principle, there is the theories are not the same. Am I right? That's what you are...
I'm saying that, from what I got
from
is
a Hamiltonian
point of view, the transformation are not canonical. So it's not said that you can take solution of the Hamiltonian equation in the Jordan frame and say that you transform this solution to the Einstein frame and you say these are the same solution. It's not
so
true.
This could have important implications for this equivalence for this Higgs inflation, for instance. Do you think so? Or
I think yes, would be nice to rethink and redo the same thing under the light of these results.
Absolutely, absolutely.
Because I got the impression that the problem is an issue of gauge fixing, as I try to stress.
Yes, that's what is important.
But if you do the gauge fixing as Dirac suggested to do,
with constraints, with
putting an extra constraint, defining the Dirac bracket, you are sure that you don't do any mistake. Okay. But I tried also to understand if essentially what you usually do in constraint theory, you have to work in a space that is larger than, as you know, than the constraint setting, because you don't have Poisson bracket on the constraint manifold. So in general, the condition that you have to pose in order to be on the constraint manifold usually are not good enough to really have a check or of the situation.
Thank you very much.
Okay, one quick question from Zravan.
Hi, my question is about actually when we add non-minimal coupling, the reason we add is we want to understand something, beyond the standard setup, right? We want to understand how matter couples to gravity. But from the first instance, why do we really worry about conformal transformation? We just study Jordan frame and we can do all the calculations there. And there's no need to do transformation and do the things, right?
But because the physics in the Einstein frame is simpler, because essentially from a mathematical point of view, every can be mapped in Einstein minimally coupled to a scalar field, and the quantity and the observable are easier to compute. This is the issue. This is what usually physicists are used to do.
Yes, I mean, they are easier to compute because there are existing formulas. It's easier to apply, but in general, it is easy to do the same computation in the Jordan frame as well. There we will have a really clear understanding of the original variables. And
in fact, this is still a question of debate. Many authors say the physical frame is the Jordan frame. The Einstein frame, it's not the right frame. If you want to be completely sure, you stay in the Jordan frame.
Yes,
I agree with you. But since the community have even said that the transformation and I had a discussion with Gonzalo Olmo, and he said that the community thinks that the passage from the Einstein to the Jordan frame from a Hamiltonian point of view is canonical. And there is a paper of the Deruel in which he says that the passage is canonical, but it's not true, as I've shown. I mean, could be true if you are able to do calculation on the constraint manifold and reduce to the real degree of freedom. But in physics, because of the invariance, you always will large the phase space in order to take account of the invariance, because you have to introduce extra variables always. This is the problem.
Okay, I think we can probably move next. Okay, thank you very much, Gabriele. Gabriele?
Start sharing.
Yes.
One moment. I don't find where I have the
Luca,
Zoom.
you can also stop sharing.
Yes, yes, I just done that. Okay, so our third speaker is Alessia Platania from Perimeter Institute. Hi, Alessia.
Hey, Luca. 1 second, I'm sharing my presentation. Yeah, can you see it?
Yes.
Great.
Perfect. Please, the stage is yours.
Yeah, thanks. Yeah, so hi, everyone. So let me start by thanking the organizers for organizing this nice conference and also for inviting me to contribute. So this talk will be about some works that I have done with in collaboration with Christoph Wetterich. Some already published, some are coming soon. And it is about aspects of unitarity, non-perturbative unitarity from the point of view of asymptotic safety and the functional normalization group, and about fictitious ghosts. So now the starting point is that, well, there are a number of approaches to quantum gravity. There was a proliferation of approaches to quantum gravity that essentially started from the observation within the framework of standard quantum field theory of an incompatibility between renormalizability and unitarity when quantizing gravity. Specifically, within the Einstein-Hilbert action, the theory turns out to be unitary but perturbatively non-renormalizable. And adding higher derivatives generally makes the theory renormalizable, improves the UV behavior, the ultraviolet behavior of the theory, but introduces additional degrees of freedom, and in particular, a massive spin-2 ghost. And this was the starting point for the development of a number of approaches to quantum gravity, modifying like details of the quantization procedure or details of the theory, or introducing new physics and so on. Asymptotically safe gravity is one of these approaches, in my opinion, one of the most conservatives, since it essentially relies on the framework of quantum field theory, but is based on the Wilsonian idea of renormalization, and in particular on the conjecture by Weinberg that was developed in the 70s, that eventually gravity could still make sense as a quantum field theory, and that could be renormalizable from a non-perturbative point of view. So I will just quickly review what asymptotic safety means. Asymptotic safety is nothing but a non-perturbative generalization of the notion, the well-known notion of asymptotic freedom in quantum field theory. Asymptotic freedom essentially means that all couplings of the theory in the ultraviolet regime approach the so-called Gaussian fixed point, that is the origin of the theory space, where all couplings essentially vanish. And asymptotic safety is essentially a generalization of this notion because it still corresponds to a fixed point of the renormalization group flow, but it corresponds not to a free theory, where as the Gaussian fixed point, but to an interacting theory. And this means that the values of the couplings, or at least the value of one coupling, will approach a constant, finite, but non-vanishing value. And now, the existence of such fixed point, in principle, can be checked using different methods. For instance, by looking for second order phase transition using lattice methods, like in Euclidean or causal dynamical triangulation. But in the context of in the asymptotic safety community, one very used method is the non-perturbative functional renormalization group. And if one applies this framework to study gravity, within the Einstein-Hilbert truncation, one indeed finds that there is not one but two fixed point of the renormalization group flow. The Gaussian fixed point, the free theory, corresponds to a saddle point. It is not a UV attractor. And this statement, the fact that it is a saddle point, corresponds to the fact that the theory is not is perturbatively non-renormalizable. But there is also an interacting fixed point that acts as a UV attractor. That means it provides an ultraviolet completion for the theory. And this is essentially the famous, one of the famous first plots of the renormalization group flow in the Einstein-Hilbert truncation, the horizontal axis corresponding to the dimensionless cosmological constant, and the vertical axis corresponding to the dimensionless Newton coupling. But now, of course, these are just two operators, corresponds to two operators in the action. And in general, one should verify the stability of the result within higher truncations of the extended truncations of the theory space. And in particular, this is important to identify the number of relevant directions. So the number of experiments that you have to perform in the infrared to completely fix the theory. And this turns out to be 2 or 3, also depending on how much matter one puts into the system. But now the important point is that in order to verify the existence of this fixed point, one is supposed to enlarge the theory space step by step. So starting from Einstein-Hilbert, then adding quartic operators like R-square, the Gorovsky term, and so on. In general, one should take into account all operators allowed by the symmetry. And then the question is, what about unitarity? Because there is a finite number of higher derivative operators within truncations, and many outsider, let's say, of the raised this criticism against asymptotic safety, namely, if one considers only a finite number of operators, why would I expect that the theory is unitary? But if the Wilsonian approach teaches us something, is that the non-perturbative effects could be important to understand the fundamental properties of quantum field theories, such as renormalizability and unitarity. And the concept of non-perturbative unitarity was indeed introduced in the 70s, so in the same years of the Wilsonian formulation of the renormalization group, and Weinberg conjecture of asymptotic safety is based on these papers. And the basic idea is that even though quadratic gravity has a ghost, eventually resounding quantum effects could lead to a resolution of the problem of unitarity, making, for instance, the ghost unstable. At least this was the proposal in these papers. My idea is that eventually quantum effects can even remove the ghost. But now, starting from basics, what we mean in by unitarity? Well, in the context of quantum field theory, since asymptotic safety is based on quantum field theory, the concept of unitarity essentially boils down to the unitarity condition of the S matrix. And so the S matrix can in particular be decomposed in trivial part and the transfer matrix, and a simple replacement essentially gives rise to the optical theorem. Then unitarity essentially means that the operator in the right-hand side has to be positive definite for any process. And within the context of perturbation theory, what one does is to verify this or use this equality process by process and at each order in perturbation theory. But so exactly what does this mean? This can be visualized in a really nice way by inserting an identity here between T dagger and T, and diagrammatically the optical theorem would look like this. So inserting an identity essentially means inserting a sum over all possible intermediate states. And the intermediate states are those belonging to the set of asymptotic states. And the set of asymptotic states, in turn, is a Fock space only if there are no ghosts in the set of asymptotic states. Because if there are no ghosts, namely negative norm states, then in the identity, quotation mark, because it would not be really an identity, there would be some minus sign entering here. Some minus signs would enter the right side of the optical theorem. And as a result, one would have some probabilities that can be negative or bigger than 1. This does not make sense anymore. And in this sense, one loses unitarity, physical unitarity of the theory. And so question is, we need to identify for a given theory what are the asymptotic states of the theory. And now, in the context of quantum field theory, there is a well-established way to do this. I mean, it's something that one can still find in books of quantum field theory. And it is via the propagator, essentially, the dress propagator. And in particular, one can use this nice representation for the propagator in terms of the spectral density. And this is nice because it does not, in principle, does not rely on any perturbative expansion. It is a fully non-perturbative expression for the propagator. And the spectral density here is just related to the imaginary part of the propagator. And for a stable particle, say a theory with one single degree of freedom and corresponding to the stable particle, this is just a Dirac delta, because this essentially would give via the integration the standard Feynman-like propagator. But in general, in a theory, we can have several degrees of freedom. And simply by combining this spectral representation with the Cauchy integral formula would give the most general expression for the propagator, that in general will be a sum over single poles, single degrees of freedom propagators, plus a continuum part related to unstable particles. So in general, there would be real poles that correspond to stable particles, and so are just residues, and M are the corresponding masses. There might be complex conjugate poles and unstable particles, as I said. And now what enters really the optical theorem, what defines the spectral density, is just stable particles. essentially if one takes the imaginary part of the propagator to compute the spectral density, the complex conjugate poles, since also the residues by construction are complex conjugate, they would just give a zero contribution to the spectral density. While real poles obviously contribute to the spectral density and contribute with deltas that are weighted by these residues. And in order for the theory to make sense, in order for the theory to be unitary, these residues should be positive or eventually zero. So in other words, in the theory, there should not be stable ghosts. But in order to establish what are the 2 degrees of freedom of the theory, in particular the stable ones, one should take into account quantum effects. And the reason is simple. So even for a theory where the Bayes propagator has one single pole, resumming quantum effect would generally give rise to a correction to the inverse propagator in terms of self-energy. And in particular, the self-energy can have an imaginary part. When the interaction that one takes into account for this theory by summing quantum effects give rise to an imaginary part, then this interaction is responsible for the instability of this particle. And this is something that one can only see by looking at dressed quantities, essentially. So still, in principle, one can use Bayes quantities and try to prove unitarity order by order in perturbation theory. But there are some things that could lead to, in some specific case, to miscounting of degrees of freedom. For instance, if one use truncations, approximations, as we will see, or unstable particles essentially cannot be described just using looking at perturbative expansions order by order. One needs to resum that expansions. Using dressed quantities, instead, the idea would be to resum quantum fluctuations first, all quantum fluctuations, and then try to infer something about unitarity, causality, and so on. And this essentially boils down to computing the effective action for the theory, to correctly identify what are the degrees of freedom of the theory. And now, how do we compute the effective action? In principle, there are several methods. One of them would be, if one is able to, just to by resumming the functional integral. Equivalently, one can use the functional normalization group equations. This equation for the for a scale-dependent version of the effective action. So this is essentially an exact equation that has been developed by Wetterich for scalar fields and then by Rother for gravity in the 90s. And yeah, it is an exact equation. You don't need to understand for this talk the details of the equation, but just let me tell you how this works. So essentially, this equation generates a flow for this scale-dependent effective action. And in the limit where k is infinity, what one would get is the Bayes action of the theory, hopefully a local action. And instead, in the opposite limit, one would get the ordinary effective action of quantum field theory. And at any intermediate scale, what one gets is, if you want, a partially quantized theory that is obtained by integrating out fluctuating modes with a frequency that are bigger than k. So from the UV, from the ultraviolet to k. And in this action, what one would have what one should consider are all terms that are compatible with the symmetry and the field content of the theory. And even if you start with a smaller ansatz, in principle, you would generate all of these terms. And in the limit where k goes to 0, as I said, one would recover the ordinary effective action. And as a result of the integration of quantum fluctuations at all scales, one would get some non-localities at the level of the effective action. But this non-locality is induced really by quantum fluctuation, while the fundamental theory hopefully is local. And since this action incorporates all quantum effects, essentially all amplitudes that one computes from the effective action at 3 level contains already all quantum effects. So this is the object that one should use to check unitarity. And now let me make a digression. So what I say is that the effective action really comes from integrating out all quantum fluctuations. So can be used to investigate the fundamental properties of the theory like causality, unitarity, stability. But there is more. This could be used to do some phenomenology, and in particular to study the deep quantum gravity regime, or for other theories, the deep high energy regime. While at low energies, effective field theory, of course, is enough for to describe physics. And the basic idea is that even if quadratic gravity has a ghost, if one integrates out all quantum fluctuations, eventually unitarity can be restored. And this was the idea put out in these papers. And there is already some indication. I mean, even in the one loop approximation of the effective action, that is still one loop, it is not the full effective action. One loop effects are enough to make the ghost unstable. That, in my opinion, is just a partial solution, but we are talking about the one loop approximation, not the full effective action. The full effective action would be non-local. Maybe it will not be only logarithmic interactions, but there could be more, and in particular could be free of ghost instability and compatible with unitarity. This is how, in theory, conceptually this would work. But as I said, there is the small issue that, in principle, one to really realize this equation exactly should take into account all terms that are compatible with the symmetry of the theory. And in practical computations, however, one needs to consider only a finite number of operators. It can be a large number, but it is a finite number of these operators. And if one just takes into account a few, say, expand the effective action in a derivative expansion, and then cut this derivative expansion to only a few operators, naturally there will be a finite number of higher derivatives, and those a finite number of poles. Some of them will be ghosts. And the question is whether one should really consider these poles as dangerous. It is clear that not all of them will be ghosts. Some will be just spurious degrees of freedom. And in particular, quantum effects, resounding quantum effect could remove some of them. And the question that I want to ask is, what is the decoupling mechanism of these spurious degrees of freedom? And to study this question, it is not really necessary to go to the case of quantum gravity, that is difficult itself, but one can use a toy model. And as a good toy model to study this problem, I will just use quantum electrodynamics in the one loop approximation, or Leibniz quantum electrodynamics, because these are theory that we definitely control better, and try to understand what happens in these cases. And as a toy model for the full effective action, I will just take the one loop effective action, that is whose quadratic part is essentially an f square that brackets a form factor p that has a logarithmic interaction in there. You can find it in this paper. And now the key point is that we know that this theory is unitary. Both quantum electrodynamics and the Liebig quantum electrodynamics are unitary. Of course, in QED there is a Landau pole, but in the regime of validity it works well. So the question is, what happens if I now take this action with the logarithmic interaction as a toy model for my effective action, and I introduce an artificial derivative expansion of this form factor, and I truncate it to a finite truncation order. And this is exactly what I'm doing here. Just a bit of notation. I'm denoting by Z the ratio of the momentum square over the threshold mass square that essentially appears here inside the logarithm. I'm setting this alpha equal to 1 because it's not really, its value is not really important. And now the dress propagator coming from this truncated version of the P function that comes from a derivative expansion of the logarithmic interaction, and then by truncating the derivative expansion to a finite truncation order. Well, this will give rise to a propagator that has whose scalar part has this form. But now this, of course, has a finite number of derivatives, a finite number of momenta here, and therefore there will be, or one would expect to have a bunch of poles. And this is exactly what I'm plotting here. This is the real part of the pole for Q square over M square as a function of the truncation order, essentially this N. And there will be a bunch of complex conjugate poles that are these red dots, and also real poles. In particular, for small truncations, there is a pole here at positive momenta square, and this essentially disappears after a few orders. But there is also another pole that essentially is not only a ghost, but it is even a tachyon. It essentially tends to converge to this minus M threshold square, and it is persistent, is there for essentially any truncation order that I have explored.
Alessia, 4 minutes. 4 minutes.
Okay, so essentially, one would see this pole that we know that is spurious because is not present in the full theory. And the reason why it is generated within truncations is due to the convergence properties of the P functions. Essentially, it is due to this alternance of positive and negative divergences of the P function for finite truncations. And the pole is generated anytime there is a negative divergence. So this generates a sequence of zeros for this P function. And now the question is, how do we really understand within truncations whether a pole that one sees is a 2 degrees of freedom of the theory, or just a fictitious pole, a fake ghost. And this is something that one can see by studying the residue of the propagator at the corresponding pole. And in particular, what one sees for these spurious degrees of freedom is that the residue of the propagator evaluated at this pole is negative, but increasing the truncation order, it essentially decouples from the theory because the residue vanishes when a sufficiently high number of operators is taken into account. And one can play the same game by flipping the sign of this P function, because this introduces essentially a true ghost in the theory. And one can see essentially that for a true ghost, the residue, the behavior of the residue order by order is like this. So it is negative and quickly converges to a negative, a finite negative value. While for the fake ghost, the spurious degrees of freedom that are seen within truncated derivative expansions of the effective action, the residues quickly goes to zero. In upcoming works, we will also show that the same applies for the case of entire functions. And there is also a general proof that I'm working on, and seems like this thing really works for quite a lot of cases. And so I think I'm running out of time, so I go to my conclusions. And so what I discussed is just unitarity and the non-perturbative unitarity from the point of view of the functional prenormalization group. And so what is really important to determine unitarity is not only resumming all quantum fluctuations, as was already known in the literature, but it is also important, and not only important, but crucial to take into account all operators that are allowed by the symmetry of the theory. And clearly within truncations of the derivative expansion of an effective action, there will be fictitious poles, fictitious degrees of freedom. And in particular, this could be the case for stellar gravity. That ghost could be a fictitious degree of freedom due to the fact that we are not taking into account all operators allowed by symmetry, by diffeomorphism invariant. And in principle, a way to see this would be that of tracking the value of the residue as function of the truncation order of the derivative expansion. And so what one should really try to do is to determine these properties using the effective action, and using approximated version or truncation of the effective actions would just lead to unreliable results. So with this, I thank you for your attention.
Thank you very much, Alessia. So we have some time for questions. Yeah, there is. Srama, please, you can speak now.
Hi, Alessia. Well, my question is about, because you are mentioning non-perturbative unitarity, which means you basically want to count degrees of freedom without doing perturbation around some background, right? And my question is specifically how, because you have this all the cover of non-local terms in the context of gravity, how do you count degrees of freedom? How do you know how many degrees of freedom are non-perturbatively?
So the point is, one should, a good way to do that would be to compute the effective action, like the full one. And this in general will be non-local. It can result, for instance, in an entire function. It can result in something like the logarithmic interactions, like it happens at one loop already. And then compute the full propagator. And from there, you can infer what are the degrees of freedom of the theory. And so the problem with using perturbative expansion is that as soon as you do not resum that, you could also see some degrees of freedom that in the end are unstable. So this is explained in some of the papers by Donoghue. So this would be one problem. And second, it is really important to consider the flow of all couplings, all form factors down to the infrared, because if you take a truncated version of the effective action, so with a finite number of derivatives, you would obviously see some degrees of freedom, and they might not be in the theory. So you would see something that is not describing physics, is describing, I mean, is the result of the bad approximation that we have. And for this reason, one cannot really check unitarity within truncation, or you can do that, but I'm not sure how much you can infer. You can say I see this in this particular approximation. That could mean nothing in particular.
Do you understand correctly? What you call non-perturbative counting degrees of freedom means you're adding all the loop effects, and then you're trying to achieve a final action. Then you do in the standard way, try to see the propagator, just doing like perturbation around Minkowski, and then you see the propagator for the effective theory. Is what you mean?
Yes. So essentially, the one loop is just one part of the effective action. So you can use, in principle, the perturbation theory, but you need to resum it.
Can I ask another question if there is time?
Okay, quickly, yeah.
Okay, so see, okay, well, there can be ghosts in effective theory. That's okay. That's what you are saying. But suppose if we apply this, if I apply this effective theory, because I mean, for low energy physics, for example, inflation. Okay, well, it's not Planck scale physics. It's still few orders of magnitude lower than Planck scale. But these ghosts will definitely cause instabilities. Either during inflation or at the end of inflation, which is well known and well studied in the literature. So, how do you solve this problem in your approach as in predictive safety program?
So you can look at the paper by Stelle and Jean-Luc Lerers, A Safe Beginning for the Universe. So in that paper, they essentially take R-square gravity. And notice that if you take into account the running also of the Ricci square term, you will see that essentially the corresponding running of the ghost mass is such that you would hit the ghost instability, you would hit the ghost pole at scales that are essentially trans-Planckian, not Planckian, but quite a lot of order of magnitudes above the Planck scale. And at the scale where you hit the instability, you definitely need to have more, to have the effective action, or at least better approximations for the effective action. But at low energies where the instability essentially is not realized, you can still use the R-square gravity as to do some physics, of course. And also, then stellar gravity is perfectly nice effective theory, right? Why to go for a more complicated setup? I mean, in this view, from the paper of Stella and Lerner, I mean, they show it, right? Safe beginning, okay. Low energy effective, stellar gravity is okay to work, and it still works. R plus R square is nice interpolation. So why to add more and more terms and complicate? Again, try to find some effective theory at low energy. So I'm not sure I got the question also, because at least to me your audio is not great.
Your audio is bad. It's very bad, Sravan.
Okay.
Hear me now?
Yes, much better.
Yeah, my question is like, okay, stellar gravity is a nice effective theory, right? So then why to add in this effective theory more terms, like more higher derivative terms? This is my question. So
well, because so the starting point is that you would like to have a theory of quantum gravity, okay, a theory of gravity that can be quantized and is consistent with the requirements of quantum field theory that we know, so renormalizability, UV completion together with that, unitarity, possibly causality, or at least, I mean, not breaking causality on large scales, and so on. So the point in asymptotic safety ideally would be to find understand whether quantization of gravity within the framework of a quantum field theory admits a renormalization group trajectory that connects the low energy theory that we know, so Einstein gravity essentially, plus R square if you want, a classical theory, to a fixed point. The fixed point is your V completion, okay? Then within this framework, theoretically, if you have infinite computational power, you can derive this effective action. And what you will see, of course, is that there is a classical part. Well, in the one loop case, you would have one loop corrections, but in the general case, you would have all possible corrections. And the corrections would come with the H bar, of course, but would also be Planck mass suppressed, such that essentially at low energies, it is completely fine to describe, you have essentially the classical theory, but the higher is the energy that you have, the more important is the contribution of quantum corrections to the classical action.
Okay.
So, of course, you can use R square to describe something like inflation, if you want to.
Okay. Thanks.
But, yeah.
Thank you very much, Alessia. So, the last speaker will be, I think, will come in a couple of minutes. So that's why I didn't stop this nice discussion between Alessia and Shravan. But yeah, I think we should just wait this couple of minutes for the last speaker. Unfortunately, he was blocked in the traffic in Moscow. So let's see. Sorry for this situation. I think I'm just sending a message. Yep. Yep.
Well, discussion can be continued as well, right?
With Alessia? Yeah, of course.
Yeah. No, I have one last question still to ask. Okay, there is on one hand you are talking about a fixed point, which is UV completion. Then you are hunting for effective theory, right? Which is away from the fixed point, UV complete fixed point. Am I correct?
Not effective field theory, but effective action. So okay. Of course, so you can attack the problem from in two different ways. So within the framework of effective field theory, essentially you try to construct an action as an expansion of momenta square over some cutoff square. You don't care if the theory is UV complete. You just have a cutoff that can be, for instance, the Planck mass in the case of gravity. And in particular, you don't really, you are not predicting anything. While in the top bottom approach, and by this I mean that if you try to really compute the renormalization group flow and the full effective action from the UV completion of your theory, what happens is that you have an enhanced predictive power, because the fixed point will have, hopefully, I mean, if the theory is renormalizable in the Wilsonian sense, you will have a finite number of relevant directions. And this means that at the level of the effective actions, yes, you will have infinitely many terms, but these terms are parameterized by 2 or 3 parameters that correspond to the relevant directions of your fixed point. So if you have 3 relevant directions, then the effective action will have infinitely many terms, but not all of them are independent. They all depend on 3 parameters, if 3 is the number of relevant directions associated with your fixed point.
Physically, what these directions mean when you say directions with the fixed point?
So essentially, so they are, if you look at the normalization group flow, there will be some, if you look, at the entire theory space and this fixed point, so there will be some directions with respect to which the flow is attracted towards the fixed point. Along other directions, it is a repulsor. So essentially, also if you don't get the right initial conditions, it could be that you don't get this ultraviolet completion. So in order for your theory to be consistent, the RG trajectory, renormalization group trajectory that is realized by nature, has to lie on this critical surface of directions such that all trajectories in this surface are attracted towards the fixed point. And of course, this is not enough because you want, so the number of relevant parameters in the infrared have to match what you observe. So say if the Newton coupling cosmological constant are relevant directions, the initial condition for my flow will be the input that the cosmological constant is 10 to minus 120 Planck masses and so on. And you have to see if there exists a renormalization group trajectory which connect these inputs, experimental inputs in the infrared with the UV completion. It is not even obvious that this happens in general. It can be that you have an ultraviolet attractor, but your initial conditions are such that the corresponding renormalization group trajectory is not UV complete. So it is important to study not only the fixed point structure, but also the number of relevant directions, and check if there is such a renormalization group trajectory that connects what you observe with an ultraviolet, a well-defined ultraviolet completion.
Okay, thanks. So with these finite directions, you can completely fix the infinite parameters in these form factors, right?
All of them, yes.
Okay. Thanks.
Yeah.
Alexey has come.
Yeah, oh, I think I can see Alex. Luca, please make Alex Cost. Hello.
Done.
Okay, we have our last speaker, who is Alex.
Hey, Luca.
Hey, Alex. Hope you're doing well.
Hello?
Hey, can you see me? Can you hear us? Alex? Alex?
Luca?
Yes. Can you hear me? Yes, now yes. Please share your screen. Alex? He disappeared from the participant.
We lost him.
Yeah. Luca. Alex?
Yes, I'm here. I'm here.
Okay, now I can hear you very well.
Yes, it was some problem. There was no sound, apart from all the rest.
You can share. I think you're cool.
Yes, 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 I will. So, do you see my screen?
Yes, if you can make it full screen.
Yes, yes, just a second.
Alex, since we are a bit tight with time, we try to do it in 25 minutes. Is okay for you?
Yeah, I will try.
And then we can do questions in the discussion. Okay.
Yes.
So, okay, thanks. Please, you can start.
Okay, thank you very much. And thanks for waiting due to this crazy Moscow traffic, which I encountered today. Here is a title, which I want to try to explain you in the next 25 minutes, as you tell me. And the title is about physical propagator in analytic infinite derivative gravity. So first I will explain why at all infinite derivative gravity and why I think it is good to have. And then I will explain why I'm so curious about derivation of propagator, given that some time ago, me and my collaborators reported this looks like already, but I want to say that something is going to be rectified, let's put it like this, or better to say something new appears on the way. And I think mainly it is because we are playing with analytic infinite derivative gravity, which means practically speaking, quite tough subject, because infinite derivatives, they make life harder. Yeah, and this is mainly based on works with Sravan Kumar, Alexey Koshelev, and Anna Tokareva, as well as some work in progress. And of course, many other people were contributing to this, because generically topic is, in my opinion, quite popular. And in order to avoid some introduction, just because I believe all of you know why is gravity, why we should quantize it, what are the big problems. Let's put things like this. Apart from GR, which is encoded in the first term of this section, and probably lambda, I would like to propose you this particular action. So, I mean, the second line is the crux of the model. And I think it is nice action to study. And let me try to explain you why. First of all, before I will go and explain exactly why, let me say what is here. Things are simple here, but still, it is d-dimensional stuff, but most likely we will target d equal 4. R is curvature, L mu is kind of Ricci tensor, and W is Weyl tensor. So L mu is not exactly Ricci tensor, but something of second rank composed of Ricci and Ricci scalar. But it's not Einstein tensor either, because it has here 1 over d and not 1 over 2. So this action, why do I like this action? And why do I think it's worth to study? I will explain a little bit later why I need exactly infinite number of derivatives, but for the time being, I want to say that this is the most generic thing. It's the most generic action to study linear perturbations around maximally symmetric spacetimes. And moreover, if we employ Bianchi identity, we can show that in principle, we can put FL equals 0 without loss of generality, or constant if we have d greater than 4. So let me explain you a little bit what does it mean most general and in which situation. This is the situation. It was a couple of papers actually mentioned here. There's a couple of papers in which me and my collaborators, we have shown that given such a generic action, which contains a lot of things, we can single out a piece of it, which is responsible for linear perturbations around a maximally symmetric background in this theory. So exactly, I mean the following. Exactly, I mean that given this action, which contains some P and Q depending on curvature and O depending on covariant derivatives, and given all of this depends analytically on respective arguments, we can deduce that this is the most essential piece. Actually, not really most essential, how to say it better. It is all what we need to study as long as we worry about linear perturbations around maximally symmetric spacetime. So technically, this derivation is not difficult. It's just a little bit cumbersome, but there is no conceptual problem here. You just exclude term by term, whatever, what cannot contribute to linear perturbations, and then you make other terms looking similar, move left and right, derivatives, contract here and there, indices, and eventually you end up with what has been shown on the previous slide. So you see, the idea is that this generic monster action without any meaning only has this part crucial for maximally symmetric spacetimes, which are essentially Minkowski and de Sitter and anti-de Sitter spaces. But these are important spacetimes because they describe important parts of evolution of the universe, and moreover, practically only around these backgrounds we can sensibly define what does it mean a particle, and further what does it mean quantization. So in principle, this is a primary thing which we have to study. And this is what we can get. This, for example, spin 2 propagator, spin 2 part around maximally symmetric spacetime. This is a quadratic spin 2 part of the action. H mu is kind of graviton, not exactly yet graviton, and I will speak a bit about this later. It still has more components than physical graviton because we employ here true Poincare symmetry and not something less. And as such, this spin 2 in the sense of 4-dimensional theory, 4-dimensional group symmetry. But whatever it is, you see the propagator, how it's constructed. It's a box multiplied by P of box. And this P of box is what we try to get for a long time. And quite a while ago, we have obtained it. You see, this is not actually the final answer because it is, as I say, just around maximally symmetric spacetime, and it is not yet physical two-component H mu. We have to impose more conditions, take gauge into account, and this is what I'm going to continue. But even this is already quite tough to get. This in principle is enough to study dynamics of perturbations in, for example, de Sitter or Minkowski. And you see, we here clearly notice few terms like unity, it's how it would be in GR. This green constant term, how R bar is a background curvature. So if we speak about maximally symmetric spacetime, it's a constant. So green constant, how it would appear in local R² gravity. And this term, how it would happen in our case. And this red term is exactly the very new this red factor is a very new component. Would it be 0 FW, it would disappear at all. Would it be just local while square term here, just while contracted altogether, all indices? This is not 0, it's 1. And this results in this particular propagator. And this is exactly what, for example, observed Stelle in 1977, when he suggested that R² gravity is renormalized. So first of all, this demonstrates that we can compute something. Second, it demonstrates that we can really track all the previous results. And moreover, if we look carefully, we see that we always gain, apart from one pole, the physical pole for a graviton, we gain another one as long as, for example, Fw equal 1. And this should be a ghost, and this we pretty much know starting from Ostergradsky statement, and no question we will gain problems. This is what exactly observed by Stelle. Renormalizable, but not unitary series. Spin 0 around maximally symmetric spacetime. Let's say no, not so clear notion, but still looks like this. And normally it's a gauge degree of freedom in GR, which at most can represent the Newtonian potential. But here we gain this factor, S of box. Again, the structure is very simple, like unit for GR, green constant, which would appear, would it be R squared, and the rest, which appears here, and would it be R squared local gravity, FR equal just 1. You see? Here we gain a second pole if FR equal 1 or equal constant. But it's not a problem here because initially this phi, if you compute it in just GR, is nothing but a gauge degree of freedom, and moreover it's a ghost, by the way. But we don't care about this ghost because it can be gauged away. But the second pole will not be something possible to gauge away. This will be exactly the scalar degree of freedom of f of r gravity. And here we are very good to go. We understand what's going on. And now we understand that as long as FR is present, we can gain something. If FR equal constant, we gain just a pole, and it's okay. And if FR of box is not a constant, we gain something which we don't know exactly what. But in spin 2, it was a problem. Whatever Fw of box is, it will be not something nice. Yeah. So, what is the resolution out of there? We're gonna to study to see later that since it's not all the story, we will see how to first of all improve it and second defeat it and defeat the ghosts which appear. But first, let me explain that here, since we already now have demonstrated that we can compute something, and that in particular that we can compute second variation of the action, let me say that in principle, this quadratic in curvature action, analytic infinite derivative action, abbreviated as AID, it in principle can incorporate much more than just maximally symmetric space-time. In principle, it's very rich, and it has a lot of nice background solutions, which in principle can be studied and analyzed, etc., etc. And here is just an example that any solution which corresponds to such a substitution box R equal R1R, where R1 is a constant, it will be a solution to this action as long as it is conformally flat. You see, it looks like it may be not everything. It's hard to analyze all the possible space of solutions, but in particular, Starobinsky solution, Starobinsky inflationary solution, is exactly of this form. So we don't have to know it exactly, but we can prove by direct substitution that if this condition holds, then it will be a solution to equations of motion. So you see, at least we can have Starobinsky inflation as an exact solution here. Then we can construct some other solutions, like, for example, ghost-free bounds or something else interesting. Here there is a proposal which comes out that maybe this put on the very first slide the quadratic and curvature analytic infinite derivative action is already enough to approach quantization of gravity. It's true that on the second slide, I have shown something totally untractable and something fully misunderstandable, because there is no way to understand what is it as long as you don't specify all the components. But the idea is the following: why not to just test whether these two lines is already something good enough, at least to approach quantization of gravity, which is a big deal. And why I'm saying quantization immediately, because this is what was formulated by Stella. He said clearly, take R squared gravity and you get gravity renormalizable. But he got a ghost. So you see, some idea behind is to improve Stella a little bit and to make it without a ghost. To make it without a ghost, we have to somehow understand the structure of these operators. And let's see how we can understand it. But first of all, let us say the following. Since we now can be courageous to consider something like richer than just maximally symmetric spacetime, let's go for example, FRW. And let's try to get propagator in FRW. It may be a complicated mess really to do it, but what we can try to do, we can start with the following fact, that we will, first of all, figure out what are the physical degrees of freedom. And in order to do this, let's try to forget for a moment that we live in a maximally symmetric spacetime and try to treat it as FRW. Practically nothing forbids, okay? You can easily apply ADM decomposition to just Minkowski space, no question. You don't have to because you have 4-dimensional symmetry, but you can. And this is what we do. So technically taking Minkowski space, I treat it as FRW in a sense that I apply ADM decomposition. And this is a test bed for my derivation. And I obtain propagator for a scalar. Scalar how it would be in Bardeen parameterization, in Bardeen potentials. And I obtain the operator, which is in a quadratic form for scalars of this, not so easy at the moment form. Yeah. And the same I do for Hij, which will be tensor in 1+3 decomposition, which will be exactly physical spin 2 tensor with respect to 3-dimensional symmetry group. And this is an operator like it looks like for tensor field, for graviton, for physical gravity. And our demand, as usual, in any theory, and in particular in this crazy model, is that we want no ghosts. No ghosts in a very simple translation. If we don't go to some complicated models, like, for example, Horndeski models, whatever, it is just avoid more than 1 0 with respect to the Lambertian in this operator. This will correspond to no more than 1 pole in the propagator. And we will count poles. As many poles, as many degrees of freedom. If there is more than 1 degree of freedom, it's bad. If there is 1 degree of freedom, it's good. If there is no degree of freedom, okay, well, this may happen, but this is literally strange. At least for graviton, we want at least 1 degree of freedom. And I think that it's obvious that we have already box factored out of these parentheses. So for the tensor sector, what we will want to see whether we can make this don't give a pole. But then we have to tackle this. You see, as long as we switch to 1+3 decomposition, we immediately gained mixing of F of box and FW of box in the kinetic operator for a scalar with respect to 3-dimensional symmetry group. So we have to understand what's going on. You see, it's not an easy structure anymore. So let me just spend a couple of minutes to explain what exactly I want, meaning I don't want a poles. This is what I want. I somehow generalize kinetic term of some field to some function of box. What I don't want more than one pole. So this structure written here is bad, because one of them will give a normal field, another will give a ghost. No luck. The same will happen if I will add here many factors of box. As many factors I add, half of them will be good, half of them will be ghosts. But if I change in this way, saying that sigma is some entire function, things have become much better. Because if a sigma is entire function, exponent of sigma doesn't have 0. And being inverted, it doesn't have a pole. Good. This is what I want. And this practically unique way to construct a function such that being inverted, it doesn't have a pole. It must be exponent of entire function. So this structure, which is here, is which I like. Which means, as long as I speak about physical degrees of freedom, I want this operator to be at most like this, because you remember we agreed that one scalar is okay. But for tensors, I cannot allow any extra pole here. Oh, sorry, there is a misprint. It should be no box here. It should be no this box here. It should be just this parenthesis. So this parenthesis, in particular without this box, which is by mistake here, should be just exponent of 2 sigma. And sigma should be entire function. And sigma 0 should be entire function. So it means that Fw can be expressed clearly like that. Very simple. But then I have to substitute this Fw inside of this whole large expression. My credits here go to Anna Tokarev, who helped me in understanding all of that. And the point is that you, in principle, gain a miracle. You can indeed make things happen such that this form, exponent of entire function multiplied by box minus mu squared, appears. But in order to gain this, and in order to avoid some strange poles in the denominator, you obtain a miraculous condition that these two functions must be related in a very simple way. One is proportional to another. As simple as that. They're practically they're the same, with some coefficient in front of one of them, which is practically logarithm of 3. Being said this, we find out that Fw is quite simple, and f of box is nothing but some expression through Fw. What happened here is a very important fact, which I want to concentrate last few minutes. You see, we started.
You have 3 minutes, Alex.
Yes, I know, and it's almost the last slide, so I know, I count them, thanks. So you see, we started with kind of very monster action, but I don't eager to consider it. I like to stay with this, you see, quadratic in curvature, but still a lot of functions here. Somehow I convinced myself that at least around good spacetimes FL of box can be eliminated by Bianchi identities. Okay, but still a lot of freedom. Then you see, we have obtained conditions using maximally symmetric spacetime and maximal symmetry. This condition said that something should be said about Fw and something should be said about Fr, which is good. Still a lot of freedom, but you see now, thinking more and understanding that physical degrees of freedom usually described by 1+3 decomposition, because this is how you single out and gauge out everything unneeded and live with only what is propagating really in your real world, you see that in practice these functions must be connected, which in turn means that we are having a clear connection in between of these possible entire functions which enter our definitions. I mean, it is not yet all, of course. We still live with the entire function, but what I want to propagate here is that the previous result, which was obtained in the maximally symmetric setting, definitely becomes much more rectified and much more constrained as long as we go to 1+3 decomposition, even if we apply it around the maximally symmetric, even if we apply it around Minkowski. In principle, it would be possible to do the same and apply it around de Sitter or anti-de Sitter. And what is, let's say, almost done, but really not ready to be announced, that it can be done for a generic situation as long as we have this particular relation box R equal R1R. It can be done. It's cumbersome, no question. But the actual outcome is the same. We are able to constrain the system by effectively eliminating one of these functions and expressing them through one and the same entire function. So let me conclude here. I tried as much as I could to convince you that starting with some class of analytic infinite derivative theories, we can try to target UV completion and quantization, because this class of actions generalize and improves proposal of stellar to the moment maybe the only proposal which provides you some, let's say, from beginning to end example of renormalizable graphs. It was an issue, a ghost, and we eliminated the ghost. Price for this is infinite number of derivatives. But on the other hand, we see a lot of nice properties for this action, and we even can contemplate about connection to string field theory, because it looks like a clear connection given how all these infinite derivative operators look like. But the main topic of this talk was to show that in principle, there is more to study, much more to study. And in particular, I have shown that computation using 1+3 decomposition is something very important to finish here in full for, let's say, at least for FRW universe, because already at the level of Minkowski, we see how a system becomes more constrained. And this is something very important, because given a relation between scalar and tensor sector in the action, it may have deep consequences with respect to many questions, which we can ask about inflation, about bounds, and about other things where scalar modes entangle with tensor modes due gravity waves and stuff like this. So let me stop here, and thank you for your attention.
Okay, thank you very much, Alex. So as I said before, we will straight away start our discussion session for this session. But I can see there is a question from Leslav. So, but I would say that the discussion session starts now. We can have at least 30-35 minutes of discussion with all the speakers. Okay. So let's start with the question from Leslav to Alex, and then we move to other questions. So Leslav, you can speak now. I am muted. I'm muted you.
Okay. Hello. Thank you, Alex, for your nice talk. Yeah, let me first make a comment. Yes, it's nice. You could also put, I mean, reference to papers that we wrote together with Alexey and also with Stravan. But let me ask the question, maybe it's more important. You nicely put the two sectors, spin 0 and 2. And of course, I agree with your computation, but ask about the following. What is your opinion on the following thing, that in the spin 0 sector, the so really the inverse is dependent on the gauge fixing? How you can deal with that?
You see, the point is that I claim that spin 0, at least being considered as spin 0 with respect to 4-dimensional symmetry group, it is indeed gauge dependent. And this is why I wanted to go away from this. 1+3 decomposition, where you get this operator, is free of this, because phi becomes a gauge invariant Bardeen potential. You have no gauge freedom here. As such, it is totally fine to study it here. And this is what I mentioned briefly, that this formalism, even though it should be totally equivalent if we apply it around Minkowski, and it should give totally the same results, it, let's say, much more convenient to study whatever really propagates and how it behaves. So I would say I would incline working further using this formalism, which allows me to see a really physical degree of freedom, which will be gauge independent.
So if I can maybe try to understand, so you mean that, because as I said, I agree with your expression on the level of second variation. And when I agree that, for example, this was the previous slide, when you write this transverse mu nu, this is exactly the thing that, and the functions there exactly are like you computed, that's everything correct. But just the problem, as I understand in literature, was if you really try to, maybe on FRW you don't do this, but if you try to go to the propagator, then you really see that it is not anymore invariant. In a sense, it depends on the gauge fixing. So
exactly.
in principle, you know, I like very much your construction and the calculate the form factor in spin 0 with form factor in the spin 2 sector, especially due to this FRW thing. But yeah, one can also keep, I mean, maybe it's a kind of twist here that on flat space-time, at least we see this problem that we've already discussed in 90s. We are not very recent in discussing, but already there they say that actually the mass of the spin 0 ghost, if it is there, is not a problem, because, you know, it's fixing independent, this sector. So the only real problem was really the spin 2 massive ghosts, typically, like in stellar gravity. This was the real problem. But if there was anything in spin 0 wrong happening, this is not a big issue.
Yes, this I totally agree. And no, you see, it's very, how to say this, it's tantalizing really to make use of 4-dimensional symmetry as long as you have it. Yeah, it looks like way better. And indeed, there were many papers from 1990s and 80s even, where people tried to write propagator using 4-dimensional formalism and then trying hard to eliminate the gauge. Even here, you see, even for spin 2, in a 4-dimensional sense, H mu nu being transverse and traceless, it contains 5 components. It's not what exactly is propagating. You have to really,
it's not 2, yes.
You see, it's even H mu nu, it's not exactly graviton. We are a little bit lucky because when you do 1+3 decomposition, even though you don't need in Minkowski, and when you consider Hij, this 3×3 matrix, let's say, it is exactly embedded in this H mu nu, so it is part of it. So whatever propagator here immediately is inherited in further derivation, so you don't need to bother too much deriving it. But this, you know, it's in a sense analogous to electrodynamics. When you impose like Feynman gauge, you still have to work a little bit, which is d mu a mu equals 0. When you impose Landau gauge,
residual, yes,
like di ai equals 0, you are kind of all done, all set. It's almost the same analogy. I don't say that 4-dimensional formalism is wrong, of course. No, it's correct. But you have to think much more, as you say, in order to eliminate gauge freedom, to fix here and there, derive some gauge-dependent quantities, understand them. And on top of this will be absolutely useless and unneeded and even wrong if you apply it to anything apart from Minkowski or de Sitter, because there is no maximal symmetry. As long as you step out of de Sitter, you must go to 1+3 decomposition, because, I mean, you have to follow your symmetry. Yeah, I mean, otherwise, what's the reason to make? I mean, you cannot use what you don't have. So this is what I wanted to explore, and I was really surprised that this way, picture becomes much more, let's say, much more intuitive, in my opinion. And of course, I think it's a very good result that we can constrain these form factors more, because it's always a problem. They're unconstrained, but here it looks like there is one more step forward. not yet done, of course. I mean, not yet final. A lot of work on the way, but this is what I wanted to propagate to you. That looks like a more intuitive picture here.
Nice. So
Okay,
yeah,
thank you for your answer. Yes.
So yeah, I would say we can move to also questions or comments to other speakers or the same speaker of this last talk. So I will just stop the sharing, Alex.
Yeah.
So we can join all together. So please, yeah, if there is any question, comment, yeah, I can see already one from Luca.
I had a comment for Fedele before. Then I said to move to. Is it still here or?
I'm here.
Ah, yes, I can see. I can see. Just a curiosity, actually, because it was a very nice talk. And another, you talk about Kappa Poincaré, but another very famous group in quantum gravity, but better in quantum cosmology communities, the SU2Q. I have seen also SU11Q in some paper. Did you try to encode also that? Because if I'm not wrong, you told you we have no problem with rotation, but in that case, instead of rotation group, you have SU2Q, and it's quite convenient because typically this is related to cosmological constant. Also, Giovanni showed in his talk some days ago.
No, we didn't look at SU2Q, but we did look at this angular non-commutativity, which is again something in which there is no problem with the problem is with rotations, and there was the part that I didn't discuss. SU2Q, which is another standard group, we didn't look. It would be very interesting to do this, but. We landed on it looking for Kappa-Minkowski, but I'm sure that it can be done, this similar reasoning for all quantum group and their homogeneous spaces. So we just said we're doing them one after the other, but historically you get interested in one rather than the other. This Minkowski is because there are people in Naples, Gianni in particular, looking for Minkowski. So, you know, there was a time when we were actually seeing each other. So if you were we have forgotten this, but if you were physically in the same place, then you start talking and then you get interested in each other. So these things, we didn't actually collaborate with Giovanni, but I was working with Flavio, who was a former student of Gianni. And so we started looking at these things from Kappa-Minkowski, but I'm sure that the same work can be done for
no, sure, Kappa-Minkowski is
yes. If I had an infinite amount of graduate students, I would do all of them.
Sure, in particular, Kappa Poincaré that you mentioned is very interesting also because it was shown that if you take, for example, a Regge-Ponzano model for gravity coupled with scalar field, and you integrate out the gravitational degrees of freedom, what you find is a scalar field theory, which is Kappa, a non-commutative, on a non-commutative spacetime with the Kappa-Minkowski, sorry, Kappa Poincaré symmetry, for example. So. Also, Giovanni proved that in the context of a polymer quantum mechanics, which is toy model of loop quantum gravity, naturally emerged this Kappa Poincaré structure, for example.
Yes.
Are there further comments, question? Luciano.
Yes. Okay. So sorry, I was lowering Luca's end, so that's why it took much time. So actually, curiosity also for Fedele. Okay, it may sound a bit trivial, of course, but I mean, at the phenomenological level, what are the implications of having the non-commutative space-time that you have described? I mean, I guess that the deformation parameter of the algebra also enters somehow in some predictions which can be tested in principle?
It depends on the kind of non-commutativity that you have. Kappa-Minkowski essentially, but again, Jan is not here, but Amelino Camelia is the great expert. The dispersion relations is one thing, and then another, there can be other variations. Instead, for angular non-commutativity, whatever is angular, then it's addition of angular momentum, and it's anything that has to do with angular momentum. And in fact, I'm also looking at G-2. So anything that has to do, so it depends on which kind of non-commutativity. So the original one, the one of Seiberg-Witten, the one used by Seiberg-Witten, that is breaking of rotation. But you have still translations. But then it depends on what sort of non-commutative space, then you can have relevant things. They have to be always either cosmological, or you need some amplification factor. Amplification factor can be something which travels for a long time, for a long distance, or if you have large numbers. In other things can be decays which are forbidden in with one symmetry. For example, there is a lot of work by Trumpetitz and a group people in Zagreb and also people in Würzburg. If you have some non-commutative field theory on non-commutative spaces, then you have some terms which you wouldn't otherwise have. And now this may give you some forbidden decays, like Z going into pi pi and Z going into 3 pi. Now I don't remember very well because I'm not a phenomenologist, far from being a phenomenologist. But so if you have a non-commutative theory, then you have a non-commutative field theory. And this field theory might have forbidden phenomena, but will have some extra vertices or correction to the vertices. Yeah. And this can be seen of phenomena like ultraviolet, infrared. They are nonlinear theories. So there are, in fact, in general, I talk more of this kind of things, but this talk instead I concentrated on the interplay with quantum mechanics and the role of observers. But I can talk. I give a series of lectures on this. So there are, but it depends case by case. One has to go case by case.
Yeah, no, because I was thinking that one of the other implications now, I don't remember probably the non-commutativity with the angular momentum, etc. You said also that time must be discretized at some point. At the end of
another version of non-commutativity, then you have a discrete spectrum of time. Of course, the chronon is called because it was introduced long ago. It's like Planck time. But then there is a uncertainty principle which connects uncertainty in time with uncertainty in angles. So it's like uncertainty between phi, the angle phi at time. It's not very correct because phi is not a good operator, but you can write it in several ways. And so there will be consequences for angular momentum. And the time would be discrete, but the discretization of time would be very minute. I mean, a chronon will be a time 10 to the minus, I don't know. And
I know, but I was asking this because even though, I mean, discretization of time is really tiny, and of course it appears as if it's almost a continuum in a sense. There is a paper of mid-90s, I don't remember exactly, by Burgman, if I'm not mistaken, in which by discretizing time, he showed actually that you can have some sort of decohering process for quantum systems. So in a sense, if there is an underlying theory that is capable of explaining this discretization of time, well, in a sense, one of the implications would be also the coherence that we experience also at the classical level. So that's why I was
What you are saying is very interesting. Do send me the reference. And, I don't know. It's very interesting, but again, I reached an age in which you say I don't know very easily and very often. And please do send me the references. The topic is very interesting.
Yeah. So that's why, I mean, there was a connection in this direction.
No, I can also, now that you mention it, I can also see that is see somehow how it comes about, and so it would be a very interesting reading and a very interesting line of development. By all means, send me the reference. I will read it with great.
And Fedele lost coherence.
Okay.
Okay.
Thank you.
Okay, it was my connection. Sorry, I think my connection went back.
I hope that I was hearing Luciano perfectly well. I don't know.
No, I also.
Yeah, I think it was my connection. Sorry.
Yeah, okay.
Okay, thanks. Any other question or comment or opinion? Okay, so if I'm not wrong, the program says that in
wait, there's still Luca. Luca again. Luca.
Yeah, Luca, speak. You are muted, Luca.
Okay. No, I was saying that if you have also consideration, you can go before. Mine was very general question.
No, I think you had only one.
Actually, no. I think it's very early to say something like that, if I understood. But just to Alessia, all these studies of unitarity can ultimately say something about information loss problem or some. Okay, I imagine that you can manage to prove that quantum gravity is unitary ultimately. But
I think it is a kind of a related but separate question. So ideally, if you are able to derive the effective action, then you can also look for the effective field equations that now, I mean, you can solve them for the effective metric. They look like classical, but they include all quantum effects. And then you can see if you have black holes, if you have a modified black holes, and then eventually study the problem of unitarity in black holes. But at the moment right now, I do not see it as a problem.
It's too early, actually, probably. Too early, I say, probably.
Yeah, I mean, maybe in a few years. And Shravan has another question.
Hi, actually, Luca motivated me to ask another question to you. So, in your talk, when you said quantum gravity might be local, what is the understanding or expectation that how it look like? I mean, what kind of locality?
I'm not saying that quantum gravity is necessarily local. I'm saying that it would be nice not to get rid of locality. That is an axiom of quantum field theory. So try first to see if fundamental locality is can still be retained. If not, I don't know, but I think it would be nice to have something like a fundamental local theory and emergent non-locality that arises only because of the integration of quantum fluctuations. Then it is possible that if I can study exactly the normalization group flow, I can derive a fixed point action that it is non-local. But I mean, I would let the normalization group flow decide on that. I don't want to start assuming that the theory is non-local. I would prefer it to be local, to be as conservative as possible.
Okay.
And so I have a related question to people working on non-local gravity. So I never really get what is the interpretation of the actions that you are studying, like with the form factor, with the exponential. Because if it is that a model for the effective action, in my opinion, that works nicely, can work nicely at least. If it is a bare action, I think there might be a couple of problems. And for instance, the fact that being a bare action, the moment one starts introducing quantum effects, the form of that nice form factors will be essentially gone, because you will immediately produce a bunch of terms. And so essentially the nice properties that you have at the level of the bare action, you would lose them. And in general, the effective action can be very different. It could not be an exponential anymore. And so essentially, that nice form factor would definitely guarantee perturbative unitarity to, but probably not unitarity at the level of the effective action. For this, I mean, one should really study that. And also, I mean, there is the problem of the essential singularity that would not allow to weak rotate. And well, this is a more general problem, because maybe in quantum gravity, maybe it is not even possible to weak rotate in general. But the presence of the essential singularity means that one can never use the residue theorem. A lot of Cauchy integral formula that are really useful in quantum field theory. So maybe can you compare? So it is possible that you really have to study everything in Lorentzian. So anyone wants to comment on that?
I would be happy to comment if hosts allow me.
Yeah, I mean, of course, we are the speaker. Yeah.
Okay, thanks. So, well, as far as I could catch your question, because it was fairly long, related to whether it's basic action, which we're going to quantize, or effective action, it's absolutely true that we have to study renormalization in a sense that we have to understand whether form factors will not be turned apart by some corrections, for example, logarithm of box, which will make them not like exponent of entire function for sure. It's a good question, but let's say like this. So we may hope for this for the moment, and there is any no-go statement that it will happen or not happen. You can, as far as I understand, clearly do this for, let's say, for a scalar model with derivatives, but this is what not you want, because you exactly want gravity, because gravity where you have these factors entering both in propagator and in a vertex. So this is why you want especially to attack gravity. This is tough, and we didn't do it.
Yes.
We didn't do it, and as far as I know, no one has done it, at least in full. There is no anything, let's say, neither promising nor negative on the way. So let's say about this question, we are working. We still have a hope that it is possible to start with such form factors that they will not be spoiled upon computation of your one loop, for example. And maybe it's not a stupid idea to just compute one loop action and see what the determinant will appear in the path integral. But definitely it's much harder than it was done. For example, Fradkin and Zeitlin paper of 1987, if I remember, they did it for R-squared gravity, but you understand that here it's much harder, and we hope to do it one day. But what you say about weak rotation, it is a good question, but it is, let's say, in my opinion, it's solved question. Because it's true that you cannot make use of weak rotation. It's correct. You don't have hope to apply it in all situations. In principle, you can do something very, very tricky and fine-tuned to make weak rotation work, but it's not generic. But generic approach is outlined, well, it's, let's say, very well formulated, but it's very hard to overcome this paper. It's a paper by Pius and Singh. And then we elaborated on this paper recently, me and Anna Tokarev. We have put a paper in March, actually, which is named exactly like explicit one-loop unitarity of non-local theory in Minkowski space. So yes, you can do computations, and essentially it means that you modify a little bit your procedure.
Okay, so essentially you have to take into account the contribution of the contour, I guess, or something similar.
No, it's let's say different story. Contribution of this contour most likely is undefined in a sense that it always will take different values because it's essentially singularity. Procedure tells you different. Procedure tells you that all the integration of internal loops of internal momentum must be done in a Euclidean space. You obtain the result and analytically continue it to Minkowski space. This procedure works in a sense that you observe exactly what you have observed in a local theory if you apply it to a local theory. It also works because the result which you obtain has clear local limit. So you can just take parameter going to 0 or to, well, whatever you define it. In our case, it was exponent of alpha box. So when alpha goes to 0, we have a clear local limit with logarithmic divergence, like it should be in cutoff. And this was actually the whole, not so long, relatively short paper about 10, 12 pages, right, about computing this in 5 to the 4th theory. You can do it, and we expect it should work in a more complex situation, but this requires much more attention because, you know,
yes, absolutely.
Even in a local theory, you know, you obtain some crazy poles here and there. The more propagators you have, the more chances you get some pole when different momenta come to 0 in different combinations. So it's not like easy stuff. Open, for example, paper by Ashok Sen, again, he was devoting the whole paper, about 40 pages, just to compute some box Feynman graph, some 4 fermion, if I remember, scattering or something like this. So, I mean, it takes a lot of patience to do it. Really, even in a local case. Now you go to non-local case, much more trouble, but expectation is that you do apply this procedure and it should work.
Okay, that's great. Yeah, I mean, I agree.
Say something?
So just let me say something in reply to Alexey. So for the weak rotation, yes, I would expect that it is more difficult, but can still be, it is a problem that one can overcome. My main question was about the quantum correction and the fact that in general, since there is no symmetry that protects the form of the form factor, the exponential one, in general, you might have something really different when you, so unless there are really magic cancellations. Because when you study the RG flow, what happens is that you generate all terms are lowered by symmetry. So you have your starting point for your ansatz that is, in your case, the essentially quadratic gravity with exponential form factors of entire functions. But then quantum effects would essentially immediately generate a bunch of terms, and it is not obvious at all that they would resum again to an exponential. Maybe yes, but of course is a difficult question.
Well, exactly as I say, there is no no-go statement for the time being. We're hoping that it will work. Either there is no statement that it will work, and there is no obvious symmetry there.
Okay.
it may happen. So
Oh, good. Okay.
it's just
Thanks.
question for further study, really.
Thanks.
Azran?
Alexey, there's a small point. When you said, okay, you define the theory in Euclidean. Okay, we live in Minkowski. So are you meaning that fundamental theory must be defined in Euclidean if you believe non-local theories are good route to quantum gravity? So
in a sense, yes. I'm saying you that you see, it's like that. If you open a textbook and follow all the computation related to weak rotation, you will see that this is equivalent to what I have said. Okay. The point is that technically you cannot find any. Well, maybe you can find a bunch of other procedures, but this seems like quite natural to do like that, in a sense of its simplicity. You simply can define something which first of all gives you a result which you like, and second does have a limit which you want and need. So and maybe it's not so easy actually to define something else which will, for example, allow you to have a good local limit upon computation. Okay, or on the other hand, it's not so easy to define whatever which you will give you let's say equivalent result to weak rotation as long as you apply it to local theory. So in a sense, yes, I'm saying that whatever happens inside of these loops must be computed as like it was in Euclidean space. But this is actually what you do by Feynman parameterization. Oh, sorry, by alpha parameterization. This is what you do. You eliminate.
Well, I mean, in the local case, you can go from your Minkowski to Euclidean and back, and right here it is not possible. So the only thing I can convinces me here is that okay, well, fundamental theory must be defined in Euclidean. So local theory, there is no problem at all. I mean, it is clear. You can go. We can do whatever you want. So
it's like that. Would I understand completely what was written in a textbook by Peskin, if I remember correctly? It was written like that, that as long as you apply alpha parameterization, and which makes you 1 over chi squared made exponent of alpha chi squared integrated by alpha from 0 to infinity, you can easily, without issues, analytically continue to Euclidean or Minkowski space or vice versa, because in this form, there is no issue of poles. So you see, I mean, even in a local theory, you use kind of tricks. It's not like you always utilize, you see, weak rotation is a nice explanation, but even in a local theory, you could explain exactly in words which I just told you, that what you do, you see major integral which you don't know how to compute, you make use of alpha parameterization, then you analytically continue to Euclidean space to make computation sensible, then you compute and continue back. Result will be the same. So if you look from this perspective and assume that this is your explanation and weak rotation is just extra optional setup, let's say, then you are very good to go. What I want to say, you can easily explain your local theory in just in the same words.
Just a quick comment. Yeah, sorry.
No, Luca, go ahead.
No, you can say. No, I was referring
No, I was
to
just a comment that it is not that in local field theory you can always rotate essentially. So say that you have complex poles in the ROG quadrant of the
yes, but what I'm
plane.
saying, even if you can always weak rotate, it doesn't mean that you cannot, you obliged to make notion of weak rotation as your whatever cornerstone in your definition. Okay, you can equally say that what I do, I put my propagator from denominator inside of exponent, then I analytically continue to Euclidean space, compute, and analytically continue back. Your result will be equivalent to what you get by weak rotation. And maybe, I mean, it's okay, but don't you think that weak rotation may be just more easy explanation of the same thing, which hopefully worked in worked in local case, and really doesn't work in higher than 2 derivatives? Practically more than 2 derivatives, you're already in stack.
Okay, guys, unfortunately, I cannot even make the comment because in 3 minutes we have to start the second session. So I would just say that I think it's time to close this first session of the last day. And I'd like to thank all the speakers for the nice talks and discussion. So I really hope that you will also stay with us for the next 2 sessions until the end of this conference. So thank you very much again.
Thank you.
Thanks.
Yeah, thank you for your questions.
And yeah, I can see a raised hand by Peter. Peter, unfortunately, we are now starting the second session. Let me just unmute you. Hello, Peter.
Hi.
Hi.
So I have 2 comments, one on locality.
No, well, we are starting now the second session, unfortunately.
Oh, sorry, sorry.
Yeah, because we were a bit late. So in 2 minutes we start.
Okay.
Basically. Yeah, I'm sorry. Okay.
Since I see that Jorge is already here, probably you want to try to share your screen so that we can see everything.
Okay. Let me try. Can you hear me well?
Yes.
Okay. So can you see this?
Yes, we can see the screen.
Okay. And try to put it full screen. That's okay.
Okay. Perfect. Okay, just a couple of minutes and we'll start. Okay, I guess we can start. So, hello again, everyone. And after this 3 or 4 minutes break, we are here again for the second session of the day. And we will have 3 speakers now. The first one is Jorge Zanelli. So, Jorge, if you want to share your screen again.
Okay.
So that you can start.
Okay.
Okay, so you can go whenever you're ready.
Okay. Thank you very much, Luciano. Thank you very much to the organizers for inviting me to this conference and for allowing me to share with you our work. This is a work that we have developed with Marc Casals, Alessandro Fabri, and Cristian Martinez. And it's essentially a discussion about what happens to black holes and naked singularities when you add quantum mechanics to them, and to see whether cosmic censorship has something to say about all this construction. So let me start with this presentation. So we all know that Schwarzschild geometry is essentially a solution of Einstein's equations, the first exact solution of the Einstein's equation, which is non-trivial, that has this geometry, this form, where for positive mass, you have a horizon at precisely where this vanishes and this vanishes. And there is a curvature singularity at r equals 0. So the geometry is more or less, you can make a cartoon like this. There is a region inside the horizon where the light cones propagate towards the singularity. So all the future directed light cones end up in the singularity. And outside, all the light cones more or less behave in the normal way. So you have propagation of light outside of this region that reaches infinity. But anything inside the horizon will reach the singularity eventually. So the question is, what happens when you change the sign of the mass? Well, then you get this doesn't vanish anymore. And then you don't have a horizon, and the singularity becomes a naked singularity. And this is an infinite curvature region, and to have a singularity is certainly a problem. And then the information that propagates from the singularity can reach infinity also. So observers outside can see the singularity. You can ask, well, so what? I mean, who cares about that? I mean, what is the problem with singularities? Well, the problem is the following. If you're trying to do physics, like if you try to solve the wave equation, and you have some initial condition, and you want to propagate those initial conditions from a Cauchy surface to a future, then usually what happens with this operator is that you propagate signals from the point, the source, to a future surface. And everything inside the light cone of that point is going to be affected by what happens here. Now, if you here have a singularity, then this integral, this solution will not be possible to know in this region. Because if there is a singularity, this integral cannot be evaluated. And therefore, you do not have information about what happens here, because you don't know how to incorporate the effects from here. And then the information about the future, in the future, will not be possible in these points. Now, as time progresses, you will be on a different surface here, and then the amount of ignorance about the situation here is going to grow, and eventually it's going to cover the whole space. So that means that if you have singularities like this, the breakdown of the geometry of the space-time continuum will make this possibility of knowing about the initial, the final state from the initial state becomes completely blurred. So singularities that are causally connected to us, like this, like naked singularities, give rise to serious problems in physics. Physics would fail to be a predictive science because causality, conservation laws, and stability and predictability will not be valid anymore. So you will not know what happens, and you will not have a predictive theory of the world. As Jan Hirman said in pictorial way, it says green slime, lost socks, and broken TV sets could emerge from naked singularity. So anything can come out of them. And then physics will not be a science anymore. So, but the fact that we have black holes in nature is an indication that something is more controlled, because black holes having a horizon protects us from this exposure to naked singularities. And this is a good news. But still, singularities can occur and occur generically. And this has been shown by the theorems of Hawking and Penrose, that any reasonable initial conditions will generate singularities at some point in general relativity. So if you start with a generically regular initial condition in general relativity, the solutions of that will generate singularities of space-time. Now, this theorems only hold in classical general relativity. So it might be that quantum mechanically there's something different. Also, this does not specify the type of singularity. There could be any or several types of singularity. In particular, there could be naked singularities. That is not ruled out by these theorems. Now, Penrose immediately noticed that the problem with singularities is only those that are causally connected to us. So he wondered whether there exists a censor, a way of forbidding this, that forbids the appearance of naked singularities, clothing them with an absolute horizon, so that it would be nice to have a mechanism to produce an obstruction to naked singularities. So he proposed this conjecture in 1968, says that there must be a physical law which implies that naked singularities cannot exist in nature. Of course, this was proposed as a conjecture because we know that it is probably true, but he didn't know, and we still don't know, of a proof in general relativity of this fact. So the conjecture seems to be true because we have the overwhelming experience that physics is a predictive theory. Therefore, we can infer what's going to happen in the future. If there was naked singularity somewhere in the universe, that would not be true. But there is no proof of that. We don't have a proof of the cosmic censorship conjecture. Now, Christodoulou, over several decades of work on this, has convincingly shown that naked singularities can be produced by collapsing matter, collapsing dust, or he tried also with perfect and imperfect fluids, with scalar fields, with lots of things, and every time he could show that naked singularities could be produced. However, these naked singularities require some fine-tuning. So the initial conditions have to be carefully chosen to do this. And also in all the cases, or most cases, it's been shown that these naked singularities appear when the solution is spherically symmetric. And we know that in nature, collapse, like after a supernova explosion or so, it's very rare that it happens with this perfect spherical symmetry. Usually collapsing matter will become a rotating body. So there will be essentially an axial symmetry, not spherical symmetry. So for astrophysical phenomena, spherical symmetry is very rare. Now, since there is this need for fine-tuning in the production or the formation of naked singularities, indicates that naked singularities are probably unstable. That means that if you perturb them, they will not be there. So it could be that you need a perfectly spherical collapse to produce naked singularities, but if you have a little bit of angular momentum, this will not be true. So the question then naturally comes, if you introduce quantum mechanics, maybe quantum mechanics could prevent naked singularities. Because of course, quantum mechanics means that there's something that can be fluctuating, the vacuum can fluctuate. There would be a possibility of producing something so precise that there would be no uncertainty in the rotation or the position of things. So spherical symmetry is very rare to produce in this case. So maybe quantum mechanics could prevent naked singularities in the same way that it prevents the electron to fall to the nucleus in an atom. But the problem is that quantum mechanics is very difficult to do in gravity. We know that quantum gravity is still a hope or a dream, but not a reality. So the problem is intractable in 3+1 dimensions. We don't know how to do quantum gravity in 3 dimensions. So we can go down to 2+1 dimensions. So the plan is the following, is to consider the simplest naked singularity of black hole in 2+1 gravity, coupled to matter, switch on quantum effects, and see what happens. Actually, we don't need to worry about quantum gravity in 2+1, but we can do quantum field theory in 2+1. And when you say that, see what happens, because we don't know what the back reaction of that will be. Because these quantum effects will produce an effective T mu nu, or it will be a source for the gravitational field, and then the gravitational field will change. So for instance, if you have a black hole and you introduce these effects, maybe the black hole will grow larger, or maybe it will shrink, or perhaps it will evaporate or become eventually a naked singularity. Also, if you start with a naked singularity and follow these steps, maybe you will get a sharper singularity, a more severe case of singularity, or maybe it will be softened, will be a smoother type of solution that will not be singular. Or maybe it will also evaporate or produce black holes. We don't know. So this is a setup or a study, and this is what we try to do. So starting in 2+1 dimensions, if you take the rotating black hole in 2+1 dimensions, this is the solution. This metric function f is essentially the mass, the angular momentum, and it's a function of r. And the shift depends on the angular momentum. So when you have angular momentum 0, this term vanishes, and it's a very simple function, and there's no shift, and then everything becomes very simple. But this is the most general massive rotating black hole in 2+1. The horizons are at the zeros of this expression, and the zeros of this expression have this form. So you see that if m squared is larger than j squared, this is real, and therefore there are two real solutions for this. And if m is positive, then there are two real positive solutions. So for m larger than absolute value of j, and being positive, you have two solutions here. You have two roots, and these correspond to the two horizons of the black hole. If m is -1 and j equals 0, this is anti-de Sitter space. There is no horizon, there is no singularity. This is completely smooth and maximally symmetric space. And if the mass is less than the absolute value of j, so it's a negative, or it could be outside this region, and it's not equal to -1, so it's not in this case, then you have naked singularities. So the picture is more or less like this. In the mj plane, this is the mass, this is the angular momentum. This region here corresponds to black holes. These are the extreme black holes, the red lines. This is a massless black hole. So it's a solution with zero mass and zero angular momentum that is still a singularity and still it qualifies as a black hole. Here is anti-de Sitter space, and this point here corresponds to the maximally symmetric 2+1 space-time with no singularities. And all the green region, all these are naked singularities. So you can consider, for instance, a solution here and do the procedure that I mentioned to study quantum effects on this. And this solution will probably move in this plane somewhere. So the question is, where does it move? Does it go this way, this way? Does it go into the green region or what? And if you start with in the green region and you introduce quantum effects, does it go into the red region or remains here or what? This is essentially the question that we have. Now, black holes and naked singularities in this plane are obtained by identifications on this pseudosphere. This pseudosphere is a constant negative curvature, maximally symmetric surface embedded in R22. So this is a pseudosphere with two minus signs and plus signs that has negative curvature. This manifold has 6 scaling vectors, and therefore you have 6 ways of making identifications in this region. And this produces six types of solutions. The solutions that I mentioned before. So this is one type. The extrema black holes is another type. The zero mass black holes is a third type. And then there are 2 types of naked singularities here, and there are also extreme naked singularities somewhere here. I will go into that. So those are the 6 types. So the type of killing vector depends on which matrix KAB one chooses. And these correspond to the different eigenvalues of this matrix, that the 6 types of geometries that you can find. Now, if the killing vector K has fixed points, this produces a conical singularity. If the vector K is time-like, this produces closed time-like curves. And this is, again, problematic because it means that you can kill your grandmother and you don't know what happens. So in the case of black holes, you can obtain the black holes by these identifications. These are the regular or generic spinning black hole with R plus and R minus. And this is a linear combination of the two generators that make identifications in the 1-2 plane and the 0-3 plane. So a rotation in the 0-3 plane is a boost, and a rotation in the 1-2 plane is another boost. And so the linear combination of those two boosts produces this generic black hole. In the case of extreme black hole, there's only one horizon, and that's also a linear combination of generators of different boosts and rotations. And the zero mass black hole is still another one that has no parameters here. There is no R plus or R minus because this has no free parameters. So this is a zero mass black hole. Now, all of these are elements of the SO22 group, which is a group of invariances of this pseudosphere. And all of them have no fixed points, so there are no conical singularities. So the black hole has a singularity at the origin, but it's not a conical singularity. Since all these vectors are space-like, their norm is positive, there are no closed time-like curves. So in these geometries, nowhere you could find closed time-like curves. Now, if you want to make a conical singularity, you have to make an identification in the spatial directions. So if you can imagine anti-de Sitter space to be something like this, and you make a cut here, and you sort of eliminate a slice of a cake. So you identify this plane with this plane, and this angular deficit produces a conical singularity here in this line. So the identification is by the J23 generator. So it's an identification by a rotation vector. So it's in this plane, in the 2-3 plane, it's a spatial rotation. And of course, this is dd phi, the angular direction. So if you make identification by this and of this size, that produces a conical singularity precisely of that strength. And this generates its delta-like singularity here in the curvature. So because the curvature is like a tip of the cone at the r equals 0 point. So in that case, the killing vector is this, is a rotation killing vector, it's a space-like and has a fixed point at r equals 0. And identification by it produces this conical singularity. Now the curvature in that case is this part is a constant curvature anti-de Sitter geometry. So locally, this term is still there, so it's a constant curvature manifold. But it has a delta with support at the origin that is precisely where the singularity, the conical singularity is sitting, and the deficit angle appears here. So the larger the deficit angle, the stronger the singularity, the conical singularity. And this is in the 1-2 plane. This singularity has no horizon, there's nothing surrounding it. And if you write down the metric that you obtain in this case, the metric is essentially like the metric of the black hole, except for the fact that the mass now is negative. And the mass is being negative means that you're in the same plane of the black hole, but in the lower half part. I mean, you're in the negative mass region. And of course, if alpha is equal to 0, there is no deficit that corresponds to m-1. That's the anti-de Sitter space you started with. And if alpha is equal to 1, the deficit of 2 pi, so that's the maximum deficit, that corresponds to the zero mass black hole. So if you go again to this plane, you can also look at this way. These are the black holes that we started with. This is the region where you have these conical singularities. This is no conical defect. This is a maximum conical defect. This is a 2 pi defect. And in between, there are all the possibilities. And here, instead of being defects, these are excesses. These are conical excesses. So instead of being a piece of slice that you remove, you add some slice in the middle. So this is a rotating conical singularity. It's the same formula as before, but here the mass is negative. So you're in this region, and this produces something that is always positive. This metric coefficient is always positive. the roots of this problem are in the complex plane somewhere, so there are no real solutions, there are no real roots of this equation, of this equals 0, and therefore there's no horizon. And we are working in this region. So the identification that you do to make this solution is essentially a rotation in the 2-3 plane or the 0-1 plane. So it's a rotation here and a rotation here. So any linear combination of those two produces these two coefficients for the identification. Now these are compact elements of SO2. As I said, it has a fixed point, therefore it produces conical singularities. And it's also space-like, so there are no closed time-like curves. So this region, in spite of the fact that it's a singular region, has no paradoxical closed time-like curves. So now let's briefly look at the quantum effects. So in order to study this, we observe that in 2+1 dimensions, general relativity has no local degrees of freedom, and therefore there are no gravitational waves. There are no gravitons, and therefore there are no quantum gravity corrections. So you don't have to worry about quantum gravity. The only quantum effect can come from matter that you put on this solution. So we consider a system which combines the Einstein-Hilbert term with cosmological constant that gives rise to these solutions. And we add a scalar field conformally coupled to the geometry. Now, the conformal coupling is a useful tool because it makes the calculations much simpler and makes the propagator of this problem a local expression. Also, it gives analytic results, as I will show. Now, in order to compute the back reaction, we have to calculate the stress energy tensor produced by vacuum fluctuations of this scalar field. And we evaluate this on the black hole or naked singularity geometry. Now, you do this by the standard quantum field theory calculations, and you obtain what is the T mu nu, and you use that T mu nu as a source for the Einstein-Hilbert equations. In the Einstein equations, now you don't have a 0 here, you have this quantum source, and then you can calculate the solution of this under this new source. The solution would be the old solution plus some modification, and this modification is what we want to calculate. So after some struggle, you can get the form of this solution. This solution was found by many years ago by different people. And it's essentially a contribution which is diagonal, has traceless, so it respects conformal symmetry. You plug this into the Einstein equations, and here comes the solution. Now, the solution for this is a metric coefficient that before it was like this, and you get a quantum correction. So this quantum correction has a coefficient that corresponds to the Planck constant or Planck's length. And this function f is just the same function that appears here. It's some strange explicit function of the mass. Now, if you look for the zeros of this, now you have zeros, because before you didn't have this term. This has no zeros when m is negative. This is it's just a parabola. But when you add this term, you get something new, and then there appears a possibility of a horizon. This was a parabola in the coefficient when there is no quantum correction, and this is a quantum correction, and the intersection of this produces a horizon here. The horizon then comes it's a solution of this equation. This equation has a solution that is of order h bar for large m, as order h bar to 1/3 when the mass is small. But in any case, there is a solution, there is a horizon, and therefore you can see that the quantum corrections, what it did to the naked singularity is that it produced a small horizon around the origin, covering the singularity. Now, static naked singularities are exceptional in the same way that black holes are static black holes are exceptional, or static planets are exceptional. And so the suspicion is that maybe this is due to fine-tuning. So in order to be convinced, we have to do the same calculation when the system has angular momentum. And then we did that. And I don't want to bore you with the details, but the solution is the following. Before you add the quantum effects, the metric coefficient was this, and for negative mass, it's always a positive quantity. But if you add, so this red line corresponds to that. But if you add the quantum correction, then you get this line. And the intersection of the two, again, happens to have a finite contribution, a finite zero. That means that there is a finite horizon surrounding the naked singularity again. So naked singularities in both cases become black holes of the size of the Planck length, more or less, of the order of Planck length. So the picture that we have is that near the singularity, you have a conical singularity in the classical case. When you add quantum effects, you get a horizon that is of the order h bar due to the quantum corrections. And this is true for the static and the rotating black hole, the naked singularity.
Jorge, you have
so to summarize, 4 minutes, good. So quantum corrections, as I showed, generate horizons around naked singularities, and then they become black holes. This quantum mechanics, therefore, provides a mechanism to implement the cosmic censorship, at least in this case. This effect seems generic in the sense that it's true for static and spinning black hole naked singularities. And it also happens to be the case for black holes. If you have a naked singularity also in a flat space, not in an anti-de Sitter space, and you do the same calculation, the interesting thing is that the quantum correction produces a horizon and also produces a small negative constant cosmological constant. So it's also generic in the case of at least naked singularities in flat space. Also, if you look at the effect of these quantum corrections on black holes, the black holes also change a little bit by the introduction of quantum effects. The black hole horizon radius, the event horizon, increases by something of the order of Planck length. And the inner horizon of a black hole becomes unstable by these perturbations. There will be an accumulation of surfaces of infinite energy at the R minus in the Cauchy horizon. So the picture in the case of black holes is like this. You have a rotating black hole of radius R plus. When you add the quantum corrections, the radius increases a little bit. And in the interior region, the interior horizon becomes a region that is full of infinite accumulation points of energy. So Einstein might have been right in saying that nature abhors singularities. He didn't like the black holes of Schwarzschild in particular because he thought that singularities would not be physical. But this resistance of nature to singularity is not a classical effect, it's a quantum effect. It's a consequence of quantum mechanics, at least in this case. So if that is the case, if that is true, quantum mechanics would not only be responsible for the stability of matter, like the stability of the atom, it also could be responsible for the existence of a predictable universe because it would eliminate the possibility of naked singularities. Now, let me make a disclaimer here. The naked singularities I've been discussing here correspond to some particular class of singularities that are called quasi-regular, which are not so catastrophic as the naked singularity that occurs in the Schwarzschild solution when the mass is negative. These quasi-regular singularities are mild enough so that the initial value problem is still tractable because they are something like boundary terms or surfaces where you stop, where you have a boundary of space-time. Severe singularities like the negative mass Schwarzschild black hole could not be treated in the same way as we did here because we could not construct, could not produce a propagator in that case. So questions for the future is what happens with other singularities in the region, which are also naked singularities, but could not correspond to conical singularities, but these over spinning solutions. What happens in 4 dimensions, for instance, you take a cosmic string in 4 dimensions that corresponds to something similar to the naked singularity in 2+1. What happens if you add other types of matter, fermions or electromagnetic fields? What happens with thermodynamics, Big Bang, and so forth? And this is an interesting case here because it's a scalar field in the analogs of black holes or analogs for tabletop experiments using graphene, for instance, could correspond to phonons in the graphene sheet. So it might be interesting to see what happens if you have a naked singularity in graphene and study the quantum corrections due to the phonons in that region. Does that produce something like a black hole? So this is it. Thank you very much for your attention.
So thank you, Jorge, for the very nice talk. And okay, we have time for questions. I saw, yeah, before Alfredo and Lorenzo, there was already a question because I saw a raised hand during the talk. So I don't know if, yeah, we had also another question before Alfredo. So I was wondering if, okay, Eva is here. Okay.
Okay.
Hello. I have several questions, so I'm just going to ask one now and then save other ones for discussion session. So I was wondering, you said that that you have six types of solutions. So this was non-physical types, and the type 3 plus and minus you consider as one type.
Oh, let me see if I can go back to the slides. Okay, so let me try. Okay. Can you see this?
Yes.
Okay, so the black hole solutions are the ones that we are all familiar with. These are the conical singularities, and they have conical defects. So they're naked singularities, but there are no closed time-like curves. Here they are overspinning solutions. So the six types are 1 here, the extremal is 2, the zero mass black hole is 3, the conical singularity is 4, the extremal conical singularity is 5, and the overspinning solutions 6. Now, none of these have closed time-like curves. Even the overspinning solutions have no closed time-like curves. So all of these, the overspinning and the conical singularities have conical defects or conical excesses, like in this case. So they are exposed singularities. The black hole is the only ones that have horizon, except for the zero mass black hole. But all of these are in some sense reasonable solutions. I mean, you can write down a propagator, you can study geodesics, you can do experiments, and you can even produce them probably in a lab, like I said, maybe in these analogs of gravity that people are working with. Does that answer the question?
But these solutions in the green have one of their eigenvalues is imaginary.
Oh, yes. That means that there is no horizon. Okay, so let me go back to this expression here. If these are real numbers, that means that they're real horizons. If these are imaginary, that means that this is always positive. F, for instance, is always positive. There are no real roots. And then this geometry has no zeros anywhere. This has no zeros anywhere, but there is a singularity at R equals 0 anyway. So in that case, there will be a singularity without horizon.
I see. Okay. So the fact that it's imaginary refers only to existence of the horizon.
Right. The position of the horizon will be in the imaginary plane. So it's not there. That there's no, because you stop it, you always consider R to be a real variable. So having an imaginary solution for that means that there is no solution.
I see. And then you can just go from one type to another by letting these different values of mass and angular momentum. And right. That's all like regular. Physically, it's okay.
Yes, that's right. Yes.
Okay, okay, thank you.
They all correspond to identifications in this pseudosphere, different identifications.
Right, thank you.
Okay, sorry, Lorenzo, but we have time for one more question. But if you stay with us, you'll be the first at the beginning of the discussion session to make a question to Jorge. So, because Alfredo...
can I come forward?
Yes, you can make the question now, but Lorenzo will be the first at the beginning of the discussion session. That's what I said.
Okay, so thank you very much, Jorge, for a great talk. I was, as you might imagine, very excited. So, of course, I have several questions, but only one, which is something. Okay, you said you expect to have quantum matter here corrections, but then in the last slide, where you actually were referring to possible realization in graphene-like scenarios, you were mentioning phonons, which would represent here the gravity side. So I was a bit puzzled by that. No?
Well, in gravity, we don't have no quantum effects. So the fact that you have a black hole or a naked singularity is a global identification in this surface. So the geometry of the black hole and the geometry of the naked singularity does not vibrate. That would be a static solution. Okay. Now you can imagine that this adding phonons would be a deformation of the geometry. But if this geometry is governed by Einstein's equations, this is not the case, because the Einstein's equations do not allow you for vibrations. There are no waves in 2+1 dimensions. So you can mimic the vibrations by imagining some other distortion in the case of graphene, for instance, but not in the Einstein's equations. In the Einstein equation, that's not happen. So the Einstein equation does not have excitations like that. There are no localized waves in 2+1 gravity. So again, it's an analog, and it's not going to be the same system. It's not the same action. It would be a different action. Okay.
Precisely, that's the bit of the question, because you don't expect the geometry gravity description of the membrane to be like general relativity. You expect something more complicated, for instance, teleparallel or I know, with some torsion.
Yes.
Would this affect very much your thing here, or?
Well, you have to sort of think of it again, because it's not. It means that the graphene description is probably some aspect of this gravity, but not all of them. Some aspects that are in graphene are not replaced. They're not represented in this gravity theory. Maybe in a different gravity theory, which is a modification of this, perhaps if you put, instead of a cosmological constant, a cosmological variable, a dynamical variable, or instead of the Newton's constant, some other function. So it's like a Brans-Dicke theory. Maybe some other modification of gravity would correspond more closely to graphene in that case.
Okay, thank you.
Okay, so all the other questions to Jorge can be postponed to the discussion session, and I would like to thank Jorge again.
Thank you.
Okay, so we have now, Jorge, if you can stop.
Yes, I'll stop sharing.
Yeah, okay, perfect, thank you. So now we have the second speaker of this session, ChunJun. Okay, you're here. I hope I pronounce your name correctly. So, okay. ChunJun? Okay, are you here? Okay. No, so that's why. Okay. So the second speaker for this session is ChunJun Kao. So whenever you're ready.
Thank you. Good morning, good afternoon, good evening, depending on where you are in the world. So I'm very thankful for the organizers for this invitation, as well as we're putting together this wonderful workshop. So all of us here are interested in, let me just get a laser pointing out. So all of us here are interested in some aspects of gravity and quantum mechanics, in particular their commonalities as well as their differences. So in particular, those of us who are interested in quantum gravity are more partial to learning about how to reconcile the differences between the theory of gravity and the theory of quantum. But before we just go ahead and start quantizing gravity, let's take a step back and ask ourselves that what is it that we do to usually, and if we just look at undergraduate quantum mechanics, our usual approach is that we start with some classical theory, classical action, something that we have good intuition of, like a harmonic oscillator or some scalar field with good classical actions, and then we quantize it, right, following a set of rules like path integrals or canonical quantizations. And all of those work very well. But what's inevitable from these approaches is that you tend to inherit some of the structures that you have from the classical theories, like geometry, gauge symmetry, space, locality, etc., etc. And in a lot of times they help us, but in sometimes they also hinder us from making progress. So in this talk, I would like to take the converse approach to quantum gravity, namely that instead of quantizing gravity, we would like to posit quantum mechanics as the fundamental theory. Namely, I just mean that I take some vector in the vector space. Here is a wave function, and the dynamics is generated by some Hamiltonian. Again, I did not specify anything else, right? So other than that, you really don't know anything. There's no pre-existing notion of space-time, etc. And what we want to do is that we want to back out the notion of geometry and gravity from this complex quantum system where there is none in the beginning, or at least it wasn't apparent. So in other words, instead of quantizing gravity, we would like to gravitize quantum mechanics. We would like to find a special set of quantum mechanical systems in which gravity can emerge, or at least something that looks like gravity can emerge. So that is the ambition. And for the roadmap of this talk, we're not going to talk about dynamics at all. We're just going to focus on the kinematics and the state, and try to focus on how we can extract information from just this vector in the Hilbert space. In particular, we would like to understand, is it possible for us to, just by looking at the state, using the quantum information that's stored in the state, can we restore some semblance of matter on the spacetime background, something that we know and love? And on top of that, do the matter and the background geometry that we derive or emerge from the information in the state actually produce something that looks like gravity? So how do we go about doing that? Well, for example, let's take a state, and let's say the state lives in the Hilbert space, and that also can be factorized into tensor factors. All right, what can we learn then? Well, the first thing we can learn is that because of the tensor factors, we can study the subsystems of each state, and we can compute reduced density matrices corresponding to each subfactors, and then compute their correlation in the form of a mutual information, I over here. And then we can transform, or we can rewrite the state into a graph. So where each of the vertices is really corresponds to the subsystem that's associated to a particular tensor factor. And their edges are weighted by the correlation that's among the subsystems. And then we just turn this correlation around and use that as a distance measure. For example, larger the mutual information. Mutual information is a measure of correlation. So then that means higher correlation. And we're going to say, well, two things are closer because they're highly correlated. And conversely, if something have low mutual information, they have low correlation, they're farther apart. And that produces for you some notion of distance. And you can then use this notion of distance to reorganize these vertices, where each of these blue dots now are one of those vertices. You can reorganize these vertices in a way that's most consistent with the set of distances that you got. And this, of course, you follow a set of algorithms that are very commonly used in manifold learning, and you can figure out what the rough shape or the emergent geometry, so to speak, that's hidden in the state. And if you're lucky that your state actually does have an emergent geometry, you will be able to find, for example, its best fit dimensions. And on top of that, you can also figure out roughly how those vertices should be placed relative to each other. Now, this, of course, is a warm-up, right? It gives us a very rough idea where things are just from the information that's hidden in the quantum state. But the question, of course, is can we do better? with the stuff that we have that's hidden in the quantum state. And in particular, we'd like to back out some notion of matter, how matter can be separated from geometry. So how do we do that? One approach is to focus on a specialized set of states that we, in quantum information, we know as the quantum error correction codes. So as we all know, if you want to do practical quantum computing, you want to protect the information against environmental noise. And the way to do it is that you encode it into some error correction code such that noise does not destroy your information easily. So what I mean by quantum error correction code here is that, so originally you have some Hilbert space, which we just looked at, and then it might have tensor decompositions. So in the practical setting, you can think of this Hilbert space as space of qubits, bunch of qubits, and each tensor factor corresponds to a qubit. And the quantum code is simply by taking a subspace of this physical Hilbert space, because you may not care about everything that's in this space. Okay, and now let me just take a state that's in this subspace, and usually these states, these are called these states contain what we call the encoding information. These are the states that we care about, and they have certain nice properties. Okay, so just to give you a, just to give you a more concrete example, here is a quantum error correction code on 4 qubits. So for instance, instead of calling the 0 state, I'm going to call this 4 qubit GHZ state the 0 tilde state. And so that's an encoded version of the 0 state. And similarly, I have an encoded version of the 1 state. So this is a code that is defined by the code subspace were spanned by these 2 states. But there is a more compact way of expressing codes, namely through the encoding map. It's really just a way to package all of these subspace into one mathematical object that takes the form of an isometry that maps the information that you want to encode into the space of your physical qubits, so to speak. And it also has a graphical representation here. So in this representation, the red arrow indicates that the encoded bit of information, and the 4 legs are sticking out represent the physical qubits in which the information is encoded. And the encoding map, of course, just spreads this encoding information among all these physical qubits through the help of entanglement. All right. So the fact, in what sense is it the error correction code? Well, suppose you actually encoded the state, that this is the psi is the state, the information that you care about, and you encoded the state into this quantum error correction code, and something happened that you lost qubit number 4. So this is called an erasure error. And it turns out that this code can correct such errors, that if you only have qubit 1, 2, and 3, you can still recover the information by acting on the state, and you can extract the information that you actually care about, and you're left with the piece that you usually throw away. But if you just look at if you just stare at the code, you realize, well, there are 2 pieces of information here, really, right? In any quantum error correction code, the first piece of information is the encoded message, obviously, it's the part that we care about, and the second part is the leftover piece. And this leftover piece usually has a lot of entanglement, which is essential in helping us build a good code that's protected against errors. Now, what I'm going to claim is that it's natural to identify this encoded message with whatever that builds matter field, and it's natural to identify whatever the underlying entanglement that goes into the code into something that builds background geometry. So to make this identification more concrete, let me go into this ADS-CFT or the quantum gravity in a box setting. Right. So here we should think of it as so ADS-CFT, as some of us know that it has some resemblance with quantum error correction codes, and in fact you can define it as a type of quantum error correction code. And here are some discretized implementation of it. just for good intuition building. Now, what these codes are is that they are really quantum sets of quantum states that have emergent hyperbolic geometries, such that you can arrange these qubits or these quantum degrees of freedom by their correlation in a way that's naturally have a geometry associated with it. But what's special about these codes is that both the physical qubits and the logical or encoded degrees of freedom have two sets of the different geometries. So here, the physical qubits, which are these white dots along the boundary circle, obviously lie on the circle, whereas the logical degrees of freedom, indicated by these red dots, these are the encoded degrees of freedom, and they are naturally arranged in a way that's in a higher dimensional hyperbolic disk. Now, what's nice about this is that in ADS-CFT, these logical degrees of freedom, they just correspond to bulk effective field theory degrees of freedom. So they are really the matter field degrees of freedom that's floating on top of ADS spacetime. But so that's sort of already one piece of information why the logical or the encoded degrees of freedom should be associated with matter fields. On top of that, you see these edges that connect the different blocks, the vertices of this graph. While they are in fact indicative of the entanglement structure that underlies the state. In particular, in this is just expressed in this tensor network language. So in this very vague sense, we already see that, well, there is some connection between the encoding information being the bulk fields and the underlying entanglement being building geometry in this way. But in fact, you can make it a lot more precise through entropic identifications. So again, thinking back to this decomposition of two pieces of information in a quantum error correction code through decoding, really. So you add some mapping that extracts the information that you encoded and you're left with some leftover information. But in generally, you can also do this for more complicated codes, not just the 4-qubit code. So you're left with something that's more generic, of course, but these states can in general be mixed. And so is the encoding information. Now you just compute the entropy of both sides of this equation, right? So the left-hand side of the equation gives you some, this is the von Neumann entropy of a subsystem of a quantum state. But because of decoding, you can naturally separate this entropy into two parts. The first part associated with the encoded, the entropy of the encoded message, and the second part that's associated with, again, the entanglement that underlies the quantum error correction code. But in the holographic setting, ADS-CFT setting, if you take the continuum limit in some sense, you actually just recover the so-called RT-FLM formula, where this encoded piece just turns into the entropy of the bulk matter in some subregion, and this this other entanglement piece, it just turns into the area of the minimal surface. In this case, it will be the length of this geodesic that's bounding the wedge over here. And while since the RT formula is really very reminiscent to the generalized entropy, right? You just break it down into horizon piece and break it down into matter piece. This this identification from quantum error correction codes is a code version of that generalized entropy. And but of course, the things that we just talked about, although we used some analogy going back to holography that allows us to make identifications more easily, the properties that we mentioned really holds for any quantum error correction codes. There's no reason why the code has to be taking the form of a particular geometry. For example, you can fairly easily build a code. You take a state that's some kind of error correction code, and then you do the same thing. You can break down the von Neumann entropies of different parts of the state using what we had before into a matter part, the encoded entropy, and the geometric part that's tied to the code building. And then you can analyze the geometry of this emergent geometry of this geometry part of the entropy, and you can back out some metric tensor. And in fact, this can be even explicitly done, right? So especially if your emergent geometry is near flat, then you can even back out the metric tensor and so on and so forth. Well, so that's nice, but it's not good enough, right? So we have some geometry. It would be nice to also say, well, is the matter that you backed out and the geometry that you backed out, are they interacting in a way that's consistent with gravity? To do that, let's first look at let's first translate gravity into the language of quantum error correction code and how it could manifest itself. For example, you've identified some code, right? And then you had some emergent geometry using the mechanism that we just described. And now you can change the encoder state a little bit and here and there. And then by doing that, you would have changed the matter field distribution, right? And the question is, does this change of matter field distribution correspond to the correct change in the underlying background geometry? And you can we can see that by just translating translating this the linearized Einstein's equation, for example, on this background, let's say that's near flat, into an entropic constraint. And this can be done through a fairly simple set of steps. But the point is that if you want a quantum error correction code from which you can emerge linearized Einstein gravity, or in this case, just a linearized Hamiltonian constraint, it has to satisfy some entropic constraint. And this is really the two parts, how the two different parts of the entropy change, they're locked to change in a certain way with respect to each other. And this is actually really intuitive because this encoder part is, again, tied to some matter field, and you can write, it's actually some function of the stress tensor. And well, if you change the encoder state, and namely that you change the stress tensor, would have changed this guy, but this constraint tells you that this other term has to change as well. But remember that this term is tied to the emergent geometry, which means that the underlying geometry also has to change. So this is just a long-winded way of saying that matter back reacts on spacetime, and you can change the spacetime geometry, and this is simply an entropic repackaging of that. And now we can ask, well, do the codes that we have so far satisfy these constraints? And the answer is no, right? So the codes that we looked at so far is really more like a QFT on curved background, where again you have the encoding information to correspond to matter field and the entanglement that correspond to space-time. But no matter what your matter field configuration is, it turns out that this piece would never change. The underlying entanglement structure of the code is never changing. And that this is reminiscent of matter being decoupled from gravity. And can we then couple matter to gravity? At the very least, I would like to have, whatever the entropy associated with the geometry should change whenever I change the encoding information that's tied to the matter field. Well, is it possible? Yes. So if you instead of considering a good quantum error correction code, you would like a code that's not so good. So the codes so far that we looked at have very good properties in terms of quantum computing. But in general, that might not happen. And for example, you have some small coherent noise when you're performing the encoding process, and that resulted in a noisy encoding map. So instead of getting the clean one that you would like to construct in a lab, you picked up some extra terms that are corresponding to noise, right? And so in the end, you would get some encoding map that with coherent noise injected. One such an example would be again this kind of 4-qubit code, but here alpha beta can be unequal. So when alpha is equal to beta, this is an exact erasure correction code. This is namely a code with very good properties. But when alpha is not equal to beta, then this becomes a quote-unquote noisier code, and it doesn't have very good error correction properties. And now if you just plug this code into the kind of tensor network models that we looked at, this will turn it into V epsilon, the noisy encoding map of a more complex form. And in fact, you can also break down this map into a superposition of different codes, each of which corresponds to a different background geometry. But the point is, for this kind of code, when you change the encoded message, it can lead to changes in the entanglement, underlying entanglement that makes the code, which is reminiscent to changing matter entropy distribution. You would have changed the entropy that's tied to the horizon area. There are also other properties of this thing that are reminiscent to gravity, but I don't have time to go into. But let me just focus on one sort of, I think, neat graphical example of this analog of back reaction. So in holography, you can sort of probe in any geometry, you can probe what the geometry looks like by drawing geodesics, right? If the geometry changes, chances are some of the geodesics will also change. And in holography, you can figure out where these geodesics are through drawing these entanglement wedges, so to speak. We don't have to care about the details, but the point is that the boundary of these wedges correspond to the location of the geodesic in this ADS space, or whatever background geometry that you have. So if you have some initialized the bulk into some vacuum state, or there's a particular set of state in this quantum error correction code, you will get a geodesics as someone coinciding over here. That's similar to the vacuum configuration. However, if you have you change it to another state, then now the change in the bulk information actually changes the underlying geometric structure as well. And you will see the geodesics are curving around where this information is being injected, and that's sort of reminiscent to having a massive configuration. And last but not least, heuristically, the strength of noise is sort of analogous in this case to the gravitational constant, in the sense that if I take this, the noise equals 0 limit, you recover the original QFT and curved spacetime limit where matter does not, is completely decoupled from gravity. Whereas if epsilon is large, then actually there is no clear-cut way of distinguishing which one is the dominant geometry. You're left with a superposition of different geometries. And so in this sense, that the emergent geometry becomes highly quantum, which is a regime where we think quantum gravity should dominate. But the bottom line is that, well, it's interesting that features of gravity emerge when the code is made worse, and it's not desirable for quantum computation, but it's very nice for gravity. However, we're only halfway there. For example, for these kind of codes that we discovered, of course, the underlying geometric piece can change with respect to the encoded state, but it doesn't quite change in a way that's consistent with Einstein gravity yet. So the next step would be to turn this function into the actual von Neumann entropy. But then on the nice side is that they're just quantum error correction codes. Right? They're always well defined, and they're just the simple quantum systems that you can, and there's no obvious obstacle for you to extend or generalize this to different geometries other than the hyperbolic or ADS. And one other thing is that it's error correction code, and of course it's something that we would like to build, that we would like to implement on near-term quantum devices and on the quantum computer. So can we use this noise as a feature to actually simulate some aspects of quantum gravity in experiments? And that would be very exciting. So as a summary, well, in the beginning I mentioned that there's things that we would like to do. We would like to gravitize quantum and extract a list of things, right, from quantum states and so on and so forth. What I can say is that we have made some progress in this direction. We are able to isolate certain things. At least we have a method of doing that for some certain cases. And on the gravity front, if you want to satisfy the linear, we're halfway there, I think, as satisfying the linearized Hamiltonian constraint. And even without that, we already see that this quantumized hints at some features of gravity, even without this explicit Einstein gravity constraint. So, but of course, looking to the future, there's a lot more work to be done, right? So if you still need time evolution and you need Lorentz invariance, you need this and that, but suppose all of these hold, then you can back out indeed linearize the Einstein's equation from a quantum system as such. So this approach, although it seems like so far it has a lot of potholes along the way, and I'm optimistic that as time progresses and we spend more time and effort on this, we can actually fill those potholes with our combined might, and perhaps eventually we'll plot a way to the horizon where there might be a theory of quantum gravity. So thank you very much.
Thank you, George, for the nice talk. Actually, I didn't tell you that how many minutes you have left, because I was aware that you are approaching the conclusion. So okay, you are right in time. So okay, of course we have time for question, and I see that Thomas is okay already. I guess you have to unmute Thomas. Okay.
Okay, there we are. Very nice talk, very nice, except that I got lost very quickly. So I have, no, very nice, very nice. And I think the question you are asking basically is very important. I think it's a very important approach, and I would like to understand better. But I have two questions. The first question is, in the beginning, you presented this graph, and then you said out of this graph, via correlations, you get a notion of near and distant, let's say. Mm-hmm. The first question is, how do you get something like a causal structure out of that? If you think of Sorkin's causal set approach, how does this compare to this one? I don't see any input of that sort. So that is the first question. The second question is more of a historical kind. Namely, in the 60s, Tom Kibble tried very hard in a number of papers to gravitize quantum theory, in particular quantum field theory, and I don't know whether you're aware of that, and I would also like to know the connections of that. I mean, it looks like two different worlds. They could not be further apart, but it would be interesting to see some connection.
Yeah, thank you very much for the very nice questions. So concerning causality, here where in fact, this one doesn't have any causal structure. Now, there are two ways of getting causal structures out of it. The first way, of course, is through, well, when you have a Hamiltonian, you can evolve it in time, and that will give you some causal structure. And the second way is actually kind of more subtle. It's through these inclusion properties. Now, what we have analyzed here are just, we're thinking about putting each individual vertex here, HI, but you can take unions of these HIs, and this inclusion property will actually induce a causal relation, and that's been studied in some of the, I think one paper by Bartek Czech and friends, where they actually can find that you can induce some sort of causal structure that's similar to the Sitter space. So as far as I know, there are two such approaches. I'm actually not, I'm only vaguely familiar to the work that's being done on gravitizing quantum field theory. My worry would be that if you already started with the quantum field theory, you have introduced way too much information. That might be the actual baggage that we don't need. But I'll be very happy to learn more about it. I think it would be nice to understand what the connections are.
Okay, then. So we have another question from Sugato.
Hi, very, very novel and interesting approach. So I understand it's just at the start, so maybe a lot to do.
But can I ask you, so if you are given not really starting with an error correcting code, I mean, already you're starting with a noisy error correcting code, but suppose a kind of random many-body state or a many-body state in some other situation, have you identified any way to identify what would be the like encoded regions, what would be like the matter, and what would be the gravity part of it to separate, filter that out?
Yeah, I think, yeah, very good question. Thank you. So I think when we have many-body systems, then it's actually easier in the sense that I have a Hamiltonian and then can take, some subspace, let's say the low energy subspace of the Hamiltonian, that some of which are error correction codes. And in that sense, I think a lot of systems would have such properties, and we can use the same line of logic because it just applies to all error correction codes, right? So we can use the same line of logic to derive matter from geometry. But the question is, do you have something that actually vaguely looks like something geometrical that looks like, I have this number of dimensions? That might be tricky. Yeah, that's my comment.
I see. Okay, thank you.
Okay, Luca, probably you can postpone your question to the discussion session.
For discussion, yes. Also because I believe that will be for more than one speaker. So
yeah. So okay, would like to thank ChunJun. Okay. Oh, you already.
Sorry.
No. Thank you.
All right. Thank you.
Thank you for the nice talk. Then we have the last speaker of this second session. Okay, I already see him, Ashmeet. Okay, you are already okay. You can.
I am here. Yes.
Yeah. So you are already close. You can.
Let me try sharing
the screen. Okay.
Let's see. All right. Can people see my screen?
Yes.
Okay. Good. All right.
Okay.
So
if you perfect.
Works.
Okay, you can go.
Thank you. So first of all, thanks again to the organizers for inviting me to this wonderful conference. I must admit I haven't been participating a lot of the last couple of days. Was pretty busy with other things. That's the downside of having a virtual conference. But I'm hoping that this confluence of people can get together sometime in person soon, and we can discuss more. So I felt that given it's the last day of the conference and people have had a lot of physics in the last 4 days, how about we talk about some fun stuff? I mean, everything has been fun, of course. Fun is a very observer-dependent statement, but we'll try and make it as Lorentz invariant here. And what I want to try and talk about is basically what aspects of gravity can we use to inform quantum mechanics? Again, coming from the same camp as ChunJun just came in the previous talk, trying to gravitize quantum mechanics, but my talk will be more about on a much further along scale in that emergent discussion. So what features of gravity can we use to inform quantum theory? And then again, what implications might that have in the universe that we kind of know and love? So what I want to kind of emphasize is that, 1 second, let me move this out of the way. 1 second. Right, okay, I'm back. So the whole idea of this talk is going to be, we're going to talk about some very basic and simple ideas in quantum mechanics and try and motivate some of them by gravity. And the style of this talk is going to be a back of the envelopes calculation style. Nothing too fancy, mostly undergrad level quantum mechanics. So that's what probably makes it fun, I think. The outline of the talk is going to be, I'm going to start talking about why finite dimensionality is going to be important for this discussion. Then I'll talk about what kind of setup is kind of aligned for the right kind of thought process for the finite dimensional construction. Then we'll go on and talk about how this construction can be relevant to the cosmological constant problem. That's where the gravity part of things comes in. And then we'll see how all of this ties together and might have implications for consequences for quantum gravity as a whole. Okay, so that's my broad roadmap. So hopefully it should be nice and fun. Okay, so finite dimensionality. Of course, quantum field theory is something that we all know and love. It is great in predicting experiments, in scattering experiments, other things. But again, it has certain features which are not very compatible with gravity. One of the most important ones, I think, is the fact that quantum field theory has a Hilbert space, which is infinite dimensional. And for various reasons that we'll just talk about. So the first thing that, of course, one can have arbitrarily long wavelength modes. you can be as low in energy as possible as you can think. Of course, you can also go arbitrarily short in momentum modes or in wavelengths, which is on the UV side of things. One might argue that I can, of course, lattice my construction, put it on a lattice where I have a box, I have a small delta X for my UV cutoff or something, and I can regularize my lattice, and I can put a UV cutoff like the Planck scale or something, maybe the Gut scale, something on those lines. And the IR size of my box could be presumably the Hubble scale for our observed horizon, things like that. But that's not all. That's not the only source of infinities in the Hilbert space. Even bosonic excitations for a bosonic quantum field theory, those are also another source of infinity. Even if I'm on the lattice and I think about a quantum harmonic oscillator at a certain, let's say, momentum mode, a bosonic degree of freedom would have states available up to infinity. I can keep acting by the creation operator, A dagger, A dagger, A dagger. I keep adding more and more energy. So there is no bound on bosonic energy excitations in a standard quantum field theory. So even on the lattice, the Hilbert space of quantum field theory is infinite dimensional. And while it works beautifully for various reasons, some aspects of it are not quite compatible with gravity. And let me tell you what. So the moment you include gravity in this setup, and you try and excite these excitations by A dagger, and you keep going up, many of them, of course, would start collapsing into black holes. And that's a highly gravitating system. And quantum field theory is, of course, not kind of compatible with gravity in that regard. So when you try and excite these excitations, you eventually hit the black hole energy, the Schwarzschild energy, you collapse. And again, we've been taught by Bekenstein, by Hawking, by black hole dynamics that the amount of entropy that a black hole can pack in its size is proportional to the area of the black hole. Area not being the relevant part here, but the fact that it is finite, that it's a finite entropy in a certain region of space. It can be applied to a de Sitter horizon that we are asymptoting to, or a certain region of space. Because if you try and add more energy to that almost made black hole, you make it a larger black hole. So your region that you started with is now a larger region. So for a given region, there is only so much you can do because the entropy counts the number of degrees of freedom. So there's only so much that you can do in the region of space before gravity kicks in a very non-trivial way. So therefore, the claim here is that it's a hypothesis, we are kind of working with this, that finite entropy in the finite region of space, because of its information informed by gravity, thus the Hilbert space of quantum gravity is locally finite dimensional, which is a stark departure from what happens in quantum field theory, where there are infinities floating everywhere from a Hilbert space point of view. So that's one major difference. Again, you might ask, hey, should I care about this? Like, what's the big deal? Infinity is just a limit of finite stuff. You keep going, you'll eventually get there. But I want to convince you that it actually matters. If it's finite or infinite, things do matter. And the reason that it can be traced to is the Stone-von-Neumann theorem. The biggest arguments to be made, I'll kind of keep it glossing over at the moment for the interest of time. But in continuum quantum field theory, of course, you have infinite degrees of freedom, one at each continuum point of space, and each point has a harmonic oscillator, colloquially speaking. Whereas quantum gravity, you expect this local region to be finite dimensional because of entropy constraints, because of gravity. And the biggest difference comes, which is more of a mathematical difference, is that the kind of Hilbert spaces that you have become either non-separable or separable. On quantum field theory, you have non-separable ones, which is basically an uncountable number of infinity of dimensions of the Hilbert space. Whereas in quantum gravity, we expect finite, which is a subset of either being countably infinite or actually finite. So that's a major difference. Now, again, why does it matter? Because it matters because depending on the dimension and the separability structure of the Hilbert space, the canonical commutation relations have vastly different representations. The Heisenberg canonical commutation of the conjugate variables phi and pi or x or p equals I, maybe with the locality understanding, those have a unique representation on separable Hilbert spaces, therefore countably infinite or finite, the more drastic case. Whereas the same canonical conjugate commutation relations have inequivalent, many different representations available in the field theory understanding. And therefore a choice has to be made of what state are you in, what algebra to choose, things like that. So there is a preferred state in the algebra that's be chosen in the continuum version. Whereas in the finite dimensionality, because the representation is unique, everything is unitarily connected to one another by simple rotations of the bases. And therefore, the algebra that you're working with is just all Hermitian operators on that region of space. So there is no preferred structure in that regard, whereas there needs to be a certain choice to be made in the quantum field theory sense. So there are like actual physical differences in these two setups. And again, I come from the camp where we are trying to emerge gravity from quantum mechanics, and therefore we are working with finite dimensional constructions that all operators, Hermitian ones, are just the algebra that you have. There's no preferred structure there. So that's the background of things here. Good. All right, I've told you finite dimensionality, why it matters. Now the big question is, what kind of constructions should you be using to play with these finite dimensional constructions? And I am putting forward that the generalized okay, let me back up for a second here. So of course, both in classical and quantum mechanics, we love using conjugate variables, position, momenta, phi and pi, things like that. And those basically form the bedrock of how we do physics very often. But the big issue is that for the Heisenberg canonical commutation relation, phi pi equals I, the commutation relationship, of course, h bar is 1, I'm a good guy. There are no finite dimensional representations of the Heisenberg canonical commutation relation. This, of course, goes back to the Sturm-Neumann theorem again. But if you want like a quick, dirty check of things, look at the commutation relation, take the trace on both sides. The trace on the left is like trace of a commutator, which is commutator cyclic. So you basically get a 0 on the left. And the right is like trace of I times the identity. And that's definitely at least not 0. So there is some inconsistency that is there in this commutation relation from a representation point of view. And again, there are no n by n matrices of the position or momentum or phi or pi, which can obey Heisenberg's canonical commutation relationship. So there needs to be some changes done in how to approach them in the finite dimensional construction. So what is the right construction? It's the generalized Pauli operators. They basically find their heart in the generalized Clifford algebra. People have, of course, seen Clifford algebras in QFT, spin or gamma matrices. It's another different algebraic version of it for different number of generators if you're interested, but we won't need that today. So the GCA, or the generalized Clifford algebra, basically gives us a way to enforce the commutation relationship given by Hermann Weyl back in the day, which is more of an exponential commutation relationship between generators of translations in conjugate directions, position, momentum, or phi or pi, let's say. So you have an exponential braiding relationship between how these operators generate translations. And in the large dimension limit, they, of course, approach the Heisenberg canonical commutation relation. So what we have is we basically have a lattice-like structure for phi and pi with cyclic conditions, so periodic boundary conditions. And these finite, these matrices can generate shifts on one or the other, like general translation generations in that regard. So there is a way to use GCAs to basically have a notion of conjugacy of translations on a finite dimensional space. How does that work out? There are unique representations, of course, after unitary rotations that can be represented of these translation operators of position and momentum, phi or pi, as simple matrices, n by n. You can go and code them on your MATLAB thing, it works. And this is the representation that we have. It's a unique representation, omega being the primitive root of unity, depending on the dimension of the Hilbert space. I'll mostly work with odd dimensions because it's easier, though everything that I say also carries over to even dimensions as well. So there's no restriction there. So we have simple n by n matrices, which can represent this finite dimensional representation of conjugate variables, which is basically a way of saying one variable generates shifts in the other variable in that regard. And for people who might see, hey, have I seen this before? You might have. This is the clock and shift matrices. For n equals 2, it's a Pauli matrices. It's sigma z and sigma x. So it's familiar stuff, and it's in a more general context of GCAs that we're talking about here. Good. What implications might this have? Of course, the canonical commutation relations change. Uncertainty principle might get some modifications. the eigenspectra, the eigenvalues of an operator would change because the underlying commutations have changed, and therefore the spectra could be different. Example, the quantum harmonic oscillator, for example. So we'll use this fact that finite dimensionality is kind of non-trivial. It leads to implications in how we understand basic constructions, and now we'll try and see what implications it might have in quantum gravity. So the question we are asking is, can intrinsic finite dimensionality of Hilbert space have implications for the quantum contribution to the vacuum energy of the universe, which is the classic cosmological constant problem. I'll kind of go through it really quickly, but the fact that the dark energy or energy in the universe, which makes it expand and accelerate, how do we compute that from a more first principle quantum perspective? And we'll try and see whether finite dimensionality can have some effect or some say in that regard. So that's the question that we're asking here. Okay, so the standard cosmological constant problem is that there is energy density in the universe. It might be sourced by 0-point energies of various modes of a quantum field theory. So let's take a simple toy example, Klein-Gordon scalar free field, put it on a lattice again. So I have a lattice of points, let's say momentum space. I have a box of size L, maybe a UV of lambda, maybe the Planck scale or something, that's all right. The crucial thing is that my phi and pi conjugate variables at each momentum mode are sourced from the Heisenberg canonical commutation relationship. This is all the infinite dimensional standard textbook story. So you take this, write down the Hamiltonian, which is just a collection of simple harmonic oscillators, one at each momentum mode. It's straightforward. And each oscillator contributes 1/2 omega. So in the right, it's like 1/2 k for the energy of that oscillator. And when you add all these ground state energies up for every momentum mode as a possible explanation for the vacuum energy in the universe, the dark energy, that it might be a connection there. What you find is that when you add all these up to the Planck scale, of course, the UV modes dominate. And you basically find that the contribution of the 0-point energies of all these modes goes up to the Planck scale. So the energy density that you compute is like Planck scale to the 4th, GeV to the 4th, which is large. And what we go and observe in the universe, depending on how fast we're accelerating and expanding, the observed value of this energy density is really, really tiny. It's basically 10 to the 120 orders of magnitude away from the prediction. It's like the worst prediction theoretical physics that we always said the CC problem to be, CC standing for cosmological constant. So I will put some exclamation points because this is, of course, a big discrepancy, and standard field theory is doing us no good. I'll, of course, also put some asterisks that this is not the full cosmological constant problem. I understand there are other contributions as well, like the bare classical value, other things, renormalization, but those are, again, not the fun part of things. We're going to keep it simple today. So what we'll try and do is we'll try and ask the question, can finite dimensionality remedy some of that, that out of proportion prediction of the vacuum energy that we have, at least the quantum contribution of it? So again, same setup, lattice scalar field theory, 1 point for each momentum mode, box size L. But now what we are making different is that the dimension of Hilbert space of each momentum mode is not infinity anymore. It's finite. It's some finite d, which could depend on what momentum mode you choose. And the conjugate field operators, phi and pi, for that momentum mode of the Klein-Gordon field, they don't satisfy the Heisenberg commutation relationship anymore. It's sourced from the generalized Clifford algebra. It has a horrible looking form, not so horrible, but again, not doesn't look good in slides. So it's not at least I times a spatial locality. So that's the prime starting difference that we have. Finite dimensional Hilbert spaces for each momentum mode, and therefore the conjugate variables are not exactly Heisenberg commutation holding. Cool. The Hamiltonian, again, is a bunch of free oscillators, all decoupled, just add them all up. But the implication being here that we have a modified spectrum of the, and by spectrum, I mean the eigenvalues of the energy eigenvalues of the Hamiltonian would be different. They would be away from the usual vanilla infinite dimensional linearly spaced n+1/2 omega type of structure of the eigenspace. So we'll try and use that deviation from infinite dimensionality and see what implications might that give us, basically. Good. So this is what we have. So again, in the interest of time and details, I'll kind of just give you the bigger results and the aspects that we have. So one could say, okay, if it's finite dimensional, the first feature is that there's a maximum energy that exists in the system. It just doesn't keep increasing indefinitely. There is a max energy which is there. One can put, I haven't been able to like find a closed form expression for this maximum energy, but we can put a very strong bound. And the bound is like a very simple linear algebraic bound called the Horn inequality, which is basically saying that if you have a matrix A, which is the sum of other two matrices, so A is equals B plus C, then the max eigenvalue of A is upper bounded by the max eigenvalue of B plus the max eigenvalue of C. That's all that this inequality says. And since my Hamiltonian has both quadratic terms, momentum square and phi square, the maximum energy eigenvalue is dominated as a quadratic in the frequency here being the capital omega. So it's a quadratic scaling maximum energy, though the first few energies would of course have to be linear to match with low energy understanding, and then it kind of goes quadratic and has a quadratic form there. Okay, so far only quantum mechanics. I promised you some gravity, again, some semblance of gravity. So how about we put a no black hole condition? Because infinite dimensionality, our main issue was if you keep exciting things up, you eventually collapse into a black hole. How about I impose a condition as a 0th order back of the envelope calculation that were I to ask and demand that my highest excitation energy of any given harmonic oscillator K mode doesn't collapse the universe into a black hole. It's a very loose bound. It's a very loose 0th order kind of connection, but hey, let's go for it and see what we get out of it. So we're having a no black hole condition that the maximum eigenvalue of each momentum mode doesn't collapse the universe into a black hole. So the max energy eigenvalue is less than the Schwarzschild energy of the Hubble box that we live in right now. And that's the black hole bound that I have here. So just by looking at this, we can already tell that there is a dimension profile that we can kind of get, that the dimension of the Hilbert space of each momentum mode scales inversely with the square of the frequency of the harmonic oscillator. And there's this energy dependent Hilbert space dimension profile of each momentum mode. And as expected, higher momenta because they have more energy, they have lower dimension because for less excitations, you hit the black hole bound. So that kind of makes sense here. So we have this profile, again, loose profile, 0th order, but this is again fun stuff. So we play along. Okay, let's take a step back and quickly talk about what if I had one quantum harmonic oscillator? Here I had a whole bunch of them. How about I just had one? Textbook first quantum mechanical course. Usually the spectrum is n+12 omega, linearly spaced. But now what happens is, and the ground state energy in the infinite dimensional is like 1/2 omega, 0 point energy. But now of a single harmonic oscillator, the 0 point energy depends both on the frequency and the dimension of the Hilbert space. So they both play a role now. And again, if you go large enough in dimension, you eventually, of course, saturate to the 1/2 omega or the vanilla infinite dimensional contribution. So again, I'll not give you formulae here, give you a plot of how it looks like. So as you can see, this is a plot of the dimension of Hilbert space along the x-axis. On the y, it's normalized 0 point energy with the frequency. So if it were infinite dimensional, it would just be 1/2 all the time, like 1/2 basically. But now for different frequencies and different dimensions, I get interesting profiles. That is here. One thing to notice as a feature of this finite dimensional construction is that if I have a high frequency and a lower dimension, the 0 point energy is suppressed. So again, look at the bottom left part of the plot. High frequency, lower dimension, there is less 0 point energy. And la-di-da, what did we have? Our profile was the dimension was scaling some kind of an inverse relationship with the frequency. So from the no black hole bound, a high frequency got a low dimension. And just by the quantum mechanics of a single oscillator for each oscillator, if you have a high frequency and a low dimension, you are suppressing the 0 point energy. So that looks promising. And again, this work is also in collaboration with ChunJun, who just gave this talk before. So that's the paper up there if you want to have a look. We can work out the math, again, back of the envelope style. I won't get into the details, but what do you get? The conventional textbook that we just discussed, quantum field theoretic contribution, infinite dimensional stuff, the Klein-Gordon contribution is Planck scale to the 4th. Of course, the observed value is super, super tiny, the big discrepancy that we had. But now what if we compute it with a finite dimensional construction? So we're adding all these 0-point energies from each of these modes informed by gravity, each mode having Hilbert space dimension informed by the frequency, what we just discussed. And what we find is that there is a massive suppression in the 0-point energy because of what we just discussed. And just by this simple 0th order bound loose bound that we had, we can get it down to a 10 to the 4 to the 4th GeV to the 4th. So on a log scale, we solved the problem halfway. We suppressed it 60 orders of magnitude in the right direction because of a very simple finite dimensional construction. And again, one might ask, what else can we do about this? So this is promising in a certain regard. Currently, of course, I had volume scaling of my degrees of freedom. I need to be holographically consistent to make it area scaling. Large excitations can't be excited everywhere because holography might not let you do that. But again, the key takeaway being that just by looking at basic constructions in quantum mechanics informed by gravity, there can be predictive consequences for quantum gravity or cosmology. And this can also leak into corrections into Feynman diagrams, the Casimir effect, uncertainty principles, because you're changing the commutation relationship essentially. So that's what one can do essentially with this construction that I plan to later down the road. So in hindsight, what have I shown you? That there's massive suppression of the quantum contribution of the vacuum energy. And this could have implications for quantum gravity in the universe, possibly. This was all volume scaling. There was no holography really there. So that needs to be made consistent. Again, I confess this is not the entire cosmological constant problem. There is a bare classical value to also be, that one can tune. But again, if you're able to suppress the quantum contribution, you might not need to fine tune anything if required. So that's at least one positive outlook. And this can lead to corrections in Feynman diagrams and uncertainty principle, things like that. So that's also work to be done. The takeaway, local finite dimensionality again can have consequences. And again, in this talk, I showed you how it can work for a cosmological setting where you have the vacuum energy of the universe. So that's from my side. I'm happy to take questions. And again, thank you for your time.
Okay, thank you, Ashmeet, for your interesting talk. And okay, we have time for questions. There was Luca, who raised his hand during the talk. So Thomas, just a second, because Luca already raised his hand previously. So you will ask first.
Okay. Don't worry. I will do just one question and one I leave for the discussion. I try to do the fastest one. So very beautiful talk. Anyway, the first question I wanted to ask you is, okay, you try to do some finite dimensional version of a scalar field theory. But I feel that in the case of fermions, you should have much better behavior in some sense. Also that the form commutation relations, you say, I think, because for fermions, you have much more natural construction of a finite dimensional Hilbert space. And you need finite number of energy levels available, and then a Pauli principle do for you, actually. That's for you.
Right. I think I agree with that. And you're right. If you have a fermionic construction, of course, you have finite dimensionality right from the start because states can only be finite because of the statistical physics part of things. And again, I feel that the same generalized Clifford algebra with the right commutation relationships with the right number of generators can be used to describe even fermions. And one good thing I like about this construction, the GCA algebra part of things, is that the GCA, as I mentioned, for n equals 2 is the gamma matrix, the Pauli matrices. So it's just spin half particles. If you have electrons in quantum field theory with 4 generators, GCA gives you the spin or gamma matrices. So the same algebra gives both the spin structure and can also give you the more spatial momentum structure in the right kind of limit. So I think this can also be a good starting point of thinking about like a unification between different algebras in terms of fermions and bosons that might work here. So I agree with that, yeah. I haven't worked out the details yet about fermions, but definitely worth looking into, I agree.
Next question during the discussion. I passed it to Thomas.
Okay, so Thomas.
Okay, we can also postpone to the discussion, but in any case, I have first a question to understanding. You said you start with the idea that you want to have a finite dimensional Hilbert space for a local region of space-time. I understand it in this way, that here you assume a kind of background space-time, because otherwise what is local will be also affected by this finite dimension assumption. I mean, what is local depends how you measure it. If all the Hilbert spaces are finite dimensional, what is local will also be changed. So this is one question. The other question is, I was surprised to see when you showed this matrix representation of this momentum operator, finite dimensional matrix representation, it's exactly the permutation operator about which I made a lot of fuss on Monday. So it's kind of interesting to me. And I think I will look up your paper, what in particular, there was the momentum operator, but the conjugate operator had this omega. And my question was, just because it was too quick, what is the omega there, because it passed me by.
Right. Okay. So let me go chronologically here. So for the first question, I am totally on board with the assessment that depending on how what dimensions you have, the notion of locality would be different. And again, right now we don't have a full prescription of going from just the Hilbert space onto a region of space and then kind of make the connection between what the dimension is and what locality really means. But again, my motivation here being that if gravity is emerging from quantum mechanics, then there's got to be an association of a region into the fundamental theory, which will have a finite dimensional factor to it. What emergence map that is again, it's unclear to me, and definitely remains an open, interesting question. And it would depend. But again, my key takeaway here was, if you take that hint seriously, what implications can that drive from like a reverse point of view, by kind of taking that fundamental thing and applying it to the most emergent level and seeing what that might say? What that map is, I agree, it's an interesting question to ask. On the second point about the momentum operator, I'm not sure what the question was, but the omega, at least the little omega in these slides that I had, was defined as the primitive root of unity. It's e to the, 1 second. My bad. Yeah. So it's basically just the primitive root of unity, and that's how you define it. But again, maybe I missed the question that you were asking here, Thomas.
Okay. No, that's fine. Thank you. I will look it up in your paper.
So, yeah, so I think this paper that I link in this slide here, that's probably a better paper to look for these constructions, because the one with the finite dimensional suppression is just focusing on the vacuum energy.
I was just referring to the first operator. This matrix is exactly the permutation operator on which I base all my arguments on Monday.
Arguments in favor or against?
Come?
I said arguments in favor of something or against something?
No, it's a completely different subject, but it's nice to see the same structure appearing.
I was surprised that this kind of clock shift matrices are basically very ubiquitous than I initially thought they were.
This is a permutation matrix, that's what it is.
Yeah, exactly. So yeah, good to see their applications elsewhere. Thank you.
Okay, I saw previously that Sugato raised his hand, but I don't know if, okay, yes.
Hi. Very nice talk. I was wondering. You have taken the SU capital N group, and then you bounded that with L square, the region's area, the dimension. But the SU, if you take the SU2 group and take to a very high dimensional representation, then locally you get the Heisenberg algebra. If you So have you tried that way, or is it sensible to try that way at all? Or
that thought has crossed my mind, the Heisenberg representations in that regard. I must confess I have not played with that in a lot of detail yet, but definitely this whole business of what the algebra has to offer, what different representations tell you, it's one of my interests at the moment, but I would not have a more concrete thing to respond to. I haven't tried it right now, but I agree with that.
Thank you.
Okay, so I guess that we are perfectly in time to start the discussion session. So first of all, I would like to thank Ashmeet again. Okay, so I guess that okay, first, there was Lorenzo, the question for Jorge, but privately told me that he had to leave. So I don't know, he didn't even leave the question to me, but it's quite unfortunate. I'm sorry for that. But then we had another question from Luca, which actually said it was a general question. Luca?
Yeah, also, if I'm in this moment, I'm more in mind the second question to Ashmeet was say. And I think it's longer question for this reason I wanted to do during the discussion. And it's okay, it's a you presented the Stone von Neumann theorem, the validity in this case of Stone von Neumann theorem as an advantage of your story. And you know, I like very much all this construction and so on, but I'm not. I don't completely agree. It's a real advantage because there's a problem which is related to a description of phase transitions. I will say, which is very natural in quantum field theory, exactly because of Stone von Neumann theorem. A violation of Stone von Neumann theorem, for example, this is easily seen in thermofield dynamics, where you describe a vacuum state at different temperatures. You see, so vacuum that can be related to different phases, like ferromagnetic or non-ferromagnetic phases, are unitarily inequivalent because are related by an improper Bogoliubov transformation in that case. And in that case, this is an advantage because you have two different, completely different descriptions. You have ferromagnets and normal metal, ferromagnetic state, for example. And there are plenty of this kind of examples, superconducting phase or normal phase and so on. The vacuums still are related by Bogoliubov transformation, which is improper canonical transformation, and this guarantee that you have really different phases and so on. So the problem in this kind of cases is really description of phase transitions. I have some kind of answers I worked recently, but I wanted to know your opinion on this.
Sure. I think that's a very good point. And I can maybe add to that list of problems here, and then maybe we can try and see what the solution might be. But like another problem is that if you have finite dimensionality intrinsic to your construction, then Lorentz invariants would never be exact. There are no representations of the Lorentz group or the Poincare group on finite dimensional spaces either. So one might say there are Lorentz violations probably because of this. My take, at least, where I stand is that even though the fundamental construction might be finite because of this gravitational entropy bounds, there might be an emergent phenomena whereby you can restore the symmetries that you're looking for at an emergent level. So they might not exist at the more fundamental level, but once you have the right emergent of space and matter fields and gravity, at that level you can like restore those symmetries, even at diffeomorphism invariance. Finite dimensionality would not let you do that. You might have to pick a gauge to work with all of this stuff. But again, once you have a space-time and matter, at that level, I could imagine restoring the symmetry. And to your question, at that emergent level, that might look like as there are these emergent phenomena like superconductivity or phase transitions, they might have this choice to be made of what's vacuum, of what representation to choose or what transformation to look at. And I think something interesting to actually kind of study in detail, which I think it's definitely worth having a sense. What are your thoughts?
So your point of view is that there are probably just like unstable phases, and eventually you are not really phase transitions or something like that. Superconducting phase is very stable because you have many degrees of freedom, but in principle will decay in a normal phase and normal vacuum.
Right. I think that's what I'm trying to get at. That probably it's these phenomena are more at the emergent level as a description, and they may not have a parallel one-to-one mapping at the fundamental Hilbert space level or not. So that's something to be explored, I think.
Because I recently worked actually on this problem, and I think there is actually just one alternative, I would say, that you can see in a different way. Okay, clearly, it could be what you were saying. You have emergent description, and this is just some kind of approximation. The fact that you have many phases is some kind of approximation. So the two aqua are not really orthogonal, but you can always have some decay from one vacuum to another, some tunneling or something like that. In other words, you never have really spontaneous symmetry breaking, but you can always have some tunneling from one vacuum to another. Very, very slow, depends on the number of degrees of freedom. There's a possibility. Another possibility is that you look at topological inequivalence. That's another way of avoiding Stone von Neumann theorem. This is long time known from the classical example of quantizing a particle moving on a circle. In that case, you have inequivalent, you have many inequivalent Hilbert spaces corresponding to different Weinstein numbers. And in that case, the reason is that one of the hypotheses of the Stone von Neumann theorem you probably mentioned is that you have a regular representation of the Weil-Heisenberg algebra. And in that case, you lose regularity because the parameters of the group are discrete. And there's also the case, for example, was widely studied in the last 20 years, this polymer quantum mechanics in the loop quantum gravity community. And in that case, still you lose regularity, but it's essentially because also there is like you have standard quantum mechanics, but with discrete topology. So it's always a matter of topology. Also in that case, you manage to construct inequivalent quantization in quantum mechanics, which is inequivalent to Schrödinger quantization. So another possible point of view is that your phase is stable because of topology, not just an approximate stability.
Interesting. Yeah, I think I'll have to look into the references that you mentioned. We should probably, we'll chat on offline about this, but
I will send you an email with.
Oh, that would be good.
Doesn't work. I did on this.
The topology business. Excellent. Yeah. Thank you.
Okay. Then we have a question from Thomas.
You hear me? Okay, I have another, just a general question to ChunJun again, because I'm very interested in this approach. I think it's a very fascinating question. And also there have been some works in this direction, maybe I don't remember very precisely, but maybe some 15 years ago or so by Lee Smolin, Fontini Marcopolo and collaborators, the other names I forgot. And they also tried to extract from the correlations in quantum states some geometric structure, let's say. And it didn't go very far. I mean, there was a handful of papers, but it didn't go very far. So therefore, I want to ask you, what is the guiding principle? I mean, if I give you a set of quantum states of some unknown system or something, what is the guiding principle by which you hope to extract geometry or even more? Because that I think I didn't get this in your talk, and that's why I got lost very quickly in the quantum information business. I mean, then, okay.
Yeah, thank you for the very nice questions. In fact, I brushed over that part intentionally because it's a whole can of worms that I didn't have time to mention. But the reason we succeeded is because we cheated by restricting ourselves to a particular set of quantum states, namely that these quantum states have, well, if you translate it into the condensed matter literature, right, these are the quantum states that have area law entanglement. Basically, their entanglement is is relatively localized in the sense that you can express them with a single graph. Whereas if you have volumetric, like some hard random state, then in that case, we don't know, in fact, how to deal with it. So that is the first restriction. And the second is so once you have a graph, I think there's a separate question, what kind of graph is more geometric than others. That is less clear to me. I would like to find out more. I think people here probably know a lot more than I do. Like we spend a lot of time on this question, so I'm hoping that perhaps there will be some combined wisdom come and transpire out of this thing.
Okay, very good.
Okay, next question is from Ali. Ali, you can unmute yourself.
Do you hear me?
Yeah.
I have a question to ChunJun Sao. How can background independency be obtained and guaranteed in emergent geometry scenarios arising from matter entanglement?
How can background independence arise from this emergent property?
If you're not understood, I can repeat it.
Yeah, yes, please, go ahead.
How can background independency be obtained and guaranteed in emergent geometry scenarios arising from matter entanglement?
I'd like to think that this whole thing is background independent, right? Because the whole thing is, it really had no background. The background is something that you derive from these correlations. So I think I'm not sure. I guess we can be more precise about what you mean by background independence in this sense.
For example, general covariance in the general relativity of Einstein. It's something that guarantees the background independence of the theory. Also, the background independency is much more general concept than general covariance. But for example, loop quantum gravity. Loop quantum gravity guarantee the background independency. I have a question about emergent geometry rising from matter entanglement. How can it be background independent?
Well, if you're talking about a theory being background independent, I think it really depends on what the theory is. So right now we don't have a theory of anything, right? We were just analyzing one piece of quantum state from the information from the quantum state. So I think that the background, if I understood you correctly, the background independence is something that's characteristic of the theory, and that is related to the part that we did not talk about in the talk. So I don't have an answer at this point for that.
So if you use quantum mechanics, your theory is not background independent.
Well, if I use quantum mechanics, there is no notion of a background in this sense, right? It's what I had in mind is like I have a Hamiltonian operator that's basically a set of numbers, right? It's a spectrum that you're given the spectrum of some Hermitian operator, and that is the sense, the kind of information we're looking at here. I really don't think, at least right now, I don't have a very concrete idea how you would say anything about the background in the first place, let alone background independence.
For example, quantum mechanics preferred inertial frames. This preference is not background independent.
But I think that's because we worked out something into the Hilbert space to begin with. If you just have a matrix that's rotating a vector in Hilbert space, there is no sense in which I have inertial frames. There's no sense in which I have, some sort of locally Lorentz symmetries. So I don't think at least as of this point, it's unclear. I would say perhaps that's the most conservative answer to your question.
And one more question. And I took a look at your papers and saw several papers on this matter that you presented. Each of one is a review of all. I want one for reading without prerequisite of others.
I can send you the link in the private chat if I think that maybe that works better. Yeah.
It would be nice of you.
Yeah, thank you for the questions.
Okay. So next question is from Sugata.
Hi. So again, I fully understand that this is probably in very initial stages. The question is for ChunJun primarily. So, and you said that dynamics you have, have you started to look at that? So my main question would be, say you have a encoded thing as mass and the physical qubits as the curvature, and you bring in another mass which should now be affected by the curvature. Is that so like the encoded region of the qubit moves? Is that kind of thing possible to do within your picture?
Yeah, that's the thing that I'm hoping to do. Because one thing I didn't mention was that a lot of these are sort of rooted from. It has a more concrete implementation in this context of ADS-CFT correspondence. And there, I think it may be possible if we just take some chaotic spin chain Hamiltonian, tune it to criticality or near criticality, and use that as a substitute for the CFT Hamiltonian, and then you evolve that in the lab, perhaps. And it, but of course, the trick is that you have to choose a Hamiltonian that has this kind of error correction code picture, and then there, it is possible to actually reconstruct the metric tensors very explicitly for each time slice. So if you're able to take a picture of each time slice, you can figure out how how the geometry changes in at least in this particular gauge, right? So perhaps you will be able to figure out how masses like interact. That would be very nice to see. For instance, I think if you inject some perturbation into the spin chain that's localized, you let it evolve essentially, and then you can see that from this entanglement entropies that if the spin chain is chaotic, all of these things will eventually delocalize. But if you reconstruct the geometry, it actually looks like a blob of things that's concentrated at the bulk, and it's very kind of telling, saying that a black hole or something formed and it's gravitate, or it's just. Whereas if you have integrable spin chain, it's just bounce back and forth. There's no like gravitation.
So what you're hoping is that this center of the localized the structure will kind of move as a result of the spin chain. Okay, that's interesting. Yeah. But one more thing, you see, so it's slightly more demanding than getting just the classical equations of motion, because if a mass is moving, you have to show that it moves according to e to the power is by h bar. So it's not just the Newtonian or the you have to show that its amplitude to go from one place to another place should be this kind of e to the power is by h bar. Is that I mean, where will that quantum mechanics come in? That action? Okay, I guess it's for the spin chain to move from one configuration to another.
Right.
Okay.
But beyond that, it's a very, very interesting question, though. But beyond that, I have to think more about that.
And does it make sense to think of, well, I mean, what would gravitons be in your picture, like independent gravitational excitations without any encoded mass being carried with it?
I think it really depends on the sort of ambiguity of choosing a co-subspace, because how you choose the co-subspace is completely arbitrary. So that is sort of, you can choose your co-subspace to be smaller, then in which case you don't have any graviton interactions. Then you just, I tune out these. But if you choose your co-subspace to be a little larger and then skewed in a certain way, you can still include graviton in your sort of matter subspace. But yeah, that part is a lot fuzzier, which is something that we would like to understand.
Okay. And maybe a question for, Ashmeet in some sense, but it's relating whether his aspect relates to ChunJun. So Ashmeet, you said that you are in the same camp as ChunJun, but of course your thing, as someone else asked, was in kind of real space. You were localizing the dimension according to the area of the like through Bekenstein's. So your dimensions would now be emergent, something like that?
That's correct. When I said I'm in the same camp that had both sociological and physics connotations, we were in the same PhD group, so we did.
Right, the social, okay, now that's different.
Yeah. The other more physics aspect is that you're right. The number of, what Thomas mentioned, what would correspond to a local region of space, the dimension of the spatial space that you would have, those would have to be emergent in like the way ChunJun described. That would have to be an emergent perspective. My goal was more like, if you take those hints seriously, what can you say about the most emergent level of things? But it would have to be compatible and rather derived from this gravitizing quantum mechanics picture. So that's correct.
So I guess this is I have heard in places that it's probably an open question what I'm asking you now. So your qubits in your different qubits will have entanglement, right? This is entanglement in the bulk in some sense, and then in ChunJun's picture, what would correspond to entanglement between two emergent objects? This I don't know, but maybe this is a question which people say is an open question.
So you mean like identifying the entanglement structure?
So you will have entanglement in your physical space where you're talking about qubits are really locally there. They would be entangled, right? Yeah. And on the other hand, those are themselves kind of logical. So I guess maybe it is entanglement between logical qubits, which is. What you're talking about physical space. Okay.
Yes.
Okay.
That's correct. Yeah.
That's wow. Okay. Okay. That's interesting. Okay. Okay. I'll sign off now. Yeah.
So thank you. Yeah, this is good.
Okay. Thank you, Giuseppe. Next question is from Eva.
Hi. My question is for Jorge. It is a little bit basic, maybe historical question also. So I was wondering, how did you originally get this most general black hole solution in 3 dimensions? Did you apply the transformation and killing vector, this in SO22, then you knew what you expect in 3 dimensions and then determined the metric from killing equations? Or did you, or how did you know these transformations from the embedding? Where do they come from?
Jorge, you have to unmute. Oh, just a second. Okay.
Okay, thank you. Thank you very much. It's an interesting question, but of course the history is completely upside down. I mean, the way we found the solution was not because we knew that there was an embedding in anti-de Sitter space that produced a solution. It was rather indirect. We found a family of solution of black holes in anti-de Sitter spaces for any dimension, for D, arbitrary D. And we tried the formula it started with D equals 4, 5, 6, but then we realized that also for D equals 3, there was a solution. So it was a shock and we were surprised. We didn't expect this because we had heard that there were no black holes in 2+1 dimensions. But then we realized that the only reason there is a black hole in 2+1 dimensions is because the cosmological constant provides you a scale for the radius. And so that was the way we found the solution. Then looking at the solution, we understood that it had to be a constant curvature manifold. And the only way to make a constant curvature manifold, which is non-trivial and has a singularity, is that if you take that manifold and make an identification of some kind. So we looked for identifications afterwards, and we identified which was the killing vector that produced that. And also we looked at all the other killing vectors that produce all the other possible solutions, and then we made a classification. But this was afterwards. I mean, it was not originally thought that way.
I meant, how would I pedagogically understood it if I didn't go through a historical approach? If I knew this classification now and killing vectors, how would I find how to go through from this SO2 to embedding for all the regions 1, 2, 3 that I need exactly the transformations that you have? How would where would I get them from if I didn't know historical background?
Well, it's the only way I know is that if you look at the, if you put your solution, let's say the anti-de Sitter solution, in and you, the only requirement is that it's locally anti-de Sitter, so you know that the curvature has to be constant. Then you look for the most general spherically symmetric metric that solves that equation and is stationary. And then you see that the equations tell you that there are 2 integration constants. And those 2 integration constants correspond essentially to mass and angular momentum. So it's essentially solving in a straightforward manner the Einstein-Hilbert equation with cosmological constant, that it's going to give you those solutions. So it's just a matter of naive, I mean, doing exactly what you do for the Schwarzschild solution in 3+1. You just write the most general form of the metric in 2+1 and require that it has a constant curvature, and then out comes the solution, the black hole.
I see. So there is all this embedding story comes once I know the solution.
Yes.
I see. Okay. Yeah. And then, for example, for extremal black hole, the story is the same. Also, I know the transformation from the SO2 to 3 dimensions after I already know what I'm looking for.
Sure. Actually, we wrote a longer paper with Max Bañados, Marc Henault, and Claudio Teitelboim, where we did this classification of all possible solutions in 2+1 dimensions. And we identified the different cases that correspond to black holes or other singularities. And actually, we are now working on a different paper and a different project, trying to understand all the geodesics in those geometries. And we will have more information about the identification and the killing vectors in that case.
I see. And for example, for extremal black hole, this is actually the paper that I'm referring to. For extremal black hole, can I go from using the transformation for the BTZ from SO2 to 3 dimensions just by taking mass and angular momentum to certain values? Because you have in one part statement that this is some different transformation, and then you give the transformation from Poincare patch only.
Yes. No, you see, the problem is the following. In the metric representation of the solution, you can continuously change the values of M and J and sort of cover the whole plane. But the identifications that are necessary to go to one of each of these things are disconnected. So you cannot continuously change the parameters in the identification for the black hole to get the identification for the extremal black hole, or to get from the conical singularity to conical singularity to extremal conical singularity. Those are independent transformations because they correspond to different eigenvalues, possible eigenvalues of the matrix that you used for the identification. So In the metric representation, it's a continuum, but in the identification parameter space, they're discrete sectors. They're disconnected sectors.
Okay, thanks.
You're welcome.
Okay. Next question from Peter. Just a second. Okay. Peter, you can talk.
So I'd like to comment on Clifford algebra. In the geometric.
We cannot hear.
No. Now probably it was getting better before you stopped.
Can you start once more?
Okay, I'm starting again. Hello.
Yeah, because the volume is quite low. Probably, I don't know. You're far from the microphone, or.
Okay, I'm looking for it.
Okay, but I guess that you can talk even if you are a bit closer to the computer. So probably we can hear you better.
Okay, I'm seeking to increase. Okay, increase the volume here. One more moment, please.
No. Okay, I guess now it's okay. It's okay.
It's okay now?
Yes.
Okay, I'm going ahead. So two things that seem to recur in this discussion are background independence and emergence. The Clifford algebra is naturally background independent. If you look at it in the geometric representation, you can get an intuitive sense of that because one of the primary users of geometric representation is the video game community. It's a first-person view of the world. In one person with nothing else there, it's background independent. If you add a second thing, then there's a two-body interaction. If you add a third thing, then you've added a background. So the Clifford algebra and the geometric product, which is how we model interactions in the Clifford product, which is how we model interactions in quantum mechanics. In the geometric representation, then there's just those two things there. There's just two wave functions. The third thing isn't there. The third thing then is emergence. And in the emergence, when we concern ourselves with Lorentz invariance, then you have to keep in mind that's that third thing. The Lorentz transform is just the Pythagorean theorem. It's just a three-body problem. So a fundamental theory, if you really want to work at the level of a fundamental theory, I think you need to work with Clifford algebra in the geometric representation is very helpful for doing that. The geometric representation for the vacuum wave function is simple. It's just the point scalar, three one-dimensional objects, which are vectors, and three two-dimensional objects, three of them because there's three orientational degrees of freedom, and a volume element. And so then you can use the Clifford product to take to model an interaction, and you get something that's six-dimensional. You started with 3 dimensions and you have 6 dimensions. 3 dimensions are space and 3 dimensions are phase. And you can quantize that. You can add quantum fields to that, but I think I've said enough. I'll stop here. Thank you.
Okay. Thank you, Peter, for this comment. If any of the speaker or anyone wants to add something, feel free to do it. Okay. Otherwise, okay. No, I guess, yeah.
I have one thing.
Yeah.
To confirm.
Yeah. Please, you can go.
You basically mean like is this like a certain representation you are referring to, or is this more like a general property of the algebra? I didn't catch that point completely.
Well, it is a general property of the algebra. I think the people who do geometric algebra, there's a claim in that community that the original intent of Clifford was geometric, multiplying geometric objects together. You multiply two lines and you get an area and a point. Right. So if you add quantized fields to those geometric objects, then you can generate an S matrix by.
Interesting. Yeah, I'll check this out. This sounds interesting. Yeah, thank you.
Yeah.
Okay, we have also now another question from Pablo. Okay.
Hello?
Hi, Pablo.
Can you hear me?
Yeah, we can hear you.
Hi. My question is for Jorge. Well, hi, Jorge.
Hello.
Hello, very nice talk. My question is about the mass zero black hole. My question is if still there are corrections, quantum corrections to the horizon, even in suppose that in the mass zero black hole, the classical horizon is like in R equals 0, right?
Right.
So you still have quantum corrections in that case?
Yes. Actually, in that case, what happens is that you move slightly above from there.
Mm-hmm.
And there's a finite displacement of your position in this plane. So there is a small horizon that appears, and it's of the order of h bar to the 1/3. So it's an important change, because if h bar is very small, h bar to 1/3 is very large compared to everything else. So there is a finite correction in that case also. Yes.
Okay.
So because
yes,
well, we didn't know what to expect. We thought that maybe if you have a zero mass black hole, the quantum correction would produce a naked singularity. So you would go down instead. You could go up.
Yes, this is one of my question, because zero black hole is just in the limit, let's say. Somehow.
Yeah, in the boundary in two cases. Yes.
Okay, yes. Thank you.
Okay. Is there any other question? Any other comment? Any other observation? Okay. If not, I would like to ask Jorge just a quick curiosity, actually, because you said that in 2+1 dimensions, actually, there's no need. We have no need to quantize the gravitational field, so we can only consider the quantum. The quantum is coming from matter fields and see how they can help to dress the naked singularity. But if instead, suppose that we have to go in 3+1 dimensions. Okay, in 3+1 dimension, probably something similar can also happen with standard quantum field theory in curved space-time. Probably it's a matter of computation and something like that. But if in 3+1 dimensions now we consider that there are some, at least hypothetically, some models also predict a regularization of the naked singularities, then this kind of treatment from a quantum field theoretical point of view in curved space-time then becomes somehow effective, or I don't know if it can change somehow if there is this regularization of the singularities.
Yeah, well, in 3+1, you have to be careful about the type of singularity you're dealing with, because if you take the black hole, the Schwarzschild black hole, and just change the sign of the mass, what happens is that you have a singularity that is a very terrible singularity. It blows up as r to the 1 minus 6 or something. So the curvature is not constant. It blows up as you approach the singularity. And that makes the possibility of writing down a propagator impossible. You cannot do quantum mechanics, so you cannot write the propagator in that case. That's a very bad singularity. If you have another type of singularity, like a delta singularity, like the one I was discussing in the conical case, then you could write down the propagator, and you could make the calculation of the renormalized stress energy tensor contribution to the Einstein's equations. So it all depends on what kind of setting you are. So in this second case, you could do the calculation, and my feeling is that you're going to get the same effect, that the naked singularity will become surrounded by something, or a small horizon, so there will be some sort of small tiny black hole forming there, or it may be smoothing out the singularity. So instead of a cone, you have something rounded shape thing. but we haven't made the calculation. We were trying to do this for the cosmic string. A cosmic string is a singularity that has a conical defect on the string. So there might be a possibility there that a similar calculation can be performed, but we haven't been able to do that because computation is much more harder than in the case of 2 plus 1.
Yes.
Thank you.
Okay, thank you. Okay, there was another observation from Peter.
Yes, so can you hear me?
Yes.
Good, okay. So responding to your comment, Jorge, I hope I'm pronouncing your name right. Bjorken and Drell, I think on page 384, he outlines his interpretation of Feynman parameters, the Feynman parameters of regularization. And he interprets them as quantized conductances. And at the time that he did that, and I think you can look in Bjorken and Drell and see, he claimed that this would be a great intuitive advantage, that we could make fast progress in quantum field theory. But the problem is that he interpreted it as a conductance when it's an impedance. He inverted it, and it's because of a topological inversion that the units of mechanical impedance, which is what Feynman was working with in the regularization, are kilograms per second, and more kilograms per second doesn't mean more flow, it means less flow. So there's this topological inversion that's built into the SI system of units that goes below the horizon most of the time. We don't think about it. So the point is, though, that this impedance that Bjorken was working with, it becomes infinite at the singularity. The singularity has an infinite inductance and a zero capacitance. You can't impedance match to it, so you're protected right away. You can't get energy into it, and it can't get energy out to you. So how you can incorporate that into the work you're doing in terms of understanding what's going with the singularity. If you put the impedances in, if you put those Feynman parameters in, you can put them in directly instead of putting them in during the process of renormalization. And then you don't need to renormalize. They're just the quantized impedances. If you take the geometric wave function that I was mentioning earlier, and you take the 4 fundamental constants that define the coupling constant, the fine structure constant, combinations of those constants give you quantized fields for all 8 components of the geometric wave functions. And then you've got QED extended from the Dirac equation of a scalar and a bivector, a charge and a magnetic moment, to the full 8 components of the vacuum wave function. And that works. You can calculate with it, and you can understand aspects of the unstable particle spectrum.
That's fascinating. Thank you very much. I was not aware of this interpretation, and in fact, it's a very beautiful idea. But I don't know how it fits in our work. We did something very, very elementary. We just calculated the propagator of that operator in that geometry, and out comes this renormalized stress energy tensor. We didn't have to regularize anything because
you said it's 6th power to the 6th power.
Oh, that's in the Schwarzschild case in 3 plus 1 dimension. It's 1 over r to the 6th, the singularity there, the curvature singularity at the origin. Right. But that's beyond the scope of our work. I mean, we could not do that. But maybe using the idea of this impedance, maybe you might get something out of it. That's a good thing. Thank you.
Okay. So sorry, but we have to be quicker. Just some small break between the second and the third session. So there will be one last question from Thomas. Just a second, Thomas. Okay.
Can you hear me? Yes. Okay, that's, I think, is one of, for me, is one of the biggest difficulties with online meetings, is that you never have enough time to figure out your questions, then the people already disappeared. In any case, so you cannot come back the next day and ask the question if you thought over it. In any case, I have another question to Ashmeet. Namely, when you started motivating your finite dimensional Hilbert space, you invoked the three cutoffs, I mean, ultraviolet, infrared, and on the occupation number of bosonic modes. And the ultraviolet alone, for example, would suffice to invoke band-limited functions. That means functions which have a finite extent over Fourier space. And that's just another way of saying that you have a finite length in your problem. So I was wondering how much or to what extent what you presented could be matched to the many talks we heard about in this conference about the modified uncertainty principle and so on and so forth. I mean, that to me is not obvious, but I think there is a connection.
I agree. There's a very strong connection between generalized uncertainty principles with what I showed today. I think this approach, so standard GUP expressions often have parameterizations based on minimal length constructions. They would often go momentum squared with some prefactor along with it. I think what this can help us do is, once we have the right understanding of the emergence features between Hilbert space and normal space, this can help us kind of constrain the prefactors of the parameters of the GUPs based on the dimension of the Hilbert space. I think that can be done. So you can actually have corrections to the Heisenberg commutation relationship based on this directly dependent on the dimension of the Hilbert space. And that might be a more fundamental way to kind of look at the GUPs from the Hilbert space perspective. And that's something I think is definitely worth trying. I tried it once last year. I didn't get very far. There were issues with like unregularized sums and things like that. So I don't have a full answer to it, but it's definitely on my radar. And also at that point, once you figure those things out, one can very easily find connections to Feynman diagrams and things like that based on the dimension of the Hilbert space, rather than like a parameterization in the GUP. So there should be a very strong connection. I agree with that.
Okay, then. So I guess that you can say that it's the end of the second session. I would like to thank again Jorge, ChunJun, and Ashmeet for the nice talks and the nice discussions. And so I guess we can have a 10-minute break. Correct me if I'm wrong, but I guess that we have 10-minute break. 10 minutes break, and I will leave the chair to Luca.
Almost 10, yes.
Yeah, something like that. And okay, I leave the rest to you, Luca.
Thank you.
Thank you, everyone.
And thanks to all speakers. I just want to remind to everyone that last discussion session, after contribution of the speaker of the first session, is devoted to all speakers of the day. So you are all warmly recommended to participate if you want, or if you can today.
I'm here.
Ok.
Sono qua.
Ciao Carlo. Allora, no, non so cosa... Ah, ecco qua, ecco Luca. No, no.
Ci sono.
No, non sentivo nessuno, quindi...
Ci sono.
Buonasera.
Ok.
Allora, vediamo di impostare tutto.
Metto già lo schermo, cosa, o no?
Sì,
Metto già...
sì. Sei già host, quindi puoi condividere. Perfetto. Già schermo intero.
Come va? Si vede bene? Va bene così?
Sì, si vede bene,
Ok. Bene, dunque mi ripeti i tempi così non mi sbaglio.
Allora, sono 30 minuti di talk più 5 minuti di domande. Diciamo, facciamo le domande urgenti e poi l'ultima discussione, se vogliamo, è no time limits, quindi l'ultima discussione della sera, quindi ci sarà tempo per...
Va bene.
Io ti farò sapere quando mancheranno 10 minuti ai 30 minuti, diciamo, senza includere le domande.
Ah, perfetto. Come me lo fai sapere?
Voce.
Ok.
Aspetto che termini una frase, ci provo almeno e
Va
dirò 10
bene.
minuti.
Va bene.
Aspettiamo ancora qualche minuto. Tempo previsto, inizio previsto è 35. Vediamo se arriva qualcuno. (53) per una sessione serale non è poi così malvagio.
Dai tanto tempo, non ti preoccupare.
No, ma infatti io direi aspettiamo almeno 35, 36.
Sì, ma infatti non dobbiamo essere proprio strict.
Per fortuna questa è l'ultima sessione, quindi non ci sono più vincoli così stretti.
Vuol dire che posso parlare per 4 ore?
No. Magari la discussione, ma andiamo avanti per 4 ore. Hai visto la fine della discussione precedente? Ci piacciono lo spirito di questa conferenza e cercare di dibattere il più possibile.
Ok.
Raccomandazione per tutti, siamo sempre su YouTube.
Non
diciamo cose
Luca,
compromettenti.
yes, but I guess we can
Yes.
already start switching to English, otherwise.
Sure. It's
All
just
Italians can understand.
during the breaks, one forgets.
Luca, mi senti?
Sì, yes.
If there are questions from YouTube channel, I can watch them and pass to you, or
We will see it. We can
Yes.
see anyway in
Well,
the discussion. I
yeah.
think the
at least for the discussion, perhaps.
Yes, in this case, there's time for the discussion session. Yes.
Because I'm watching on there as well. Okay.
I see. We will see how it's going.
Because there is already one question for Dr. Rovelli.
Be good.
Don't even start talking.
Oh, wow. Probably he was asking what he's having for breakfast, because I don't know other question.
What did you have for breakfast? You want to answer? Okay. I think it's almost time to start. So, okay, person are only slowly increasing. So, in the meantime, probably we can start. And
Yeah, let's start.
okay. So, in that case, welcome to this last session of the Quantum and the Gravity meeting. I am very happy to be the chair of the last session, as I was very happy to be the chair of the opening, so I opened and closed. And I'm very happy to present. We have very great guests. We have Carlo Rovelli for the first talk, and then Renate Lolle and Giovanni Acquaviva, which will close the event. And so I think that, Carlo, you can start.
Thank you. Just give me an okay if you see the slide and hear my voice. So I'm sure that.
Perfect.
Okay, wonderful. So thank you very much, all of you, for surviving until the end of the last session of the conference and listening. I'm going to talk about quantum gravity applied to black holes, and in particular loop quantum gravity. So to frame where I'm talking from, so where this this presentation is based on, I think that it's not true we don't have a quantum theory of gravity. We have, in fact, more than one, very few, but we have a pretty completed possible quantum theory of gravity. What we lack, it's positive or negative evidence. So for this reason, I, together with many other people in loop quantum gravity, have shifted from theory building to theory applying, so to say. So I just flash one slide without commenting it. These are the basic equations of loop quantum gravity. So here it is. It's like, Maxwell theory. You can present the Maxwell equation. This is it. So this is loop quantum gravity. It's a Hilbert space, a set of operators, and some transition amplitudes. It's ultraviolet finite, and it's Lorentz invariant. The question is what physics, what we can do. And of course, the traditional areas for trying to apply quantum gravity are early universe and black holes. I'm going to talk about black holes. So most of the talk will be what loop quantum gravity says about black holes. But I want to start by sort of denouncing two misconceptions about black holes, which I decided to, I usually discuss that at the end, but this is a short talk, so I put it up front because otherwise it becomes very incomprehensible what happened after. And one is that there is a problem with the black hole information paradox before quantum gravity comes in, page time. This is a widespread idea. It's wrong in the sense that it is based on some assumptions which might very well be wrong. So it's not the arguments are wrong. The arguments are right if you write the papers, but they use an assumption which I'll discuss in a moment, which it's false in loop quantum gravity. And the second is that when we talk about black holes, we always sort of imply or have in our mind that there is an event horizon. And this may well be wrong. In fact, if loop quantum gravity is right, this is most likely to be wrong. So let me say what I mean by black holes if there is no event horizon, I mean the things which are in the sky, the real thing up there that we call black holes, which of course look quite like the Schwarzschild solution or the Kerr solution. They're very well accounted by the Kerr solution. But an event horizon implies something about the distant future, which might be questioned by quantum gravity for a reason that I'll illustrate in a moment. So if everything we see about black holes is well accounted by GR, what's the role of quantum gravity? Well, because there are at least two questions which are open in the sense that without quantum gravity, we have no idea whatsoever. One is that we virtually see matter falling to black holes through the accretion disks, and we have no idea where it goes. So this is obviously, I mean, if you take a bunch of matter, you have it spiral and emit and fall into black hole, where does it go? Answer, we don't know. Second, we consider Hawking radiation prediction reliable. So black hole shrinks, become very small. What happened next is a quantum gravity question. And without a quantum gravity theory, we don't know. In fact, the hypothesis that the black hole just pops out of existence at the end of the evaporation, it's an assumption about quantum gravity, which is wrong if loop quantum gravity is right. So this is a standard Carter-Penrose conformal diagram of a non-rotating. I'll talk about non-rotating black hole for simplicity. Black hole that with an event horizon forming. The quantum gravity region, it's sort of around the singularity, and roughly it's when curvature becomes Planckian. Now, I want to stress the fact that because of Hawking radiation, the horizon, let's say the dynamical horizon, the apparent horizon, the trapping horizon shrinks. So the black hole shrinks, it becomes smaller, smaller, smaller. At some point, if it is isolated enough, the things don't fall inside, it becomes Planckian. And when it becomes Planckian, the mass becomes of Planck order, the curvature, the radius becomes of Planck order. Therefore, the curvature outside the horizon, which is order m over r cube, becomes of Planck order. Namely, we are deep in a quantum gravity regime outside the horizon. Okay, so I stress, if Hawking is correct, quantum gravity comes in most likely outside the horizon, and therefore to assume that the horizon continues all the way to infinity regulated by classical GR is a ungranted assumption because we're deep in a quantum gravity regime. So let me say why the idea that before this quantum gravity regime, there is an information paradox problem is wrong. Because the usual argument is that when the horizon shrinks, the area shrinks, the entropy shrinks, the number of states of the horizon shrinks, so the possible number of states inside becomes small. But since the Hawking radiation, it's thermal and it's not in a pure state and it's correlated, at least at first sight, with something that falls inside, in order for unitarity to be true, the Hawking radiation must be purified by whatever is inside. So you need a number of states inside sufficient to purify it. But the number of states decreases because of what I just said before. And this happened roughly at page time, say halfway of the evaporation. And this is a problem. And that's a source of, firewalls and all sort of nonsense that it's being hung around. Now, why all this is wrong? Because it confuses two different entropies. And it relies on an assumption, namely the number of states of the black hole which is relevant for the Bekenstein-Hawking entropy, it's a total number of states. But there's no reason for that. And in fact, it's not so in loop quantum gravity. And to explain what the actual situation is a point of elementary physics. Just think that there is a room that exchanges heat and work with the outside. there's an entropy that regulates that, which is the number of states inside. But if it's inside the room, there's a box which is completely isolated. They cannot exchange heat and work with the room. The number of states in the box does not contribute to the counting of states that determine the entropy. However, if something in B was quantum correlated with a side observer in a previous time, it does contribute to the von Neumann entropy. So this is a situation of the black hole. The Becker-Sorokin entropy counts the number of states on the horizon, and in fact, that's what the loop quantum gravity calculation of entropy gives, which diminish when the Hawking evaporate, but the correlation with inside are determined by the von Neumann entropy, which is entanglement with something that before the quantum gravity region is lost, but after the quantum gravity region can be recovered. So if you look at the papers, well, I'll skip this, I don't have enough time. This is the famous paper about firewalls. They have an explicit hypothesis that says that the number of states total of the black hole, it's determined by the Becker-Sorokin error. That's an hypothesis, a postulate for them. And that postulate just falls in loop quantum gravity. If you want, it's like taking holography too seriously. Holography is correct to some extent, as long as the horizon behaves an event horizon, the black hole behaves as a system with a finite number of degrees of freedom determined by the area of its horizon, but not after the quantum gravity regime. All right, so let's go. This was a preliminary. Let's go to the heart of the matter. We know physics until the curvature becomes Planckian. So this region here is where it becomes Planckian. Now, importantly, let's look at the geometry, the last geometry before the quantum gravity region. So take this thing, this region here, take the Schwarzschild metric, just read out the geometry. It's a simple exercise. The geometry, this is the horizon, this is the outside. The geometry is the three-dimensional geometry of a very long tube where the star is at the end of the tube. This is space-like, right? This is a constant time surface. So it's a space-like surface, which as time passes, as you go up toward the quantum gravity regime, the tube becomes longer and narrower. And you enter the quantum gravity regime when the radius is not the Planck radius, but the Planck radius multiplied by the mass of the original black hole divided by the Planck mass to the 1/3, which means that if you take a stellar black hole, if this is a collapsed stellar black hole, and if you wait long enough, assume it's isolated and it evaporates, just before evaporating, the inside is a tube whose length is 10 to the 75 light years, right? So by locality, what happened here, what happened here, and what happened here must be disconnected problems, which means that the problem of quantum gravity properties of a black hole is actually three distinct problems. What happened to the star, what happened to the horizon, and what happened in between where you don't, you're spatially, so locality prevents you from being affected by the star and by the horizon. So there are three problems. Let me describe these three problems separately and what loop quantum gravity says about the three. So I'll start with the C region, the star. The star is relatively simple because it's a compressing ball of matter which behaves very much like the universe if you run generativity back in time. And there's all the huge amount of work in loop quantum gravity done in cosmology, it's called loop quantum cosmology, where one finds that the Friedmann equation is corrected by a term, this term here, which gives a sort of repulsive force when the energy density becomes Planckian. So instead of having the classical solution that goes into the singularity, you find a bounce. It's sort of the Heisenberg principle produces a repulsive force that pushes the star outside. So the physical C reason is that the star wants to bounce out. Now, careful, it wants to bounce out, but it's at the deep of this very, very long tube in this space-like surface here. It's far down there. And how can it bounce out if there is a black hole around and so the light cones point inside? How can it bounce out? Well, wait, let's look at the problem in the A region. Now, in the A region, we can ignore the Planck star and we can ignore the horizon because none of the two is relevant. And so just ask the question, in the case in which there is no evaporation, so the horizon is always macroscopic and there's no star inside. What quantum gravity says about the possible continuation of the dynamics after the singularity. And this is a problem that has been studied in loop quantum gravity very much in the last years. There is a lot of works into that. This is some of the people involved. In fact, the study of that goes back to the 50s. The first idea comes from Singh in a paper in the 60s. There is a completely natural continuation of the metric from a Kluska region to another Kluska region, in which you go from the black hole to the white hole, through a transition which you can view as quantum tunneling, which is predicted by the evolution of loop quantum gravity. You can just use a sort of a mini superspace loop cosmology techniques to evolve, to continue, exactly like the bounce in cosmology, and you find yourself from a trapped region to an anti-trapped region. The geometry is pretty because you can look at the effective metric, the sort of expectation value of the metric, which gives you a classical geometry that goes through. And the classical geometry is the simplest you can imagine. Remember that the surfaces here, which is actually surfaces of constant Schwarzschild radius. Remember that inside the Schwarzschild radius is temporal coordinate. So constant time Schwarzschild radius. Okay, when you move in, you have this tube that becomes long and narrower. And when you get to the Planckian regime, namely when this tube has a size, a radial size, which is not Planckian, it's Planckian multiplied by a power of the original mass of the black hole, you get to a minimum cylinder which bounces back. So you have a completely smooth transition which becomes singular only in the limit in which you set h bar to 0, so to say. So this explains what how can the star bounce, because the star want to bounce and find yourself in an anti-trapped region. So in the moment in which there's a transition, the trapped region evolves into an anti-trapped region, and the star bounces because it can in an anti-trapped region. That's exactly what it wants. So the C and A solution of the problem are consistent, physically consistent. What about the B region? Because if I glue two different Kruskal space-times in this way, well, inside I just a star bouncing, but outside I have two asymptotic regions. And I mean, what creates the other asymptotic region? Well, this is probably the most, in my opinion, the best results in this game, which is a result which came up in a paper a certain number of years ago now, which is the following. There is a classical solution. This is a result in classical generativity. A truly unexpected result in classical generativity. There is a solution of the Einstein equations, vacuum, spherically symmetric, which allows this two asymptotic region to be one. Namely, the same outside can continue into a black hole here and into a white hole in the future, not in the past, like the Kruskal case, provided that there is a violation of Einstein equations in a teeny quantum region here, which, remember, this is the end of the OK evaporation, maybe before, but at least at the end of the OK evaporation, namely, this is Planckian, okay? Inside is not Planckian because there's a full mass of the thing, which is losing mass because of the negative energy flux of the incoming Hawking radiation. So how is it possible that there is a classical solution there? Well, I guess this talk is too short to give you the construction, but the key is that it's a solution which is locally isomorphic to Kruskal, but not globally isomorphic to Kruskal. So in other words, you can take Kruskal, cut it in pieces and double some of the pieces, the ones here, and patch them together and obtain the solution here. So we have a completely consistent story. I'll skip this. We have a completely consistent story in which is classical generativity all over, beautiful. Okay. Inside, there is a bounce of the star due to a quantum gravity effect. At the singularity, there is the loop quantum gravity transition from the trapped to anti-trapped region. And then there is this teeny region here in which the trapping horizon tunnels into an anti-trapped horizon. And notice that there's no event horizon, right? The null infinity, the past of null infinity is everything. There's no boundary of the past of null infinity. So as I said before, there is no event horizon. Remember that at some point, Hawking published a paper saying there are no black holes. He was saying exactly the same thing. It didn't mean there are no black holes. It means the black holes, the thing we call black holes, have a trapping horizon, but not an event horizon. Good. And what about the information paradox? Well, the naive information paradox, where does the information inside go? It's easily resolved. It just crosses over to the white hole and comes out. The sophisticated page time information paradox also is not true, because the number of states inside is not just determined by the number of states on the sort of extended horizon here, but it's much bigger. So the number of horizon states decreases with Hawking entropy, but the von Neumann entropy, if you trace inside, stays big. And in fact, it decreases when things come out from the white hole. The full metric, including a guess of the full metric, including the Hawking evaporation, has been studied in great detail. From the outside, the mass decreases with the Hawking radiation, remain non-finite, and then it decreases further when the inside comes out. This is just to show you that the full metric is written in great details. Of course, I'm not going in all these messy things.
10 minutes.
Oh, thank you. Oh, good. I'm doing great with time. Now, what about this B region, which somehow I said, well, if quantum gravity allows it? Well, notice that the physics of this free region is determined by just a small number of parameters: the mass of the black hole, the time of the evaporation, when the time it takes when this quantum transition starts, the tunneling time itself, and then the mass of the and then the lifetime of the white hole itself. So if this was classical theory, the theory should give us how initial data determine that. But this is quantum theory, so what we want is the amplitude for this transition given these parameters. So the technical problem is to compute the amplitude as a function of these parameters here. And that's what is being done in loop quantum gravity today, this calculation. And one has to do the quantum gravity physics of this region here. The way it's done in loop quantum gravity through this equation that I flashed very fast at the beginning is to compute the transition amplitude from some initial state to a final state with a spin-form transition, which can be viewed as a truncated sort of Feynman integral. You're summing over the geometries here, so to say. You're summing over the geometries. And so what you do is to whoops, I want to go fast. Yeah, no, sorry. I'm going to slowly. Yeah, you pick in the classical metric. We know the classical metric as a function of this parameter. You pick an initial surface and a final surface, classical. You have the intrinsic and extrinsic geometry. You can compute it because we know it. We have the solution. And we want the quantum transition to go from this intrinsic geometry, from the past geometry to the future geometry, which, since the geometry depends on these parameters, is going to depend on these parameters here. And in quantum gravity, you do that. You have to do this in a truncation, of course. So you truncate the information here and here by choosing a spin network on the boundary and a spin form in the bulk. And this is a bit tricky because the topology of this thing is funny, right? It's a disk times S2 times a sphere, because this is a Penrose diagram. So this is a spin network, this is a spin form, and this is actually the transition amplitude. Just to flash you what it is a complicated integral of SL to C, it's finite. There are some technicalities. I'm not going into the technicalities. So what we're doing right now is to try to evaluate these integrals using both symptotic techniques and numerical calculation. There's a beautiful code which has been developed, is online. There's been a work of several years of developing this code for actually computing these things, which are complicated. What comes out next? Well, here is a white hole, which, remember, it's a very long tube here, even if this is very narrow, because this happened at the end of the Hawking evaporation. So the throat here, it's Planckian, but it's a very, very long tube. So it takes a lot of time to come out. So there are some indication, this is not definitive, that the lifetime of the white hole is m to the 4th. It's very, very long. Which give immediately, this is I don't have time to go through this slide, but there are some arguments that this white hole is stable because of quantum gravity. So you have the stable microgram particles floating around if there were small primordial black holes that have ended the Hawking evaporation, which are a natural candidate of dark matter. So one of the attempt to connect that to phenomenology is using this as kind of possible candidate, maybe component of dark matter, and see what the effect have into cosmology. One remarkable thing is that if you compute the proper time for an outside observer between, say, collapse and emission of something, is very long, but the time inside is very short. It is GR, right? So you can have a very short time here, a very long time here. I mean, billions of here, microseconds here. So in a primordial black hole, what fell in is it's very high energy photons, according to standard primordial black hole theory, formation theory. So if this is correct, we should see very high energy photons coming out from the white holes at some point. Right? And now there is something very, very pretty here. I don't know if I have time to go into this. If one of these comes out from a white hole at cosmological distance, long time ago, then its emission frequency is shorter because the lifetime of the white hole is determined by the mass. The mass is determined by the temperature at which, according to primordial black hole formation theory, at which it's determined by the Hubble radius when it formed here, which in terms determine the temperature, which determines the energy of the photons. So there is a correlation between the emission wavelength and the time in which this is emitted, which will be unique. No other astrophysical object that we know have this thing. So this might give a signature of seeing this thing in the star. That's one of the many possible phenomenological consequences of the story. So of the story of the black hole tunneling into white holes at the end. I am not an expert in this phenomenology. There are attempts to interpret this as dark matter, to, as I said, see particular signal in gamma ray, very high energy gamma rays. As an idea to connecting to fast radio bursts, which I don't have time to mention. And of course, if these are out there, they have a effect on cosmology or some review and experiment. So I prefer to use a little bit less of the time that I have to have more time for questions. So I'm going to finish a little bit in advance. This is my summary. First of all, I want to stress there are three distant quantum gravity problems for a black hole. And when we try to solve all those three at once, we get confused. I think we get contradictory things is not clear and things don't work. There is a C region, I call C region, which is what happened to the matter when the matter gets to the quantum region, okay? This has nothing to do with the question of what happened to the singularity, because I can fool the black hole much later than the collapse, And I never meet the matter. I'm very, very far away, spatially far away, millions of years far away from that. So there's a quantum gravity problem here. What happened to me? And what happened to the star? It bounces. What happened to me? It's just I found myself in an anti-gravity region. And third, there is a problem when at some point something happens to the horizon. Certainly at the end of the black hole evaporation, the calculation might even tell us, and it's possible, in fact, I hope so, that the transition could happen when, not at the end of the black hole evaporation, but earlier, at sort of not time m cube, but time m square. I was hoping that, but the first calculation seems to go the other direction around. So there's no event horizon. The black hole, the black to white hole transition have a rich astrophysical phenomenology. Nothing has been seen clearly yet, of course. But one possibility is that all the dark matter that, or part of the dark matter that we see could be this remnant, white hole stable, quantum gravity stabilized remnant of black hole. Loop quantum gravity specifically has been used in all these regions. The covariant version, which I work, spin form, can be used to do the physics of the B region. The canonical version is easier to do the A and C transition. And then I want to stress, every time you hear people saying that there is a problem at page time, there's a black hole paradox, remember that they're giving for granted, because they believe it, a version of holography, which is an hypothesis. Could be right, but it could be wrong. It's not something we know we have acquired. And final message that you may remember, a black hole, even at the end of the evaporation, when its throat is very small, its inside is very long, is huge. There is a precise definition of volume inside, and it grows with time. So two black holes with the same area are the same as seen from outside, but not the same inside. All right, so there's a lot of physics one can do with loop quantum gravity in various ways. This is sort of rapid survey of what is being done with loop quantum gravity on black holes. Thank you.
Luca, you're muted. Okay. Probably, I don't know if the chairman is having issues with the sound, but
sorry, I didn't see, but I was saying you're perfectly in time, and we have time for questions, actually. So sorry, Francesco is the first.
Hi, thanks. And thanks for this very nice talk. I really enjoyed it. And also, I really agree. I agree very much with you on many things like the event horizon and the information loss. I have a doubt. It could be a also very stupid question, but let me just ask it. So in this picture, you have all the matter that forms the collapse enter into the black holes and then gets emitted into the white hole, right? But at the same time, from an external observer, this takes a very long time, right? Like M cube or like. So this means that if we assume semi-classical physics for this external observer, you also have emitted this the mass, you also have emitted it as Hawking radiation, right? So
there seems to be a problem.
Sorry?
There seems to be a problem.
Yeah, but I mean, maybe not, maybe there isn't, but
yeah. No, there seems to be a problem. I tell you what is the solution. I see exactly what you're pointing out.
Mm-hmm.
Yes. So that's it. That's the question, right? How is it possible? I mean, in sense, you're saying I'm looking for the right slide, but I can't find it. Where it is? I lost it.
Yeah, I'm saying there should be a way to convert the matter into Hawking particles in order not to avoid violation of energy, right?
Exactly. Maybe here. Okay. Here. So this was just to remember that when the Hawking radiation is, so your problem is, and you're completely right. And in fact, at the beginning, we were enormously confused here. So the matter falls in, say it's a mass M, then the Hawking radiation comes out and arrives here.
Yeah.
And the Hawking radiation has a total energy roughly the same, right?
Exactly.
Maybe half or whatever, but it's the same order. But then the matter comes out again. So then we have double the energy here. What is going on? I mean, something seems funny. No. In fact, we were confused for a while about that. But then it turned out that when you go into the details, everything works very nicely, because the Hawking radiation, there is some ingoing Hawking radiation, some outgoing radiation, some ingoing radiation. More precisely, if you do, we did the quantum field theory energy stress tensor of the Hawking radiation. I can do explicit in 2D and give you an idea what happened in 4D. You have negative energy flux going in, right? Yes. So if I look at this on this time slide, I have a positive energy here, negative energy here, positive energy here. So to roughly M minus MM. So the total energy is fine. So what happens, and this is comes explicitly in this kind of calculations here, which I didn't have time to go in. This is completely unreadable. So let me go to a general picture. What happened is that the negative energy enters the horizon, crosses the singularity, and gets on the star. So you have the negative energy and the positive energy. So inside you have very little energy. And this is the point. You have a lot of information inside because information is conserved, but very little energy. And that's why you have a very long time here. Because whatever comes out must have all the information and little energy. It's possible, provided you have a long time, right? You have think in terms of photon. To have a lot of information, you have many photons, but low energy. If you have an overall small total energy, you need many of them, small energy, but small energy is possible. Photon can have as many small energy you want, but then you have, low frequency, everything is longer, so it takes more time. So the mass that comes out is not the same mass that comes in, is a mass that comes out with energy killed by the negative energy quanta of the Hawking radiation. And let me add one thing to what you said at the beginning. You said you agreed with both what I said of the horizon and the Planck and the page time. I apologize. I presented this as it was my idea. Is not. I mean, it's I'm not the only one, and these are ideas which have been around for a while. I wanted to stress this. So thank you for pointing this out.
Yeah. No. Yeah, I will think more about this point, because still I have but I need to think about it. I cannot.
So what we actually, the calculation we did is, it's not matter. We did it with light rays, with photons. So the light rays bounce and they meet with incoming Hawking radiation, and then we computed the interaction between the two, and somehow the positive energy of the bounced light ray and the negative energy of the Hawking quanta produce a something which is given by the difference between the energy that comes out. So energy at the end, outside energy is conserved at the end.
Yeah, you probably understood even though I was not formulating it, my doubt. It's if imagine that I formed a black hole with massive particles, instead Hawking radiation will be mostly photons. So what do I see out? Do I see massive particles? Do I see photons? Or because even if and maybe in the region in which you have full quantum gravity, there could be a conversion between the two. But it's not trivial. So I will.
If it's a good point. I only would be able to answer in terms of quantum field theory, where particles numbers are not conserved. If I think in terms of particles, I do see it's I don't know. I don't know.
Yeah. Okay. Well, it's very interesting. Thank you.
So sorry to interrupt you, but a little bit out of time, but I didn't want to interrupt you before. So I asked to Alexander and Sugato if we can postpone the question for a discussion session. You will be the first, actually. Okay. Alexander is still with the raised hand.
Yeah, sure. I can ask questions during discussion.
Okay,
No problem.
okay. You will be the first, actually. So
okay,
we can thank Carlo again, and we can pass to the second speaker of this session, which is Renate Loll. Okay. Okay, I can see your slide, but I cannot hear you, Renate.
Now you can hear me because I was muted, I hope.
Okay, perfect. Good. Okay.
Let's see. Does that work going full screen?
Sure. So you have 30 minutes from now.
30 minutes from exactly 1:15. Okay, great. Well, let me say, I'm very pleased to see how much activity on gravity is emerging from Salerno these days. So, keep it going, guys. We've also seen this week that there is really a lot happening in gravity and, at the interface with quantum theory and in various kinds of combinations. And what I'm going to focus on today is the end in the quantum and the gravity. So I'll be talking about quantum gravity beyond perturbation theory. So, so that's the context of my talk. The search for a theory of quantum gravity that's valid in a non-perturbative Planckian regime. And I'll just constrain myself to d = 4 and to a positive cosmological constant, whose value will not be fixed by what I'm saying, but this will be the general setting and working without any preferred background. So the framework I use is CDT, quantum gravity, which some of you may have heard about, causal dynamical triangulations, and that's a non-perturbative implementation of the Lorentzian gravitational path integral. I'll say more about this later. Of course, path integrals of the Euclidean variety seem very popular these days. So the great charm of this approach is that it allows me to address kind of Planckian problems quantitatively. And it's of course in a specific approach, but I believe its results and insights are valid more generally, and we will see some examples of that. Now, what I'll be talking about today, of course, has to fit into 30 minutes. So there's some main messages. So let's say the state of the art, having, that's a big body of research that had involved many people of the type of kind of statistical approach, random geometry approach to non-perturbative quantum gravity is that it's very different from semi-classical and perturbative gravity. So part of it is just by construction, by definition, because you're working in a very different realm of the theory, and you're taking seriously the dynamics of space-time and the fact that quantum fluctuations can be very large. Key to understanding this regime are diffeomorphism invariant quantum observables, and we've made quite some progress in finding such objects and studying them and measuring them, even beyond this particular approach. What I talk about at the end of my talk is a new quantum observable or ingredient for quantum observables. That's the quantum Ricci curvature. And it's a new notion, which is somewhat remarkable that it exists at all, because we are working with very highly non-smooth configurations, so beyond G mu nu, definitely. But nevertheless, one can define a notion of quantum, renormalized quantum Ricci curvature that is well defined in such a context. Okay, let's start by a couple of nice pictures, kind of to refresh our minds why kind of quantum geometry is so different from classical geometry. So according to general relativity, of course, so that's the little picture I have here. Give me an arbitrary curved space-time and let's stay away from singularities. But if you then zoom in on any part of such a space-time, zoom in further and further, well, eventually you will end up with a piece of space-time that looks flat, more or less, like flat Minkowski space. So it's kind of smooth and structureless. Now, the idea we have of quantum geometry is the opposite. So we are zooming in kind of beyond classical and semi-classical scales. And what we expect, what eventually happens is that, whatever geometric metric degrees of freedom are there, they will be highly quantum fluctuating. So it may not make any sense at all to speak about, a G mu nu or even some effective G mu nu, and instead people, draw pictures like space-time foams, quantum foams. So we of course know that for many reasons, including technical reasons, perturbation theory is not sufficient to describe such a regime. So of course we want to do more than draw pretty pictures. So what is our idea? What are possible ways of getting a handle on what quantum space-time might be? Now, there is a set of radical but kind of popular ideas, namely that space-time is fundamentally discrete, with some fundamental discreteness parameter typically chosen to be the Planck length, obviously. So I would say, to my mind, causal sets is the most serious of these approaches. So you have your little causal set drawn, and it's truly minimalistic. You just have a bunch of events, and you have causal relations between them. So there is no ambient space-time of any kind. So that's, of course, it's very, let's say, purist, very minimalist. We've also, in some talks today, have people talk about, how to derive space-time or gravity kind of from discrete quantum bits. I think that's interesting, but we know that it's very, very hard. It's very hard to get out anything that really resembles, well, of course, not only a specific space-time, but gravity, right? Gravity should come out. Dynamical gravity should come out. So also maybe it's sometimes underestimated how difficult it is to make things emerge. And we know, I would say, I'm not aware of any examples where kind of gravity, dynamical gravity alongside space-time emerges from such minimalist ingredients. So, but it's of course, it's what people have studied for a long time. What seems a more fruitful starting point, and again, that's a statement I'm making based on research of the last 30 and more years, if you work not with discrete spaces, but with continuous spaces, which are, however, non-smooth, but have metric properties. So the ones I'll be using are what's called piecewise flat geometries, which could be triangulations. That's a very convenient thing to do, but it could be quadrangulation. So the general idea is you start off with little building blocks that are individually flat, right? And then you glue them together. And the shape of the building blocks, well, shouldn't matter too much, right? That's why I'm mentioning also quadrangulations. But so, and you generate some approximate version of curved spaces by assembling such building blocks. In mathematics, that goes by the name of random geometry, mostly studied in 2 dimensions, but people have also started looking at this seriously in 3 dimensions. In physics, you may be familiar from this kind of setup from Regge calculus, which you can use in classical general relativity, where one works with so-called simplicial manifolds. A simplex is simply a triangle or a higher dimensional version of a triangle. So what one uses in kind of random geometry, one works with equilateral such triangles and glues them together in all possible ways. I mean, in 2 dimensions, it would be triangles. In higher dimensions, it will be, D simplices. What one then does, one takes a superposition of all objects that, say, can be built from a finite number of such building blocks, let's 10,000 according to some manifold rules, and weighing each of them with the Einstein action, some version of a gravitational action. So what I've written down here is a Euclidean version of the path integral, because that's typically what appears certainly in a mathematical context, where one has to be concerned about the existence of these objects. Yeah, because one wants to take an infinite limit where one takes the number of building blocks to infinity and kind of shrinks the individual building blocks. And then, of course, it's very difficult to understand the asymptotic behavior of such a path integral, such a superposition, when we integrate over complex amplitudes. So nevertheless, so the message is one wants to study such an object, put in regulators. And so the regulators are just the UV cutoff, the edge length of the individual building blocks, and it's just the number of objects, building blocks in your configuration. And then you want to take a non-trivial continuum limit, and you hope that some interesting physics can be found in such a limit. To get an idea of the type of geometries that kind of contribute kind of most to these kind of path integrals, yeah, you should look at this little picture here that's taken from from two-dimensional quantum gravity. These tend to be very, very non-classical objects and very non-smooth objects. So kind of higher dimensional analogs you make, a good way to think about them is higher dimensional analogs of kind of the Nova differentiable paths that are, form the bulk of the measure when you do quantum mechanics of a non-relativistic particle. Now, in order to illustrate that such an approach leads to interest in physics, there is a very nice example one can point to in 2 dimensions. So that's a toy model of Euclidean quantum gravity that goes by the name of Liouville gravity, was studied very much back in the 1980s, but really in the way one constructs it and kind of the typical features that appear, it serves as a blueprint also for more physical models of this type in higher dimensions. So the strategy here is really, again, to say work with triangulations in 2D, but think of them as a regulator. So don't think of it as, a fundamental ingredients where you postulate that space or space-time consists of little triangles. So it shouldn't matter too much what type of building blocks you use. So you then perform a scaling limit, and of course you will typically meet infinity. So that's you are approximating a quantum field theory in this way. That means you have to renormalize couplings, operators appropriately in such a limit. Now, in this particular 2-dimensional quantum gravity toy model, one can actually solve it exactly using this dynamical triangulation approach. So where you assemble, all possible 2-dimensional spacetimes from little triangles and sum over all of them. This can be solved with combinatorial methods. It can be solved with matrix model methods. And really, that's work from the 80s, and a lot of it was inspired by trying to find a non-perturbative description of string world sheets. Okay. In the meantime, it has been very much studied by mathematicians, people working on stochastic models, and I've just I've singled out here Le Gall is a very well-known mathematician who just received a couple of years ago the so-called Wolf Prize for his work on kind of making rigorous some of these 2-dimensional quantum gravity constructions, and in particular describing kind of a universal metric space kind of on the space of all geometries that comes out from such a 2-dimensional path integral in physicists' terminology. And which also shows that the universality, that means independence to a large degree on the discrete building blocks, the kind of the regularization details, we would call them, that you put in initially. Now, interestingly, 2-dimensional, the quantum gravitational Euclidean path integral is sufficiently simple in 2 dimensions that you can almost do it analytically. So, and that's also a well-known construction due to Disler and Kawai, which means you can do it modulo some, plausible assumptions which are hard to verify, but nevertheless then lead to results that can be shown for at least for observables, one can compute to be equivalent to those coming from these more statistical constructions in terms of triangulations. Now, what's important and what's also true in higher dimensions is one has metric spaces one is working with. So one does have a notion of distance. Geodesic distance is given by kind of edge distance or dual edge distance. You know, you're hopping from building block to building block. The building blocks are all identical, so everything is kind of unit one in terms of these discrete distance measures, and you also have access to a notion of volume. With these ingredients, you can then construct quantum observables. So these are kind of truly geometric, so also diffeomorphism in variant quantities that typically are very non-local. That's a well-known fact of gravitational quantum observables. And so what are examples? There are scaling exponents, so-called dynamical dimensions. You then can associate with the continuum limit. So you could think of that as kind of the ground state of this dynamical quantum fluctuating system, and diffeomorphism invariant endpoint functions. So which for low n can have also been studied analytically, but can also be measured in simulations. So that's another kind of aspect of these models. In dimension 2, for the pure gravity models, they can be analytically studied, at least the asymptotic behavior, and that has been done, and even kind of rigorously, as I pointed out. But they can also be studied by Monte Carlo simulations, and that's extremely useful for regimes. For instance, once you start coupling matter, these are not easily solved then anymore. And of course, when you go to higher dimensions, the same is the case. But it gives you, nevertheless, a quantitative handle to understand, if you ask the right questions, how these systems, how these models, theories behave. Now, another thing that is beautifully illustrated by this 2D example is don't expect things to behave as you would classically expect. So one of the dynamical dimensions one can measure, so basically, I mean, the spectral dimensions, the Hausdorff dimension are two of these classic observables that one can relatively easily measure. They don't come out as classically expected. So that's a Hausdorff dimension here that describes basically how a geodesic ball of a certain geodesic radius scales with leading power as a function of that radius. So it turns out that in Liouville quantum gravity, that Hausdorff dimension is 4, despite the fact that you started with, gluing together two-dimensional building blocks. You have taken a non-trivial scaling limit, and what then simply can happen is that you get non-canonical scaling in the quantum theory. And that's, again, a feature that one also finds sometimes to one's detriment in higher dimensions. Many more things I could say about this, but here I've highlighted in blue the things that will kind of carry over also in spirit, in the way of construction, to higher dimensional models, which are, of course, what we are interested in physically. And so in addition to the quantum observables here that were named, the endpoint functions, well, there are more. And one of them is exactly this quantum Ricci curvature that I'll be talking about in a short while. Okay, so what is the matter for d larger than 2? So unfortunately, I mean, the same kind of construction I just talked about in 2, it doesn't straightforwardly generalize. Although, of course, that was the thing that was tried immediately when people saw they had a nice way to describe, quantum gravity in lower dimensions. So why not go to quantum gravity and try to define it as a scaling limit of just some really no frills superposition of space-times? Why not generalize it to higher dimensions? Well, and there's one one problem that you already were familiar with from the continuum Euclidean path integral. Namely, it's a property that also prevents kind of brute force putting gravity on the lattice approach, which is the fact that indeed both the Lorentzian and the Euclidean action are unbounded below. So it's a kind of a killer, a potential killer for any Euclidean path integral beyond dimension 2. So in 2 dimensions, this divergence, the so-called conformal divergence, isn't there, but in higher dimensions it's there from 3 upwards. So what is the problem? For those of you who are not familiar with it, take just G mu nu and split off the conformal factor, say by demanding this G bar mu nu, say to have unit determinant or constant curvature. Then check how your action, gravitational Einstein-Hilbert action, simply the Ricci scalar term, depends on the kinematic term phi dot squared, where phi is this conformal factor here. And it turns out it contributes with a minus sign. So that gives rise to this infamous conformal divergence. And well, it's already there when you do Euclidean quantum cosmology, because then all there is of course, is a Friedmann factor. And the Friedmann factor is nothing but the global conformal factor. Now, it turns out here in these statistical models, these random geometry models, as a consequence of this divergence, the path integral is dominated by so-called branch polymers. So here's a branch polymer. It's an object with Hausdorff dimension 2, spectral dimension 4/3, and it's the Euclidean path integral seems to be overwhelmed by these objects, and there is no second-order phase transition, as one would need for this to be interesting candidate theories for quantum gravity, continuum theories. There doesn't seem to be a classical limit which has extended geometry anywhere. And interestingly, this seems to be a very generic kind of entropic effect that you also see, for instance, in tensor models or causal sets. The only known cure at this stage to overcome that problem sufficiently is to go from dynamical triangulations to causal dynamical triangulation. So in a way, it makes the path integral Lorentzian. I have to cut that story very short in 3 lines because I still want to say something about the curvature things. So the idea there is you start from the Lorentzian path integral with the I in there, impose on all the path integral history that they have a well-defined causal structure. I mean, it's still quantum fluctuating, not rigid, but it's a causal structure that is kind of a lattice analog of a global hyperbolicity. You Wick rotate these geometries and then investigate, again, convergence asymptotic properties in a continuum limit of this Wick rotated partition functional path integral. And that changes the whole ball game, and you see interesting stuff. So you see, amongst other things, second-order phase transitions, so candidates for continuum quantum gravity, and you have a phase in your phase diagram of coupling constants of emergent extended 4-dimensional geometry. Now, we do not yet know whether this formulation gives us a good UV completion because we don't at this stage have enough observables to pin down the renormalization group flows. But what we already know is that we have apparently a computational framework that allows us to investigate within about a factor 10 of the Planck scale non-perturbative quantum geometry via quantum observables. And one thing that has been discovered this way is this dimensional reduction. That means the spectral dimension that goes from 4 at large scales to somewhere around 2 on small scales was seen in CDT and appears to be a somewhat general feature of quantum gravity models. So that's a beautiful example of a quantum observable that one has been able to calculate in a whole set of approaches. Okay, here is my path integral again. Let me not dwell on this. Here is my building block in 4 dimensions, because I just want to say this is kind of the setting. As I said, it's kind of no frills. There are not many. There are just 2 tunable parameters at this stage, and one studies this system. One tries to understand the geometry of the superposition of these states in a continuum limit here, and where one sees interesting physics is very far away from a perturbative Minkowskian regime. I would take much more time to explain to you why this is so. one of the interesting results that we found is that if you are sitting in the right region of coupling constant space, you find that an overall shape of the quantum universe emerges. And this overall shape is, by which I mean the three-dimensional volume as a function of kind of a proper time, has the shape of a de Sitter universe. And here is the curve with the matching of the data and the theoretical values. It's of course, because we have equitated, it's a Euclidean de Sitter universe. Now, the interesting thing is, so we've matched, therefore, one observable, namely this what we call the volume profile, is just one mode of the geometry, you could say, to a classical expectation for sufficiently large distances. The question is, can we already claim that we are looking at a de Sitter universe? So is in some maybe coarse-grained sense, this already proves that we are talking, we have a kind of round de Sitter space in S4. And of course, there are many pitfalls in this game. And one of them is to draw conclusions guided by one's classical intuition too fast. Because the point is, no, that's absolutely no proof we have such a de Sitter universe, because we have just studied one mode and matched that to a classical expectation. But there are, of course, there are so many others. So one crucial question that we had for a long time is, can we say anything more about this quantum universe we have generated there in this de Sitter phase, which has a nice shape, a very suggested shape, and it has the right dimension, namely 4. Can we say anything, for example, about its curvature? Because then we could maybe say, well, it's approximately, in the sense of expectation values, a constantly curved space, and hooray, maybe we are closer to a true de Sitter identification. That raises the question: what the heck is the curvature of a non-smooth space like this, a nowhere differentiable space, right? Clearly, evaluating the Riemann tensor doesn't make any sense there. And until recently, no well-known, well-defined renormalized notions that would be applicable in such a regime were known. Interestingly, many other people in math, in pure mathematics, in combinatorial mathematics, people studying graphs, had arrived at similar questions and been working with various types of Ricci curvatures. And we were able to use one of these definitions and adapt it to the quantum gravitational framework. And let me just take the last 3 minutes to explain to you how this works and why this is so beautiful and useful. So what is the idea? The idea is you're sitting on a metric space. You don't need any smoothness. You only need to be able, so it's Riemannian signature, I should say, to talk about distances and about volumes. What do? You pick 2 points at a distance delta. You define 2 spheres. They don't have to be nice spheres or even topological spheres, but you then define a notion of distance from between the 2 spheres, and you compare that distance with the distance of the centers. And then there is a general observation. So that's true also in a completely smooth Riemannian setting. On a metric space with a positive Ricci curvature, this distance d bar between the spheres, quite independently of how it's defined, will be smaller than the distance delta of the centers. And conversely, if the Ricci curvature is negative, that distance would be bigger. And so we've implemented this in our quantum gravity setting, where it can be, well, relatively straightforwardly applied. So what we do, we set actually the radius equal to the distance between the centers. So we always look at kind of double sphere arrangements like this. We compute then the average sphere distance and compare it, form the quotient with the distance between the centers. So here's the quotient. And what is then the quantum Ricci curvature is kind of the deviation of this from a constant. So CQ is a constant. The quantum Ricci curvature is this KQ, depending on delta, the radius of these spheres. So that sets a scale. And so we're extracting here a Ricci curvature from this distance measurement prescription. You can do that for smooth Riemannian manifolds. for instance, in Riemann normal coordinates. And what you then see is partially what justifies this definition is that you always get kind of a constant first term, and then you get a delta squared correction term, which knows about the Ricci curvature, where V is just a vector pointing kind of between the two spheres, between the centers of the two spheres. And you can work this out in the continuum in any dimension. Yeah? So the key thing is only distance and volume measurements are needed. It can be implemented on these very, very screwy and quantum fluctuating quantum geometries. And here are the results. First, we built kind of a reference library of these things in the continuum for classical spaces. So we understand when we see a certain behavior of the quantum geometries, there is something to compare to. So, and the most straightforward thing here is to compare to constantly curved spaces. Here I've drawn the curvature of these two distances, you see, for a flat space where there is no correction term, so everything is always constant. For hyperbolic space, where this then is above the line, and here for a sphere. Yeah? And we study this systematically for other classical spaces with conical singularities, ellipsoids, to have something that's non-isotropic. But again, it's a long story, and I just want to present to you now, for instance, what do I get when I apply this in Liouville gravity, which I mentioned earlier in the talk? Well, I measure then the expectation value of these sphere distances averaged for kind of fixed delta over all pairs of spheres on my configurations, and of course in the ensemble average and in the quantum theory. And what we then find is here are the data points collected, for various volumes, and where typical universes look like this. And it can be matched quite beautifully to a 5-dimensional continuum sphere, where you should think of the first bit of this green curve here that we are matching this to. Okay, so that's the result. It shows you it's applicable, and it's a quite robust thing. Okay, that brings me almost to the end of my talk. So what then happens in 4 dimensions? That was, of course, a crucial thing. And it is not easy to measure. We have been going to configurations of up to 1.2 million building blocks. And we've done the same measurements as in 2D. But it's much more difficult to extract results. Nevertheless, what we found is a quite similar looking curve to what we found in 2D, as I said, with much more effort, where here in the beginning, this is again this quotient I talked about earlier of the two distances. We know basically the region of the lattice artifacts, which is always there, which suggests to you some kind of really lattice, where you see the discreteness of the lattice. And then we find something that we can map onto, again, a section of a sphere SFIT to S4. So definitely we see here that there is a positive curvature, Ricci scalar in this case, we have average over directions. What more we can do is we can compare this genuine Ricci curvature in time-like directions and space-like directions, because these can still be identified even if you have Wick rotated. So, and we see that they behave very similar, where you must know that the gap between these two is not a universal feature. So the slope is, the physics is in the slope here, and the slope is, almost identical. So it provides definitely further support for the interpretation of our emergent universe in terms of a de Sitter space. Again, of course, in the quantum sense, in the sense of expectation values, we have average over many things. Okay, that brings me to the very last page, an outlook. So important here was the message that properties of quantum gravity near L Planck are described by invariant quantum observables. There is significant progress on identifying and evaluating them, and they're of a particular kind, and they're non-local, and they're not very easy to work with. But nevertheless, I should say, one should, if one compares, different quantum gravity candidate theories, one should really look at what they get for observables, like the spectral dimension, and then compare, rather than comparing formalisms which can look extremely different in different theories. Now, relating such non-perturbative results to perturbative and semi-classical, say, early universe scenarios is really challenging. But this is, that's the nature of the beast. So, it's not easy to start with very non-local objects and, their average expectation values, and then try and compare them, say, with, de Sitter, quantum field theory on a curved background, early universe scenario. But I think on the positive side, coming from the standard semi-classical side, it will force us to focus more on the truly invariant properties of gravity. So not the stuff that actually is coordinate dependent. And we know also that this is challenging, also in cosmology. Now, the new scale dependent quantum Ricci curvature I've briefly described to you. I'm truly excited about it. It opens new ways to understanding quasi-local geometry of these quantum geometries, how they behave under coarse graining, and how they may hopefully approach some classical limit. They're also directionally dependent, so they are our kind of a tensorial quantities, although we are working in a completely non-smooth setting. And we are currently using them to understand the nature of a structure formation that we find beyond one of the second order phase transition in four-dimensional CDT. And that's work I'm doing with my postdoc, Clemente. There's lots of interesting things to do, but my time is truly up. So thank you very much for listening.
Okay, thank you, Renata, for this very interesting talk. Actually, we are out of time for questions. Just maybe one very fast question, I hope, from Tom. Ask to unmute you, Tom.
Yeah, I was waiting. You allow me. Okay, I hope it is very simple and very nice question. It's not my cup of tea, but assuming you will consider flat space, Minkowski space. I mean, your model of the space as some fluctuating space, right? Can you get from the flat space, Minkowski space, can you get some fluctuation of vacuum so that you will see some singularity which will grow up, will give origin of new universe or something like this? You understand me, right? Suddenly you are getting in your flat space some fluctuation which is spreading and creating more. Can you come to in your picture to something like this or not, please?
Well, so the rules of the game here are you are making a big quantum superposition, and you're looking for the ground state of that system, that whatever minimizes some effective action, that's behind this. And then you have to understand what its properties are. So it's clearly not, so this will be just maybe one geometry, right? The only thing I have to play around with are boundary conditions and choice of overall topology. So what seems to come out naturally here, at least for the sizes of universes we've studied, is a de Sitter space. Yeah, hopefully, at least some of the properties we could match on large scales to those of a de Sitter space. And of course, the de Sitter space is the more natural, of course, that is the natural state rather than Minkowski space in the presence of a positive cosmological constant. So yeah, but you must realize these are universes that are like 20 Planck lengths across. So it's clear, that they will not look like a flat or gently spaced, gently curved space with some little quantum fluctuations around it. That's not the regime. So this is really the deep quantum regime where quantum fluctuations are still very large.
Okay, I think if there is a reply, we have to postpone because we are really out of time. So thank you to Renata once again, and Giovanni can share the screen.
Here I am. Can you hear me?
Yes, yes.
Okay. And can you see the screen?
No.
No. Let's see. Here.
Okay, now you are
Yes.
sharing the screen.
Full screen. Okay.
Perfect. So, next speaker is Giovanni Acquaviva, and Giovanni, you can start.
Thank you. So thanks, Luca. Thanks to the organizers and all the participants. Very amazing talks. And the last one, so I will dive straight in. My talk is entitled From Exons to Black Holes, an Emergent Picture. So obviously, I will talk about some kind of emergent nature of the gravitational field. These are the main points of the talk. I will start with the main point, which is the Bekenstein bound and its importance in the hints that it can give us regarding quantum gravity, and in particular the emergent nature of gravity, as well as the fields propagating on the geometry. And I will highlight most of all an aspect which is very important in when one talks about Bekenstein bound and black holes, which is the page curve. The page curve is, let's say, is the way to understand if the process of evaporation of a black hole follows unitarity or not. So I will focus a lot on that and see how the emergent picture of gravity might have an impact on the page curve itself. Then I will pass on to a different point of view on the emergent picture and try to convey a derivation of the Bekenstein bound, so a bottom-up derivation of the Bekenstein bound, assuming Pauli principle for the fundamental degrees of freedom of quantum gravity. And if I will have time, I will comment also on further aspects like possible observational signatures of the emergent pictures and some important point that regards the possibility of phase transitions in this context. So let's start with the Bekenstein bound. Bekenstein bound, as many of you know, was formulated by Bekenstein at the beginning of the 80s. And it's an expression of an upper limit for the ratio between entropy and energy of a system and contained in a given volume. The form that I am writing here is like the spherical declination of the bound. So we have a radius which defines a spherical volume, and the ratio between the entropy and the energy contained in such a volume are bounded by this quantity. Such bound is, as you know, saturated by a black hole. In this case, in the case of a black hole, the bound is expressed in this way. So the entropy cannot exceed the Bekenstein entropy of a black hole, which has the same size of the system under consideration. And let's see a couple of consequences that can be drawn from the Bekenstein bound. One is the fact that if you take a system which is contained in a given volume and continue to add energy until a black hole forms, and then you try to excite even more the system by adding more energy, the effect would just be that the volume of the black hole will increase, so it will violate the bound as it is. So this led us and other authors as well to infer that the number of excitable degrees of freedom of a black hole is actually finite, and extrapolating to quantum gravity regime, one could say that the Hilbert space of quantum gravity is locally finite dimensional. This is actually one of the main points of the talk by Singh before. A second consequence that one could draw from this is that as the bound is not saturated by ordinary matter, but only when gravity becomes really relevant, the degrees of freedom that we are talking about in quantum gravity should account for both matter and geometry. So taking into account these two consequences of the Bekenstein bound, we espouse here a so-called quasi-particle picture, which means that both the geometry and the fields propagating on such geometry emerge from the same underlying constituents. So it can be schematically given in this picture, where we have a fundamental level where the fundamental degrees of freedom, which we call exons, live, and the states in such fundamental level do not distinguish between what is geometry and what is fields. And they are assumed to evolve unitarily. At the emergent level, we have different arrangements of the fundamental degrees of freedom of these exons, which can give rise to the emergent notions of geometry and fields. Of course, the question is how to map the states that are living in the fundamental level to the emergent level. So this kind of dynamical map should be given by a particular a specific theory of quantum gravity. So a note on the terminology here, the name that we use, exon, is actually was introduced by Feynman in his physics lectures, in particular in a chapter of electrostatic analogs, when he was wondering about why are the equations from different phenomena so similar. So it's Feynman's take on analogs that gives rise to this terminology of exons. And the approach itself that we are using in our work is actually inspired very much by the notions of quasi-particles in analog systems. So these are the two main assumptions that we use in our treatments, that these fundamental exons are fully excited only in a black hole state, which corresponds to the saturation of the Bekenstein bound. And that's evaporation, the process of evaporation of the black hole would correspond somehow to some kind of phase transition where the exons rearrange to form both the space-time and the fields propagating on it. So some consequences of this picture, for example, on black hole evaporation can be given. We have that different configurations of the exons at fundamental level can give rise to the same emergent geometry, macroscopic geometry, but yielding different numbers of degrees of freedom available for the fields. So in this scheme, we can see a certain geometry and field that collapses to form a black hole. We have the process of black hole evaporation, and without knowing how it will end, we can assume, for example, that the geometry, the previous geometry before the formation of the black hole is restored, but we obtain a different configuration of the fields where phi and phi prime live in different Hilbert spaces now. So the unitary evolution that we assume at the fundamental exon level entails a reshuffling of the degrees of freedom, which at the emergent level leads to an entanglement between the fields and the geometry. So let's see this picture from 2 points of view. We have, let's talk about first the loss of information and the paradoxical nature of the loss of information. So usually in semi-classical treatments of black hole evaporation, of course, geometry is not involved in the calculations of black hole evaporation. So this can lead to the problematic loss of information that happens in the matter sector. So one paradigmatic example of calculation in this sense is what Page calculated. He considered the entanglement entropy between two subsystems of the full system, a bipartite system comprising black hole on one side and the radiation on the other side. And the resulting curve, which is the well-known Page curve, shows unitary evolution, which means that the entropy, which is the entanglement entropy, which is initially 0, goes back to 0 at the end of the evaporation. So of course, the Page curve is now in the spotlight of many approaches. There are several derivations present in the literature, but it's unclear for us, at least, whether the theory of quantum gravity should actually cure the information loss or its paradoxical nature. So let's now see in a picture of emergence, how does the black hole evaporation work? First, at the emergent level. So we are considering a situation in which we already know the dynamical map, which leads from the fundamental level to the emergent level. And we consider at the fundamental level a splitting of the Hilbert space in subspaces, which yield specific distributions of degrees of freedom between geometry and fields. So there is the fundamental Hilbert space is decomposed in different what we call topologies, which is a specific distribution of degrees of freedom between gravity and the fields. We assume as well at the, let's say, at emergent level, the existence of a mass operator, which would give, which would characterize, let's say, the semi-classical geometry in terms of quantum states. And it allows to quantify, for example, for a black hole, the mass parameter of a black hole in a semi-classical treatment. And at the same time, on the field side, in the emergent sector, we define the usual number operator for the field. So any state in the fundamental Hilbert space of the exons can be expanded on the basis of states of the geometry and the fields in this way. And one can take a projection of this state on a specific distribution of degrees of freedom, a specific topology. So in order to obtain an entangled state of this kind, which is an entangled state of geometric and field modes, we can calculate the probability of finding a particular state in a specific topology. And we can define in this way a normalized state, which can give us, in the end, a reduced density matrix by tracing away the degrees of freedom of the geometry. We can have a reduced density matrix which describes the state, the specific state of the field. Through this reduced density matrix, we can calculate the von Neumann entanglement entropy, which would be the quantification of entanglement between geometry and fields for a given distribution of degrees of freedom between the two. And as a last step, as at the emergent level, we cannot distinguish between different topologies, which would be the different microstates of the system. We have to consider the expectation value of the von Neumann entanglement entropy. And in doing so, we can take a simple example in which there are only two possible distribution of degrees of freedom. Is a very, very naive example just to show how it works. there are two possible distribution of degrees of freedom between geometry and fields. We can fix the total dimension of the Hilbert space to be finite and model the emission during the evaporation in discrete quanta by imposing some expectation value for the number operator and the mass operator. In this way, we can calculate a page curve, which is shown in the figure. And it the main feature of this page curve is that while starting with 0 entanglement entropy, it ends with a non-zero entanglement entropy at the end of the evaporation. So this can be also generalized to more possible topologies, more possible microstates. When I talk about microstates, I mean microscopic configuration that give rise to the same emergent classical geometry. So the bigger the number of possible microstates, the bigger will be the deviation from unitarity at the emergent level. So this gives an idea of what could happen in an emergent picture with the assumptions stated. We can analyze the situation at the different level, at the fundamental level. So we want to calculate the same page curve in at the fundamental level, not at the emergent level. So what we assume at the fundamental level is that the system is described by a finite number of excitable quantum levels of slots that can be filled. Big N is the number, and that the fundamental axons are fermionic in nature. So these two assumptions ensure that the dimensionality of the Hilbert space is finite. And we described the situation as I expressed before. The black hole is composed by 3 axons, and the process of evaporation is a transition from a free phase to a bound phase where space-time and fields can emerge. So this can give us also an idea of a non-geometric notion of interior and exterior of the black hole, in the sense that in a quantum gravity regime, we don't expect geometry to be well-defined, to be defined, and so we wouldn't have a notion of interior of a black hole and exterior. In this sense, we express this difference by describing the black hole as the free phase of the axons and the environment as the bound phase. So in order to calculate our things, we make reference to thermofield dynamics. This is an expression of the thermal vacuum in thermofield dynamics, where in order to, where in thermofield dynamics, the usual procedure to make calculation is to double the degrees of freedom of the system in order to purify the system. And for example, the 2 copies of the system might be, for example, the left and right wedges in Minkowski spacetime that would allow to, for example, calculate the thermal effects of a Rindler observer. In this expression, this S in the exponent is the entropy operator of thermofield dynamics, which quantifies the entanglement entropy of the thermal vacuum. And in our case, the 2 copies of the system are the black hole and the environment as defined before. So we go on by defining our algebra of operators, of creation and annihilation operators for the fermionic degrees of freedom, where A and B stand for environment and black hole. And we define an initial state and a final state of the evaporation, where the initial state is given by all the slots occupied in the black hole, and the final state will be all the slots occupied in the environment.
10 minutes.
Yes, thank you. This is a very general expression of a state that interpolates between these initial and final state. It's an entangled state where the parameter sigma is just an interpolation parameter, and if we had a proper, let's say, dynamical map that would lead us to geometric notions and to an actual emergent geometry, sigma might be related to an evolution parameter or a time parameter. But for now, it's just an interpolation parameter. And so one can check that indeed we have a finite dimensional Hilbert space at this point. So we introduce, in the spirit of thermofield dynamics, the entropy operators given by these expressions. The entropy operators related to the black hole and the environment. One can show that their expectation values on the state defined before are equal, and they coincide both with the von Neumann entropy of the quantum state. So this is a plot of this expectation value of the entropy operator. It has a clear page-like behavior, which signals an unitary evolution, which is to be expected because at the fundamental level we assumed unitary evolution. The maximum of this curve is located at n log 2, which tells us it's related to actually the initial size of the black hole. This is actually an instance of the Bekenstein bound in this picture, obtained by assuming the finiteness and the fermionic nature of the fundamental degrees of freedom. So in order to see more clearly that it's related to the Bekenstein-Hawking entropy of the initial black hole, we can define the number of operators related to the black hole and the environment and their expectation value on the state. So we can, in the end, calculate separately the black hole and environment entropies, which are given in terms of the evolution parameter sigma, and plot all together the entropies obtained. We can see that the previous curve, the page curve that we calculated before, has a maximum which coincides exactly with the initial black hole entropy. The black hole entropy during the evolution decreases to 0, while the environment entropy increases monotonically. These three entropies satisfy this inequality. We have this resulting inequality where the entanglement entropy, the von Neumann entropy, is always lower or at most equal to the maximal entropy of the system. The unitary evolution is given because, of course, at exon level, there is no coarse graining, as we instead showed in the previous section for the emergent level. So we can also extract from this picture some observational possibility of testing these kind of theories. So by assuming quantization of the black hole area as Bekenstein did in terms of the Planck length squared with an unknown factor of proportionality, we can get the Bekenstein-Hawking entropy can be expressed in terms of this parameter alpha and the number of, let's say, slots, quantum slots related to the area of the black hole. According to our model, we initially have black hole entropy of n log 2, so that we can obtain a parameter alpha of 4 log 2. This parameter alpha is interesting because can be related to the discrete spectrum of quasi-normal modes of black holes, and it can be, in fact, constrained by future binary mergers observation. So it would be interesting to have a feedback from observations that can tell us something directly on these kind of models. And I'm concluding here my talk. Thank you for the attention.
So thank you, Giovanni, for your talk, and you have a lot of time left because you spend 26 minutes for your contribution. So is there any question? In the audience? Okay, there is a question from Luca Buoninfante.
Yeah, hi. Nice talk, thank you. So I have a question. I don't know if I understood correctly. You mentioned both the Bekenstein bound and the area law, basically entropy, Bekenstein entropy. But at least from the model, what I can see is that basically, since the number of states is given by 2 to the n, the entropy will be just proportional to n. So I really don't see why this n should be related to some kind of area or to some kind of energy times radius. Does it come from your model?
I didn't understand exactly the point you're referring to.
No, basically the entropy that you show for your system is basically given by the number. So it's given by, so the number of states of your Hilbert space is 2 to the n, right? Okay. So basically the entropy will be just the logarithm of this, or 2 to the n. Okay, so basically you get entropy equal to n times logarithm of 2. Yeah, right, this formula.
Yes.
Okay. So why do you call this, why do you say that this entropy is saturating the Bekenstein bound?
So this n log 2 would be the dimensionality of the state of the Hilbert space, which is, for instance, the initial state. If you consider the initial state of the system, which is the black hole, the full black hole before evaporation, this would, if we had, let's say, a geometric notion ready available for this model, one could relate this dimensionality to the actual area of the initial black hole.
Oh, that's understand. But for instance, if I just take a fermionic model, where there is in principle no notion of like radius or energy or area. I mean, I don't understand why you are saturating a Bekenstein bound in this model. I mean, at least, I mean, it doesn't come from the computation, right? What is happening is that basically the entropy is given by the logarithm of the number of states.
Yes.
That's the only thing that comes out.
Yes.
So I think to show that you're saturating the Bekenstein bound, you need to define first a notion of local, I mean, a size for the system, an energy for the system, and so on.
Yes.
Yeah,
but
so,
this shows that, for instance, the maximum of the entanglement entropy that one can have does not exceed the initial entropy of the system, which might be related, geometrically speaking, to the black hole the Bekenstein-Hawking.
Oh, no, I totally give that, but I think that the fact that you are saturating the bound is just an assumption, right? You are assuming, I mean, you're not proving that in the end.
Yes.
Because it's not even needed in your analysis, actually. You just have like some entropy given by n, that's it.
Yes.
Which in principle, if you do an analogy with black hole, it would correspond to the area, but
yes,
this is an analogy. It's not,
yes, okay. Yes, it needs some more step, but yes.
Thank you.
So we have a question from Sugato.
Yes.
Let's unmute.
Hi.
Hello.
Hello. I'm just wondering, so maybe my question is very similar to Luca's question in some sense. So if you take any two quantum systems, finite dimensional, qubits, yeah, you will always have a curve like this, right? So is it the only gravity assumption is that you assume that the Bekenstein bound you have, translated to here in this setting, right? Mm-hmm. Otherwise, so only gravity ingredient is coming from this Bekenstein bound. Is that right?
Sorry, the last question.
The only ingredient you're bringing in from gravity is just that the Bekenstein bound, right? Mm-hmm. You're borrowing that in. Otherwise, it's just two quantum d-dimensional systems. Yeah, so whose entropy will grow and decrease as as is for any quantum systems.
Yeah, this is actually the point is that in this second part of the talk, where the treatment doesn't assume the Bekenstein bound, but assumes the finiteness of the dimensionality of the Hilbert space, the fermionic nature of the degrees of freedom. And it shows that only by these assumptions one can have a page-like curve, for example, a behavior like that, which can lead to the Bekenstein bound.
Right. Yeah. So I would say that, this is not very surprising. You have two quantum systems, d-dimensional, of course they will form the page curve. I think people, when they assume a non-quantum system and with the horizon, then of course
yes, it's quite simple in the end. Okay. It's nothing very complicated, and it's if one takes. Our idea was to start first with the consequences of the Bekenstein bound, and then try to understand how the Bekenstein bound can arise. And of course, that it's not very surprising a posteriori that something like that happens with the fermionic system. But it happens. I mean, if you take into account bosonic degrees of freedom, you will not obtain a page curve. You will obtain a monotonically increasing.
In your setting, okay. So that is interesting. So it's not just finiteness of Hilbert space. You also do not want the states to be occupied by arbitrary numbers.
Yeah, because otherwise you can pile up an infinite amount of bosonic states. So the fermionic nature seems quite important in this sense.
Okay, and when you have this separable Hilbert space, in the sense that you wrote as a product of separable Hilbert spaces, right? The two things, the geometry part and the scalar field part, right? So, by geometry, do you also mean the free gravity part? Because then, the masses and the gravity they source are not always regarded as, I mean, you cannot do a separate Hilbert space for them.
Yes. No, actually, when we talk about the geometric sector and the field sector is a very rough language that needs to be refined, because we don't have a specific model of emergence, first of all, so we don't actually emerge a geometry and the fields propagating on it. The idea would be to we can extend this idea with the notion of the fermionic degrees of freedom we were talking about before. If we imagine at the fundamental level, quantum gravity level, if the degrees of freedom are fermionic in order to comply with the Bekenstein bound, then one can imagine a mechanism of emergence in which also a bosonization of these fermions occurs.
Okay.
So the bosonic part of the emergence would, let's say, in some sense, take care of the interactions, including
Okay. So fundamentally, they're only fermions, and then
these kind of things. But these are all.
Okay.
These are
Thank you for the moment. Yeah. Thanks.
I think that we are out of time a little bit for discussion, so for questions, and so we can start the discussion. So go on and share the screen. And we have a question from Alexander Wickman, before he's still here, to Carlo Rovelli. Alex, are you still here?
I'm here.
Okay.
I guess I'm muted now.
We don't have the questionnaire. So we had another question from Sugato Bose. So
that was an easy to answer, the first one.
Yes.
Hi, Carlo. How are you?
Hi, Sugato. Pleasure to see you.
Yeah. Great talk. Okay. Can I ask you? So of course, I'm a complete outsider. So I want to understand what gave that tunneling matrix element. Is that the kinetic energy of the particles falling in? Like,
can you repeat the main sentence? What?
So what gave you the tunneling matrix element between the black hole and the white hole? So is that the energy of the particles which are there in the center, the mass? I mean, is it the kinetic energy of the masses? I mean, what is the tunneling matrix element?
Yeah. So right. I mean, you are the one who is going to test quantum mechanics first in the planet. But you're not a quantum gravity person.
No.
So quantum gravity theory is not your life experience.
No.
So yes, it's a standard. The answer is partially yes, partially no. So it's a standard tunneling. So there's a standard sort of evolution operator that evolved from an initial state to a final state. In usual quantum mechanics, the evolution operator will be just the exponential of the Hamiltonian, so e to the IHT. So it's the analog of that. However, it's not exactly that, because in gravity, the Hamiltonian, you don't really have an Hamiltonian. You have an Hamiltonian constraint. So it's you cannot write in that form unless you choose rather arbitrarily a proper time parameter. So it's one way of viewing it is to think about path integral. And so then it's really that. So you have the initial configuration, the final configuration, and the matrix element are given as a function of the initial configuration, the function of the final configuration by the path integral over the exponential of the action, I over h bar of the action. So it's the analog of that. So so up to this, peculiarity about the fact that the time variable get mixed with the other variables, it's a standard tunneling transition.
And this region that you had, the B, small b region in the side, right? So is that, so when this again, I may be viewing tunneling in a very different way than it is usually already. But so obviously, when you go from one state to another, you go through a superposition, being there, and then you finally reach the. So there is in that way. I mean, if it's like a Rabi oscillation kind of thing, there's a tunneling time. But of course, if it's an incoherent tunneling because lots of environment is there from whatever the Hawking radiation or other, it could be an incoherent tunneling at a random time.
Please, sorry.
Yes, so what I was wondering is during the tunneling, is there something significant happen? Like, would like a gravitational wave be emitted from that small blue region or something like that? Like evidence that this blue region, the B region, is undergoing some kind of transition. Like, would it create a superposition of curvatures temporarily, and that would go away?
Yes. So it's tunneling. So if you think about standard tunneling, when I think about standard tunneling, I think theoretically, like particle can go to a wall, or I can think as a radioactive decay of a nucleus, which is a quintessential tunneling phenomenon. So if you think in terms of Schrödinger evolution, you don't get to a classical state. You get a superposition of states, of course. So that would be the same. So in fact, what we expect is a superposition of states. But the world is macroscopic.
Right.
So immediately we think. I mean, whatever is your view of quantum mechanics, doesn't matter which. You think there's decoherence, and you only see one.
Okay.
So what is really going on is that we assume decoherence, if you want, or we use Copenhagen projected on one outcome, which means that we go from a classical to a classical. Like the alpha particle from a nucleus, just one at one specific time. So the actual thing will be a superposition of times, in fact. Now, to the second part of your question, yes, the parameter on which the amplitude depends can be viewed as as the time at which the nucleus emits the alpha particle. So the probability we give the probability per time, so to say, and plus there is a transition time itself. If you think of the particle going through a wall, you can think the time it takes to go from a classical configuration one side to a classical configuration one side. So there's a transition time. And yes, of course, there is an excitement of a gravitational wave or whatever, but that's negligible. Remember, this is a small region of space-time that goes to a small modification, which has a consequence only on the long term, so to say, because if it was a classical evolution, the horizon would remain an horizon forever. This stops it from being an horizon. So from being a trapping horizon, it makes it an anti-trapping horizon. So it's a small change in a component of the metric. But it has effect of freeing is inside, and things can come.
Right.
That's the physics.
Okay, thank you.
So then now we have Alexander, so you can do your question.
Yeah. Carla, great to see you, and thanks for very nice talk.
Thank you.
I'm a bit puzzled because it seems that your white holes would be more stable, parametrically more stable than black holes, right? As the white hole decay time was m⁴, whereas the black hole is m⁵. So it's a bit paradoxical, right, to think that the object which tries to emit everything and which is unstable looks actually much more stable than normal black hole, which should absorb everything. It's one question, and second question is, as far as I remember, I have already asked you once, because this picture, what you present, is very nice, but severely depends on kind of extrapolating Schwarzschild interior, right? Which is not unique, which would depend on history of formation, and which actually is not properly spherically symmetric as far as I can understand. But you definitely thought about this more since we talked last time. So what is the status now?
Yeah, so it's two questions. First, about the stability of the remnant of the white hole. You're right. So by itself, a white hole, first of all, it's as an instability. Macroscopic white hole is an instability, and then what determines its long life? The point here is that the physics of the interior, it's relevant. So the future of a white hole does not depend only on its horizon. It depends on the inside, which is pretty obvious because it's a white hole. So
of course.
So a white hole with a small inside ends rapidly, but a white hole with a very long inside, let me give you the intuition, it takes a long time before evolving.
So it's a memory effect in a sense.
It's a memory effect. And if you think about a white hole as a time reverse to the black hole, which is no natural way of saying it, it sort of makes sense because, you know, to produce a black hole, if a star collapsed, the inside is small. If you wait a long time, a long outside time, just think of the penalty, right, where the interior grows. So if you want to go back, reverse, it depends how long how big is the interior before you can emit everything. So that's a question about the stability. There is another point, which is that the throat of the area of the white hole, if it is Planckian, it's very stable because it's Planckian. So it cannot become small, and you have to weight the. So that's the question. That's your first question. Your second question is what I'm actually working now about, and especially what mostly disturbed me in all the story is that it was all Schwarzschild, and so usual question, right? Is are we being blinded by doing something enormously symmetric and reality is completely different? It was a worry from day one. So right now I'm making a first step and doing Kerr.
Great.
It already is a bit better. I mean, the reality is not Kerr either because, you know, things inside get messed up. And in fact, we know that Kerr has instability, strong instability. But we're doing Kerr. This is a step ahead. And we haven't published anything. We have calculations. We should be publishing something soon, but let me anticipate something. It seems that the Kerr actually dramatically simplifies the story. It makes it simpler. We struggled a lot. And the reason is, if you're familiar with the Penrose diagram of maximally extended Kerr, you can go classically, fully classically, from one asymptotic region inside Kerr, you know, past the outer horizon, and then go out classically to the other
absolutely
universe. So now, if you believe that the B region, the same thing happened, you can have the transition of the B region without need to have a quantum transition inside. Just the Einstein equation tell you that you can go out. You can go in a black hole, find yourself in an anti-trapedy region, and go out on horizon. Just the Einstein equation is telling you that. Of course, the Einstein equation tell you that if the horizon is an event horizon, you end up in a different universe. You need a different universe to end up. If there's a transition of the horizon, the three problem, the ABC problem, the A problem, which is the one is neither the star nor the horizon, is solved classically. You don't even need quantum mechanics there. So it seems to be even better, the story with Kerr.
But what do you do with the Cauchy horizon, with this mass inflation and all these things? With instability?
The instability, the Kerr instability.
Inside, yes.
I have no idea. And in fact, one thing I would like to try to understand is the relation between the instability and the onset of quantum gravity. So, I mean, it's instability before going to Planckian curvature after, I don't know. I haven't decided yet.
Yeah,
But,
no, of course,
but
it's
if
an
you want,
infinitely harder
I
problem.
wish quantum gravity people studied this kind of problems. I mean, really what happened to space-time.
Absolutely, absolutely. Thanks a lot, and great to see you again.
Thank you, thank you. Great to see you again. Yeah.
So I think there is a next comment is from Tom. I don't know.
Yeah, it's a question to Carlo Rovelli. I mean, as you mentioned, I mean, to some of my previous question, I mean, it was not his cup of tea, but that's the same as for me. What you are doing, it's far from my business. Still, I mean, if I understood you correctly, you said that close to horizon, there is no reason to, I mean, to believe in any classical description of gravity, because there the quantum gravity effects start to play the role. So if this is correct, if I correctly understood you, then I would like to ask you, what is your view on analogy, which, I mean, there recently were published analogies in the lab that you can study the evaporation of the, let's say, analogy of quantum, analogy of black hole, right? So if it's like this, you are saying that this is what was observed, or what people claim they saw in lab is not what you are describing, because the equations will be completely different. The space will have a completely different structure than with respect to what they got in lab. So this is my question first, but it's all based on assumption that I got correctly what you said about space close to horizon. There's no way to describe it classically. Yeah, please. I will continue, but I hope they will not mute me again. Yeah, please.
Yeah, thank you, Tom. No, I think I probably was not clear, but it's good that you asked this question, so it allows me to clarify it a bit better. I expect that near the horizon, everything is classical. In fact, I expect that near the horizon, there is no firewalls, so there's nothing funny happening. I mean, I expect that near the horizon of a normal macroscopic black hole, it's a classical general relativity, it's completely reliable, and quantum field theory doesn't do anything very dramatic there, unless you yourself use particular reference frames which are crazy. So that's not what I meant. What I said that if Hawking radiation is true, which we expect, when the black hole shrinks, it becomes smaller, 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 smaller. At some point, it becomes nearly Planckian. At that point, and only at that point, quantum gravity becomes relevant outside the horizon.
Okay, so at the end, basically, at the end of the evaporation. That's
at the end of the evaporation, and this implies a consequence of that is that the horizon has no reason to be an event horizon, because from now on, things are quantum gravity. And so you have to do something to understand what happened. So we cannot rely, we can rely on general relativity, classical general relativity outside the horizon as long as it's big horizon, but we cannot rely on general relativity in telling us that this is an event horizon.
Okay, thanks. I think the rest of questions are clarified. Thank you very much.
Thank you, Tom.
Thank you very much. Okay, now there's a question from me, and it says, I raised the hand, so you cannot say I used the priority of the chairman. And I wanted to add a comment to what Giovanni was saying before, to Luca and Sogato, to the questions of Luca and Sogato. What's the role really of gravity and of Bekenstein bound on that quite abstract picture? It's true that in that model, there's no clearly notion of space-time, because Giovanni clearly said at some point that space-time and matter should emerge. Clearly, we cannot directly connect with the notion of area, for example. Even the notion of interior and exterior of black hole should emerge, and it's defined in terms of free accents, so free fundamental mode, bounded accents, so bound fundamental mode, so interacting in a way to form space-time and matter. So this quasi-particle picture, which is, as Giovanni suggested, is described by, he suggested at least from analog models of gravity. Now, The Bekenstein bound enters in an important way when in the assumptions, in particular, of the model, because which was described very much longer from in the Singh talk before. The point is that every local quantum system should have a finite number of degrees of freedom. And this is very strong assumption. You say in the usual derivation of Bekenstein bound, think to Cassini, for example. This is done in quantum field theory in system with an infinite number of degrees of freedom. And this is not implemented, but typically you put some cutoff on so on. Even when you try to derive, for example, holographic bounds from Bose gas or Fermi gas, this was done, or from more exotic infinite statistic gas, for example. And in that case, it's proved you obtain a really genuine holographic kind of bound. You typically assume some cutoff. Okay, you assume that you cannot exceed the number of your excited mode cannot exceed the some level which is defined by the condition that otherwise the mode should collapse into a black hole if you have too many modes in a small region. That's the point. So this is a very drastic way of doing. We don't have any cutoff, anything, and so we cannot assume we have bosonic nature of otherwise. And the other point is about the identification that Giovanni was saying before, is that not only we argue in that model that the maximum entropy reached by the system, and you can say, okay, it's quite trivial bound in the sense that everything there are the actions that fill the black holes. There is nothing else in the universe in this very, very simplified model. So all the universe is the black hole and what you have after evaporation of black hole. Okay. But in that case, this is the maximum entropy. But we managed to give a notion of Bekenstein-Hawking entropy in a sense of decreasing black hole entropy, monotonically decreasing black hole entropy, which is very similar to original by Don Page, which just one consideration. Also in the original Page paper, there's no black hole physics in a sense. You can apply to every bipartite system, that kind of considerations. There is nothing. It says, okay, this is the dimension of the Hilbert space is E2 black hole entropy. Okay, is the conceptual idea there. So we managed to define a black hole monotonically decreasing entropy and to prove, and this is not put by hand from the beginning, that the entropy of the initial state of black hole is exactly the maximum entropy reached available to the system. So another point where really notion of area geometry enters is at the end, when Giovanni showed that you can do some kind of prediction about the ratio of element of area and the square of Planck length. At that point, you impose clearly the equality with usual Bekenstein-Hawking entropy, but this model permits is very simplified model. It's a toy model and so on. We have already notion of how this rearrangement comes, of how the dynamics works, but this gives a prediction about the factor which can be measured from quasi-normal modes. In that case, enters a geometric notion of in the game, but Bekenstein bound is always there behind conceptually in this idea that fundamentally the nature should be described by locally finite dimensional Hilbert spaces, and this is, I think, quite drastic and not very present in literature. Luca has a comment.
No, but just to clarify what I was saying. So the fact that you're deriving the Page curve, okay, so you're considering just a Fermionic system, which is a quantum system. The fact that you are deriving the Page curve has nothing to do with the fact that your system may or may not saturate some Bekenstein bound. Okay. Indeed, I think you cannot show that, because what you are saying is that you have an
No. We show, because if you see
let me finish. You have an Hilbert space which is given by dimension 2 to the n, and the entropy of this Hilbert space will be logarithm of 2 times n. Okay, that's what you get. Now, what you show is that basically you get this curve, and I mean you just fall from basically your quantum, the fact that you have a quantum system that is unitarity, maybe, I don't know, but in the end, the fact that the system does saturate or not this bound, it doesn't matter. The important thing is that, as you said, in principle you should satisfy this bound but not saturate. Okay, and of course you have a finite entropy, but there are many systems with finite entropy which satisfy the bound, but they don't need to saturate the bound. So I don't know why you're saying that your system saturates the Bekenstein bound. You cannot even define the upper limit of the Bekenstein bound in your case.
No. We define even the environmental entropy. I told you, all matter must respect the Bekenstein bound, while the black holes.
But you have no black hole. You have a fermionic system. Okay, you have a fermionic system.
Sure.
And you have some entropy. This n is given by n. That's it. Okay. Now, why? I don't see why you need first, and how you are showing that this n is equal to some energy times some localization radius. Okay, because you don't have those quantities anyway. And
no. Apart that, we have in mind mostly an holographic.
No. But this is the analogy that you do. Yeah. Just an analogy.
Perhaps I may add one word. Sorry, Luca Buoninfante is right in the sense of the proper Bekenstein bound is never been shown there. I mean, the Bekenstein bound is the first equation that Giovanni has presented with R and E. We do not have any R. We have no distance yet in there. It's a game played entirely in terms of these exons. And so we even made an effort of defining interior, exterior in terms of interior is where the exons live free, exterior is where they are not free anymore, because when they actually get outside, okay, they make, and so that curve, the red curve, is how exons would perceive their let me say, evaporation. And the beauty of that story is that all three curves, which are usually coming from different origins, the Bekenstein entropy would do this and would decrease. Then the environment or thermodynamical entropy would go up. And then you have the space curve, which usually, if you remember the thing that Giovanni showed, is down below. Okay, it's this anorexic hypothesis. I never remember the name of that thing. Okay, which is something, and somehow we go up until the up above, and the fact that we hit that maximum is what we claim. I'm going to say no, we don't claim. We show to be the maximum of the curve is equivalent, is equal to the Bekenstein original thing, and so we say this is how in our system we show the bound. We should be careful with wording there, because Bekenstein bound is what Luca Buoninfante is saying. Is S is less than or equal than R, E, and that expression. We don't have that in that sense. In this sense, you're right. But also, it is not just a simple bipartite system that goes up and down and you expect this to be. It's a bit more than that. Okay, so we are a step behind having a distance, but a bit farther up. Towards hitting a bound, and that's why we get into fermions in the first place, because otherwise the thing would go indefinitely. I don't know if I made things more confused.
I understand your point, but indeed, I mean, I don't see in principle, I don't see any relation between like saturating the Bekenstein bound and having some behavior in the curve that you mentioned. Okay.
The word not to use here is saturation.
Yeah, indeed.
You don't have to use the word saturation. If you don't use it, then we agree. If we agree,
but that's the point, because you are saying that you are basically showing the back. You are because in the case of black hole, you saturate the bound for a Schwarzschild black hole, for instance.
It's in our hypothesis. We work with that. We start from that.
If there's an hypothesis, I'm fine with that. No problem.
But we reobtain, because I mean the thing started before in the first paper with Scholz and Giovanni again. We had that other picture. Okay, that was essentially the emergent point of view. from this fundamental degrees of freedom rearrange, and they form what geometry and fields. Okay. But then we want to see how, and we suppose that there will be some fundamental dynamics, and we didn't know. I mean, what this dynamics could be, and we found out then with Luca and Giovanni again that if you suppose this fermionic nature, okay, you have this very natural thermofield dynamic light description where there are all the three entropies, which usually are, we sort of unify this description of the three of them, and the entropy goes up and down like in the page card. Okay, that's.
But then nothing against the quantum models you consider. It's totally fine. Indeed, no problem. It's just that, I mean, you don't need to make any assumption about the Bekenstein bound. Of course, you have a finite entropy. You need a finite entropy. But this is just the assumption that your Hilbert space is finite. That's it.
But the question was, how can you get a maximum finite entropy? That's the point. With bosonic fundamental degrees of freedom, you cannot do with
sure. I understand.
That's the point.
Your assumption, but which has nothing to do with, like, for instance, Bekenstein bound. I mean, just you have a finite entropy, and you can work with it. That's it.
No, because you have to also compare with to the black hole and to the environmental entropy. You see, it's the comparison of the free cards.
Sorry, no black hole. You have no black hole. You have just a fermionic system. Then you want
to do the moderators got into the discussion. Someone outside should tell them.
Okay, in fact, maybe we can give space.
You cannot go on forever.
Space to other questions. For the moment, are there other questions?
We cannot hear Carlo.
If there's no other question, I have a question. I don't want to jump over, but if there's nothing else.
No. Please do the question because we give space for other discussions.
Well, let me somehow. I in my presentation and in presentation Alessandro, there was a remarkable disagreement. I would like to just get your view of that, because I follow the presentation. Of course, it's all right and it's all interesting, and the model shows what it shows, and but the logic which I question, and I would like to know an answer to that, not for being polemical, just for doing science, is well, there is something interesting in the black hole entropy, which suggested to Bekenstein a certain generalization. Okay, now let's leave it and let's take it as a law of nature and see how it could come out, even when it applied to concrete situation, it gives results that conflict dramatically with the physics that we know. I mean, there are theorems like the Marolf and company theorem, the firewall theorem, that imply that if these assumptions is right, then the physics that we know is wrong. It seems to me that the logic of science indicates that this assumption is wrong. I mean, there is obviously something holographic in the world in that sense, but not in that sense. In some sense, but not in that sense. So why focusing on this Bekenstein bound and the idea that the number of states of a black hole must be bounded by its area, as if it was a God-given thing? I don't understand the general scientific logic here. I do understand that there are beautiful models one can do of that, and one can invent, hypotheses on the basis of that, but they're all hypotheses based on another hypothesis. Is that science? I mean, we should do the other way around. We should test out the hypothesis if they conflict dramatically with what we think. If that hypothesis is correct, okay, in a huge macroscopic black hole, I approach the horizon and I burn when I enter the horizon. Is anybody really believing that?
Who wants to reply?
I can start to reply. So it is not taken as a God's law. It is using logic. So you have to hook somewhere. Yesterday we had Juan Maldacena, Almairi, and Hong Liu, and other people hooking very much the page car. Okay, so we are taking that seriously and say, okay, can we actually reproduce this curve somehow? What is the core of the curve? What is coming from? Okay, so this is what we're doing. We are taking that as an hypothesis. We don't say it's a law of nature. We say that if this is true, and there are many, respectable colleagues who posit this idea, what are the implications? We found in the first paper, especially, the one implication apparently was a little bit overlooked. Or someone may have it out there, and we are among great experts of this area, from Renate Lolle, yourself, and Jorge Zanelli, many people. So I'm not claiming that this is the way, but looking at the Begistein bound, holography is not that important for us, as you may have understood. We never used any area there. We never used the fact that you have to go ADS, CFT, nothing. We said it's a bound. What captured our idea was the fact that it's a bound, it's a limitation. And there are interpretations of these that leads to a finite number of degrees of freedom. If those are the finite number of degrees of freedom that are reached because you saturate the bound, then it came natural to us to think that these degrees of freedom should make everything. So, okay, this goes on the line of emerging gravity, emerging everything, and so on and so forth. These are the if you like, Giovanni tried to say that at some point in his presentation. The motivation came from a very physical thing, which is this quasi-particle picture of condensed matter. In that area, we learned that the same object staying on a certain lattice behaves very, very differently from being in another lattice. An electron can become massless and quasi-relativistic and lose all its standard properties. So all this stuff built up this idea, okay, that if you merge all together and you have the quasi-particle pictures, it stems from this condensed matter physics thing. So that's what we did. So essentially, in both papers that Giovanni has been summarized in his talk, we've been using some implication logic. If this is true, what are the implications? I think that this is theoretical physics.
And moreover, we also, as Giovanni showed, we also showed a number. We'll say that
we even made a prediction with this very simple, exactly. We even made a prediction. If you a number, this could be used in some experiments. Okay, so we really like to land over experiments at some stage. We really are looking into that. We don't like to stay in this hypothetical world for long. But this is just a series of logic steps that we took. If this is true, then this should be true, then this should be true. And we came up with this idea.
So you were asking, is this science? I would say science is, I do a model trying to explain how it works. I find some numbers and I do measurements. I see if is an agreement, it works.
No, I think I understand. I mean, it was a little bit provocative, but I understand I understand the question of Carlo.
No, I think the question from Carlo was also. Like,
excuse me, but I want to add one word. I understand this point because this is also our point somehow. We are looking for something to hook at in a world, this quantum gravity world, where, as I said yesterday, Maldacena and collaborators were hooking very much on the page card, as that was the physical thing to reproduce. We're not taking that view yet. I mean, we're just trying to use logic steps. If this is true, if the community takes this as a fundamental principle, because that's a principle, it's not proved, what are the consequences? Okay, so this is the logic we're trying to use.
No, just a few seconds. No, say, maybe what also Carlo was saying is that if you make the assumption, you have a paradox. Otherwise, you have no paradox. So why we should worry about that? I mean, of course, I'm making an assumption. So in principle, we are creating the problem with more assumptions. So
I don't think there are many assumptions in this context. You know, there are much more assumption in other models, I would say. Okay, maybe much more complicated and so on, also more predictive. I don't know. But there are much more assumptions in other areas. So that's the point. We do one assumption. We try to find consequences. Okay, we can get a number. Can we compare with experiments?
We don't do the assumption. We take the assumption from the community. It's not our assumption.
Yeah, okay.
We just follow the implication.
True, but
we follow the logical implication of that assumption. That's what we do. And I think that that's pretty much science.
And moreover, if I can add, the model Giovanni didn't show, but the model has also some other nice implication. He pointed out this similarity with thermofield dynamics, and who knows thermofield dynamics said, okay, but that state is not very similar to like thermal vacuum or something like that. This is actually not true, because this is completely surprisingly appeared that state is actually a thermofield vacuum in a sense, a finite dimensional version of thermofield vacuum, I would say. And which gives a view of black hole evaporation, which is very similar to what Israel, for example, found, or the original Hawking idea of pair formation. So it seems at least is logically consistent. You know, then we do some predictions, and we have to see. We don't know if it works or not. Clearly, this is science. So we have some comments from Tom. Tom, are you there?
Yes, I'm here, and I have always problem to unmute. Sorry for this, but I'm not sure. I don't know. I mean, my question is to Madame Law. So maybe the question of Carlo Rovelli was not answered. I don't know. Simply, I'm not convinced that the answer was given. But fine.
We tried, and we can also continue.
Okay, but I don't know if he was satisfied. That's yeah. Okay. So still to Madame Law. I mean, I apologize to repeat my question, but I'm sorry. I'm really. I mean, my picture is that I have I mean, let's say space which is just without matter. There is just vacuum. Okay. And the picture is that suddenly, by fluctuation of vacuum, something is changing in this space. I mean, the vacuum is going to different state, yeah, suddenly. So my question, sorry for repeating it, but I was thinking whether you answered me, and I apologize, I did not get at the end. I mean, I understood probably what you told me, but I'm not happy with this. So, do you think there is a chance that in your description, I would consider really flat space with a fluctuation described as in your terminology, right? And suddenly, due to some fluctuation, I will build a seat somewhere in the space, so it will be spontaneously breaking this simple Minkowski or whatsoever space, and I will get a phase transition or something like this. In your description, because you mentioned, but I have no idea when you mentioned phase transition what it really means. But that was my question. It's very naive, I admit, but can you please give me an hint if?
Yeah, let me try and get us on the same page, so we understand what the other person is saying. You're a particle physicist, right? So let me make the analogy. So what I'm looking for is kind of the vacuum of the theory. Yeah. So this is like trying to find you know, the ground state, non-perturbative ground state of QCD, you know, as people do using lattice. I'm doing something similar for gravity. And I'm asking myself, what is the nature of this ground state? And our understanding so far is that it's definitely not, certainly microscopically, it's not Minkowski space, and it's certainly also not de Sitter space. But microscopically, it seems to be something extremely quantum fluctuating with properties we are interested in, because that is what, you know, the theory of quantum gravity should tell us. Of course, we are interested in phenomenology, but if you're asking, you know, well, there are various things one can ask. So I'm just trying to interpret something into your question. You know, can I understand some phenomenology of this? And is that given to me in terms of fluctuations around a background I know? Well, I would say this fluctuation picture is quite appropriate for in perturbative quantum gravity. So that would be at much lower energy scales, right? Where we treat, you know, gravitonic excitations just as small fluctuations around a background. And we know that this makes perfect sense if we don't go to energies that are too large. We're just treating quantum gravity as an effective field theory, you know, that's valid below some energy scale. So that's not what one, you know, what people like myself are trying to do. We are, on the contrary, we are trying to go beyond perturbations here, and we are asking, you know, what is a non-perturbative, you know, vacuum ground state? And so you don't have any choice, you know, what comes out of your construction, you know, if you believe your construction, but we are constructing, we have more statistical models where we're just using superposition principle. We allow quantum fluctuation of geometry to be very large. And then we are asking, hey, what comes out of this? What are the properties of, you know, this?
So sorry for interrupting you.
Yes.
You said the word, you are using superposition. That's a little bit surprising for me. I mean, this is highly nonlinear, right? What you are doing.
No, it's a path integral. I mean a path integral. You know, Feynman's path integral. That's a superposition. That's what I mean.
Oh no, okay, fine, but that's okay. So this is just wording, but so there is it's non-linear what you are doing, definitely. So you're not putting. I mean, okay, fine. So
yeah, definitely, it's going beyond just a quadratic approximation.
Yeah, exactly. Yeah. So, my question is still, I mean, I'm not asking if you are solving a problem of our universe, but I mean, a real universe. But my question is, if you have your model, imagine that you created model on which you are testing. You are taking lattice, yeah, but you have a different structure of this lattice. It's a causal, what you introduce, I mean, to overcome some problems. So I assume you are changing the your lattice itself is fluctuating, so it's dynamical system. Yeah, exactly. So that's what is in my mind. So my question is whether within this model you see, I mean, as a simple model, not real. I mean, but if you see some such behavior in your model, that you are starting with something simple and you suddenly get something unpredictable. I mean, not predictable easily, not calculable, because it's not perturbative, right? As you are not able to find a superconductivity, you would not solve, I mean, perturbatively. So something like you cannot easily calculate. So some states will get will win, let's say, in your model, and you see the phase transition in your model. So basically, you see that due to this fluctuation which appear somewhere, full universe, your grid changed, and you have a completely different picture. That was my question. So yeah, you understand me now? Okay.
Yes, I understand. So the answer is yes. So you're superposing kind of four-dimensional curved spacetimes. Okay, you know, they're kind of triangulated, but at each of those, you have a good understanding. You know, they look just, if you look locally, like just a curved four-dimensional space. So, but then you do this indeed, this superposition, right? And then you end up in a very, depending on how you tune your backcoupling constant, you end up in a very non-perturbative regime that indeed the typical, you know, geometry you find there is very, very far away from a nice classical solution to the Einstein equations. So how do we see that and understand that? Well, only by looking at observables. And for instance, one of the observables I mentioned in passing is the dimension of space-time. Yeah? So we understand there are various ways of measuring the dimension of this quantum space-time that comes out of it. And one of them is the spectral dimension, and you find bizarrely that if you evaluate it in this Planckian regime, it seems to come out as 2. Yeah, so that's totally unexpected and not, you know, you cannot really explain it by perturbation theory that the dimension of your space-time all of a sudden is no longer 4. So that's a good example of a very strongly non-perturbative effect that comes out of this. But if you then look at the same quantum universe you zoom out by a factor of 10 only, then you find that this dimension, you know, goes toward 4, which again is nice because you are interested in a classical limit. You want to connect, of course, in the end, you know, in a suitable large limit. You want to connect even to classical GR.
Okay, thank you very much. I will note this. I mean, thank you. I will have a look in your papers, and thank you very much.
Thank you for the question.
Okay, thank you. Is there any other question, comments, or sorry. All comments are welcome. So, Carlo.
To Renate, it's of course the appearance of a dimensionality too is very intriguing, and almost I would say sort of convincing. I mean, it's not plausible. Not convincing is too short. Plausible. It's a. Am I right that it's not so surprising as you were said? I mean, you yourself and but also others had indications about this dimensionality going from 4 to 2 when you go too small. Can you say something more about that?
Well, you know, of course, this is a result from 2004 or 5, and it came out of the measurements, right, in CDT. And I should say, so when we published this, I mean, we hadn't seen anything like this before, and my collaborators were not convinced that it was interesting at all. So then we published it, and then, well, many people jumped onto it also, right? So, and pointed out that other dimensions, so not the spectral dimension, right? That the people, the asymptotic safety people, right, had some kind of arguments using just renormalization group flows that 2 is a natural dimension. And you know, from lots of other corners, people have then said, yeah, look, yeah, it's 2, and there are good reasons also in my approach of why it should be 2. And you know, Steve Carleb wrote various papers. I should say I would always reserve kind of, you know, a degree of caution. You know, first of all, is this the same dimension 2? You know, for example, you know, we were very excited as there was the coincidence with the Rojava-Lifshitz thing, right? So sometime after we've published this, that I think even years, right? Peter Rojava wrote us an excited message saying, I'm finding 2, and it must mean it's the same, you know, my theory is your theory. And we looked at this actually, I mean, for several years and trying to understand what the connection is, but we couldn't. Yeah, honestly, it seems more like a coincidence. Yeah, and also, you know, the fact that lots of other people find 2. Well, it's a little bit like, you know, everyone finds A/4 for the entropy. I mean, once you know what you want to get, yeah, there will always be, you know, there are so many loose ends in our models and theories that you can find it. But still, I mean, it's interesting, and coming out of a simulation, it has some flavor of reality, right? To me. But yet a completely different question is there a phenomenology associated to that? And no one has really come up with anything. I mean, gravitational wave people, like Mary, who gave a talk here a few days ago. Yeah, they do some quite kind of effective modeling on the propagation of gravitational waves and how it would be affected if one has such a dimensionality. Well, I think it would need really a better understanding of how matter and or light, interact with these gravitational degrees of freedom to really come with a nice prediction from this, and whether there is some phenomenology associated with it. Does this answer your question?
Yeah. No, it's completely. I just wanted to understand how you saw about that, because I knew about these papers by Carli, by others, and the various results, and there's even a vague resemblance to spin forms. But I just wanted to get your sense about this various idea. This is pretty clear. What you have.
So one last thing I want to say. I think it's very useful. Why did everyone jump at it? Because there are so few things we can calculate in quantum gravity. And all of a sudden, you need only a model that has, a Laplace operator flying around somewhere, roughly speaking, and you will be able to compute a spectral dimension. And and again, in the context of these, random geometry models I talk about, these are genuine observables, and you can kind of rule out things just looking at this observable. Again, with a degree of caution, but nevertheless, then you can understand whether something is a branched polymer, for example, right? By looking at the spectral dimension, if it's 4/3, it's very highly likely a branched polymer, and then it doesn't look good. It's not an interesting theory of quantum gravity, most likely. So it's quite powerful. Yeah.
Thanks. Thank you.
Thanks for the question.
So, other questions or comments? This discussion. I see everyone very tired. I know you hate me, but just a couple of curiosities to Carlo, actually. Not related to my work, actually. We debated about that, but no. Maybe general, one more specific and one general curiosity. No, maybe just one very general. And this is, I think, about all what we discuss here, because there are various approaches. Not everything is an accord with, not everyone is an accord with others. And I read somewhere in, for example, in a review by Ashtegger, that loop quantum gravity seems to be, which is a very drastic approach, I would say, to quantum gravity. No space-time, underlying space-time, even the Renate approach, actually, in this sense. And they say maybe string theory, which is another one of the very famous candidates for theory of gravity, in a sense, could be, in a sense, implied by loop quantum gravity as some kind of effective theory. So, because usually the standard idea is that there is some kind of dichotomy, or at least from outside of this community, there's such kind of idea. I was curious to have your point of view in this consideration. I read.
Thanks for the question. It's an idea that has been put forward various times, and various people have tried to explore it. And there are some hints of connections. Hermann Verlinde has a result on in which he he derives the loop quantum gravity fact, the theory in 2+1 dimension from a string theory perspective, and so there are some hints. The possibility is open essentially because string theory doesn't have a genuine full sort of non-perturbative formulation, right? String theory is it's a rich collection of results without a center, so to say, because there are the various sort of ideas of the various semi-classical expansion and perturbations which are connected to one another. And as Polchinski used to say, string theory is based on a fundamental principle. We don't know that principle. String theory has a fundamental equation, so we don't know those equations. So it's plausible that it's possible that if people were able to develop string theory better, could find a description of quantum space-time, a local description of quantum space-time that matches the one of loop quantum gravity. So it cannot be ruled out a priori. On the other hand, there are strong arguments against, because string theory requires, it's really an attempt to solve a different problem, which is a unification of all the forces. So it requires extra dimensions, it requires an infinite number of fields, it requires a supersymmetry, all things that seems to go in the opposite direction that what loop quantum gravity or what Renata is doing, namely the idea that, no, come on, I mean, there can be a quantum theory of gravity by itself, like there is a quantum theory of QCD, of strong interaction by itself. So that seems to be so different. I mean, why in loop quantum gravity one would need a gravitino and extra dimensions and all that when there is already ultraviolet finiteness? So the answer is I don't know, and if I had to bet, I would be disturbed. On the other hand, right now most of the people doing string theory are not really doing quantum gravity, if not doing ADF CFT. So they have this idea that you look from the outside, and everything you can say about the bulk is you go to the boundary, you set a quantum field theory on the boundary, which it's from the perspective of a loop person, it's avoiding the problems. It's mapping the problem you know where to work out. But there's no ADS boundary, there's no space-like boundary, presumably in our universe. So I wouldn't close the door, and if anybody has ideas of how to, get out the quantum gravity state, the spin network states from string theory, I would be excited, or vice versa. Find string-like excitations in quantum gravity from some region, I would be very interested. But it's not on the top of my research priority. When we have an open problem, it's tempting to put everything inside, and it's tempting to say, well, maybe we all agree on that. And history has things like that, but history is also full of cases in which a lot of people study something and just turn out to be wrong, and something else turn out to be right. If I had to bet, I would go in that direction. I mean, supersymmetry is telling us that. The nature is telling us that low energy supersymmetry is not there. Nature is telling us that the cosmological constant is not negative, as string people expect. Nature is telling us that there is no production of black holes at CERN as string theory is expected. This does not rule out string theory, but of course, but I think we should listen to nature in the indication which is given. So if I had to bet now, I would say that it's more likely that Renata's statistical approach could give a better description to quantum gravity or loop quantum gravity, which is it's a theory of quantum gravity, as I open in my talk to say, it just could be that. And then the problem of unification, well, it's open, we don't know. let me just close, because this is related to the comment I made to your work. I didn't mean at all to say that your work is not interesting or non-valuable, but not at all. I mean, in fact, I listen very, very carefully. It's this theoretical physics, no doubt. You take a hypothesis, you study it, you try to study the consequences. But one thing which I would object is that of the various justification you said is that, look, there's all these people that take seriously, Maldacena and company, that take seriously the page curve. And so I think, it could be that they're wrong. I think that they're wrong. They are trapped into an hypothesis. Maldacena made his career out of the, bulk boundary thing. And the idea that things described from infinity exhaust everything you can say about, and I think that there are some hypotheses there which in current theoretical physics are given for granted, almost as they're not treated as hypotheses anymore. They're treated as what we know about gravity. I mean, so there are a lot of people who think what we know about gravity is a Beckstein, quantum gravity is a Beckstein bound. I think it's wrong. That doesn't mean that studying as a theoretical physics is hypothesis or is anything wrong, but I think one should keep very much in mind that perhaps we want to study it to show that its consequences are contradictory to what we already know about nature.
No, but just to clarify, I was not disappointed on your comments or something like that. Is that when a scientific discussion, I think it's interesting. I don't know, at least it's my way of doing scientific discussion. Very, very hot. It should be some fire in science, in a sense. If it is cold and too calm, it doesn't matter.
Fine.
And can I ask before? Okay, and I don't understand if Tom had comment or not because the end. But I was also wanted to do a similar question also to Renate. So we have different point of views. We are at the end of this long conference where many approaches compared, and so what do you think about unification of different approaches? You're very interesting, I would say, even look quantum gravity. Actually, I studied.
Yeah. So one of the things I really want to emphasize is going away from comparing formalisms, because if you compare formalisms, they're just so different. You ask about string theory, you ask about quantum gravity, you ask about causal dynamical triangulation. They seem just kind of completely incompatible because they're so different ingredients that go in, right? So if one instead, and of course it's forced upon us because we have so few things we can calculate, but nevertheless, even this, maybe this stupid, you could say this very banal thing with the spectral dimension, that I mentioned in answer to Carlos' question, shows you that a more fruitful approach is really, to compare outcomes. Of course, we don't have phenomenology, but we can try and find some, gauge invariant quantum observables, which we hopefully can compute and compare. Right, because
I mean, some robust results. That's if you have results in many different approaches, like black hole entropy or so on, maybe likely are correct.
But of course, black hole entropy is really very semi-classical, and I'm still in that class of people who thinks it hasn't, unlike what people have been saying since the 1970s. What has it really taught us about quantum gravity proper? I mean, and it may not in the end tell us very much. I mean, although that is a mantra that's so often repeated, that people, I think, start thinking, thinking about it. Well, it may simply not lead us to quantum gravity. Yeah. I'm very curious, picking up on Carlos' comments on string theory. Of course, really that community has moved away from trying to explain quantum gravity. And then, there's the idea of CFT correspondence. I feel extremely gratified nowadays when people, even famous people, acknowledge they really want to understand this bulk gravity in the bulk, then I want to say, yeah, hey, that's me. Or curious things that now happen. I think string theory is more and more forgotten. The whole, the page curve discussion, etc. For me, I'm old. That this goes back to the 70s and people arguing about, the failure of the Euclidean path integral. And really, it had been really relegated to the dustbin of history. And all of a sudden, the Euclidean path integral is back, but it still has all the sicknesses when you go beyond 2D that it always has had. But we understand, of course, more about it from a non-perturbative point of view. But to some extent, it seems that history is going in circles. But I do see it moving towards gravity proper. Also from that community, they're now saying, okay, we were motivated originally by string theory. But let me now really forget what I'm going to say. It doesn't really depend on any of these things. Let me do, okay, path integrals over two-dimensional wormholes. Well, interesting. Can you make it work in high dimensions? Is that my question?
Thank you very much for your comment. Is there any other question or comment for this discussion? It seems to me not, and I don't want to do whole questions actually. Only just very technical, not maybe it's general but technical curiosity in sense to Renata, and also Carlo can correct me eventually. It's just when I hear about discretization or lattice. In your case, it's not lattice actually. You have simplicial complexes and so on. But I think that very natural framework to describe it's some kind of discrete calculus like Q calculus and so on. In fact, I was mentioning Carlo because I know that it's used in loop quantum gravity, for example, sometimes as a regularization approach. I don't know if I'm saying something wrong, but you consider the Q deform version, for example, your Patti integrals, so on. And then is it playing any role in your approach, or?
You mean Q deformations?
Yeah, Q calculus in general. I mean Jackson integrals and so on.
No, I have enough. I have enough just with H bar and standard path integral. I mean, yeah.
Yeah, not necessarily with the H bar. I mean, you can have just also some length scale or something. I mean, like when you describe things in lattice, you can have lattice spacing and so on.
Yeah.
Okay. No, the answer is
no. No, I don't really understand the question to answer it properly, I'm afraid.
I mean, I was asking if this kind of techniques plays any role, or you try to use because are very natural in on discrete structures.
Yeah,
instead of using
but
standard
again,
calculus, using.
Yeah, we don't take of course, the discrete structure is of course not the real physics. It's just a regulator. So we don't take it seriously from that point of view, but we are after a continuum limit, a scaling limit, where most of this lattice structure will completely disappear.
I see.
But that's different in some approaches, of course, where we can take this seriously, and some people do that, and then, well, all kinds of new possibilities appear, and also people use things like, I don't know, discrete exterior calculus, and you can, of course, build whole, classical framework on these piecewise flat things, but that's a whole different universe. That's very interesting in itself, but in a way only tangential, to what we do.
So that's your point. You don't think that this could be a fundamental description. Anyway, you have to count these things as at best as regulators. You don't think it could be discrete, fundamental discrete structure of nature?
Well, you see, yeah, that's of course an endless debate also in the quantum gravity community. You know, the idea about fundamental discreteness and what this actually is supposed to mean. Yeah. So yeah, I think there is a lot of wishful thinking, you know, and naive thinking, naive classical thinking of what is fundamental discreteness. You know, from that point of view, I would say, you know, for instance, what happens in loop quantum gravity, the fundamental discreteness, what one means there is something completely operationally well defined. You know, a certain operator is about geometry, it has a discrete spectrum, great. But people use this fundamental discreteness in very hazy ways, right? Of course, sometimes it's completely meaningless. You know, I have of course, I can Hilbert space states I can label by discrete labels, and I label them by continuous labels, you know, and they describe the same thing. So, for instance, you know, one has to be slightly careful what this discreteness is all about. What I want to say, of course, if you are postulating Planckian discreteness, then the dynamics at the Planck scale will typically be very dependent on how you set up things. And usually these are just, you know, structures you're dreaming up. Well, I like whatever, you know, I prefer squares to triangles. I believe, you know, the Planck scale, everything is built from little squares. And you believe triangles. Well, let's compare. Well, there will be Planckian observables that will be sensitive to this. So whenever you adopt such a point of view, then you have to learn how to live with the multitude of, you know, phenomena at the Planck scale. If that is avoided, if you say, no, look, this is a regulator, I shrink it away, right? And I only look kind of at, as I renormalize, I'm interested in asymptotic behavior, then you can arrive at a series that's well defined at the Planck scale and has universal properties at the Planck scale. You see, and there are not so many mechanisms that achieve this. And, you know, the one uses when one, you know, in this critical systems way of thinking, like we do, statistical model, finite regulator, you know, you remove the regulator and you hope to find a continuum theory in the vicinity of a higher order phase transition point. Yeah, that if you're lucky, then your results are kind of unique, you know, and maybe parameterized just by a few parameters that you can try and fix. But you have to be careful that you're finding yourself that in an infinite universe of possibilities, which all have, you know, different physics associated with them.
Sure.
Yeah, if I may, I agree with what Renate is saying, namely, some sense one expects discreteness of some sense, but the idea of discreteness is often used in a misleading way and taken misleadingly. I don't think it makes sense to think that after having done quantum gravity all my life, the idea that you can do quantum gravity by saying, oh, space is just a discrete lattice with a lattice spacing which is Planckian size. It just got wrong. First of all, because there's no reason it be like that. Second, because it's based on very weak assumption. And third, because like Renate is saying, if it was like that, we have all sorts of possibilities, open up 2,000 alternatives. If you look carefully, none of which works actually, and we would have seen that in breaking of Lorentz invariance in gamma rays already experimentally, which we haven't. So that's one of, I mean, the quantum gravity is connected to experiment. That's a good example. I mean, theories which break Lorentz invariance have been ruled out by observations, astrophysical observations. So I do expect there is some discreteness, but it's much more subtle that just making a discrete calculus. In fact, you know, I mean, it's funny because Renate is there. I mean, sorry for it was making you smile because the discreteness of loop quantum gravity, it's a discreteness of the area. So it's a physical thing. I mean, if we could in principle, if we could make a scattering, total scattering amplitude with Planckian precision, we would expect certain eigenvalues if loop quantum gravity is correct. And similarly, certain eigenvalues of the volume. And when Liz Molling and I published this paper with the value of the volume, there was a mistake. It's a famous story at the beginning of loop quantum gravity, and Renate Lowell found a mistake, and in our paper,
don't embarrass me here.
Published the right eigenvalues of the volume, no, embarrassing us at the time, which we had a wrong thing in our paper. So but those eigenvalues are a quantum. So it's not, no, you know, angular momentum is quantized in standard non-relativistic quantum mechanics, which doesn't mean that there's little bits of angular momentum and discrete in the classical sense. Rotational invariance is perfectly preserved in quantum mechanics, and what is quantizing means when you interact with something, when you measure something in Copenhagen terms, you just get certain energy, certain levels. So that's how loop quantum gravity predict discreteness. That's a possible way in which there's discrete quantum gravity. Maybe there are others, but I would definitely not take it seriously. An arbitrary discretization of space as a good model of quantum gravity.
But just to be the advocate, the lawyer, I don't know, of the devil, I would say, in a paper of you and Bianchi, you proposed once that I'm very curious to understand in what sense, in this respect, that fundamental rotation group could be SU2Q, because this lead naturally to cosmological constant, for example. So when you have minimal scale, in particular Planck scale, and maximum, and some cosmological horizon, for example.
Yeah, but that's
in what sense in this context?
Yeah, in fact, there is a version of the loop quantum gravity amplitudes, which was developed by Mushin Han and before by two people, I forgot the name, Hellman and
I know the works.
Yeah. And in fact, it's a very good version which uses Q deformation and use quantum groups. And in fact, in my book, I indicate it as presumably the best version. The reason is it's because it's really completely finite. It's not just ultraviolet finite. There's a theorem. The amplitude is not just ultraviolet finite, but it's also infrared finite. So the amplitude really finite, which doesn't mean that one might still have to renormalize because with the Planck scale. And
no, sure.
But that comes in, yes. And the beauty is what you said, namely the Q deformation comes out not as in the description of space. In fact, it's an infrared thing, not a ultraviolet thing. It comes out by limiting. If Q is the root of unity, you limit the representation. So you have a maximum J. So you have a maximum area. So locally, you can have a locally de Sitter, but not too much close. You're not too much big in the sense, and so the Q is related to the cosmological constant. So this is a version of LQG which is beautiful mathematically, but nobody uses it because it's too complicated.
I see. Thank you very much. Other questions? Oh, I think that everyone is very tired. This was a 5 days conference on 9 hours every session without breaks practically. So I think we are really at the end of this beautiful experience.
Can I thanks in the name of everybody, the organizers, for having done that and for bringing all us together.
You're welcome. I think. Also, in name of our organizers, if they want to say something to close.
Thank you. Thank you to everyone for the participation. Really, it was really nice. Really nice.
Bye, everybody.
Okay. Bye, everybody.
Bye. Thank you very much.
Bye.
Good night.
Bye.
Thank you. It's great. Thank you.
usual.
I mean, Luca, you have so many questions.
First,
you could have prepared a few words to end the workshop at least.
First of all, you can also close the live. Giulio, close the session.
Okay, I think I can.
So that we will be free to